I guess. Well, good morning, everybody. Thank you for coming to this tipping points cross-working group session. I know that tipping points or tipping elements or tipping whatever mean different things to different people. So we'll try to essentially put them in context here within sort of the Earth system modeling community, and particularly within CMIP 7 context. So this session is organized by Betty and myself, and okay, stop moving. I can't, okay. So especially over the last several years, interest in evaluating risks associated with crossing individual or compound tipping points within the Earth system in the presence of especially increasing warming has significantly increased. And such tipping points include, and I'll show you a schematic on the next slide, include both reversible and irreversible changes. And they can include, for example, high latitude permafrost, Atlantic meridional overturning circulation or AMOC, Greenland and Antarctic ice sheets, and boreal and tropical forests. Right away, there might be a controversy here because it's unclear what reversible and irreversible mean, because they usually use single metric to determine those reversibility issues, and it's usually the global mean surface temperature, while the spatial distribution of that temperature might be quite different between a recovered space or recovered state. So in any case, there are already two proposed efforts within CMIP 7. One of them is tipping point model intercomparison project. That's called, and the goal is to obtain such events that are listed here and assess any related uncertainties, again, reversibility and recovery aspects and related things. And the second one is what if MIP modeling intercomparison project, what if MIP in short. And this one investigates extreme outcomes, impacts, risks, and that are associated with such events, assuming that they have already happened. So that's the distinction between TIP MIP and what if MIP. So the goals of this particular cross-working session are to introduce these intercomparison projects along with several other related international, mostly European efforts, and therefore many of our participants are from Europe this morning. We'll be reviewing related national efforts within the US. I don't know whether there's any or not, as far as I know, and gauge interest of the community, in particular CESM community, with respect to these efforts. The next slide. So this is a schematic from a Science 2022 paper by Armstrong and McKay. It's essentially showing various tipping elements in this. I mean, they are not tipping points necessarily, but tipping elements. And they include, as shown here, Atlantic overturning circulation, Labrador Sea subpolar gyre changes, Barents Sea sea ice collapse, Greenland ice sheet collapse, Antarctic ice sheet collapse, etc. And in this case, they are color-coded. There's also sort of shape coding as well. Those are the sort of when those tipping elements will tip based on the sort of estimates of global warming levels. So this is sort of, I think you may see this schematic in other presentations as well. So without too much delay, so this is the agenda. And we'll be starting with an introduction to TIP MIP. Then we'll have Betty talk about what if MIP. And then we'll have Laura Jackson from UK Met Office. She'll be talking about North Atlantic hosing model intercomparison project, which is also related. That's called NA Hose MIP. Then we'll have overviews of two Horizon 2020 projects, Optimism, ESM, and TIP ESM. I don't know how they pronounce it, TIPism or something. And Didier will be presenting those. And the actual leads of those projects could not join us because as we speak, there in Brussels, there's a review of all these Horizon 2020 projects right now that's ongoing today. And then Peter here is going to talk about climate interventions with CESM. And then we are hoping to have a 15-minute discussion about what we will hear and then what we can do going forward. So let's go with our first speaker. It's Sina Loriani from PIC, that's from Germany, and he'll be introducing the TIP ESM, TIP MIP, sorry. Go ahead. So you have about 15 minutes or so. If you can leave 5 minutes for questions, that'll be great. Go ahead, please.
All right, thank you. Can you hear me well in the room?
Yes, yes, we can hear you. Yep.
Perfect, and I'll just share my slides. Yeah, thanks for the invitation and thanks for the introduction, and thanks Gökhan for taking us through all these different MIPs and acronyms that involve some form of tipping in them. I'm speaking here on behalf of the TIP-MIP team, so the Tipping Point Modeling Intercomparison Project. It's led by Ricarda Winkelmann, and I'm speaking on behalf of also Jonathan Donges, Donovan Dennis, and the larger TIP-MIP community that has been assembling over the past years, actually, to form this initiative. And I'm very delighted to talk to you guys here and present this to you. So we've already seen this graphic right now. So in 2022, we put together this review of tipping elements in the Earth system. You see that they're kind of well spread out over the globe. And then last year for COP28, we did an updated large assessment, the Global Tipping Points report. So you can see the cover on the top right, which was an assessment with more than 200 authors contributing to this. Maybe some of you are in the room, I cannot see that so well. So, and tipping points have been an active area of research recently. And our working definition has been in both of these assessments that a tipping point occurs when change in part of a system becomes self-perpetuating beyond some threshold that leads to substantial, widespread, and often abrupt and irreversible impacts. So to us, abruptness and irreversibility are kind of symptoms of tipping that emerge from these self-perpetuating dynamics. The IPCC has also increasingly acknowledged this notion of tipping and acknowledged the high risk that's associated with it. But so far, most risk assessments do not account for potential tipping dynamics. And there's a call for an improved understanding to comprehensively manage risks and respond to loss and damage associated with climate change impacts. So this is from the COP28 Global Stocktake, and there's been increasing interest also. So for example, when recently the IPCC, during that process, there was a membership process to see what the members of the IPCC membership states wanted as a special report. Largest endorsement was for the topic of tipping. So this was not selected in the end as an IPCC special report, but the interest is huge. So what we want to look at in the tipping point model intercomparison project is at the different dynamics and different dimensions of tipping. That includes key feedback processes, what the critical thresholds are, the characteristics and timescales involved, the different types of uncertainties that are associated with tipping, like already mentioned, irreversibility or reversibility and hysteresis, and finally the interactions between the different tipping systems. So huge and big research questions. And what we went for right now is in the first phase, a subset of tipping elements, so a subset of these this list of tipping systems that you have seen before. So in this phase one, we are focusing on these systems, which are the two ice sheets over Greenland and Antarctica, the AMOC, or circulation dynamics in the Northern Atlantic, involving also the subpolar gyre, tropical and boreal forests, and permafrosts in boreal regions. And this is because these are global core tipping elements with impacts on the whole Earth system. We understand these comparably well. They are captured, or the most essential dynamics are largely captured in state-of-the-art Earth system models. And we can also study longer timescales and the possible commitment gap that comes with the ice sheets, for example. So this is kind of the, let's say, hierarchy or family tree of TipMap-like experiments, what we envision. So what we're looking at is climate forcing over simulation time. And here you see 4 types of experiments. One is a baseline experiment, ramping the forcing up, then a constant climate experiment, so these commitment experiments, then ramping down from these branches and doing the ramps at different rates. So these are the 4 types of experiments that we're exploring in the context of a notion that emerged during the discussions over the past years that we would label as see what happens to the different tipping systems if you follow these forcing scenarios. And this is part of the different EU projects also that Gokhan mentioned, including ClimTip and TIP-ESM, about which you will hear later a bit more. Then this kind of an additional stage is make it happen, to add system-specific forcing scenarios, for example, deforestation for forest systems or freshwater forcing on the North Atlantic to and force dynamic and explore the stability of the system. This is also in conjunction with partnering projects. And finally, and we will also hear about more about this later, is to look at extreme forcing. I've heard the sentence, we know how to kill the AMOC, and also heard this about other systems, that modelers know how to take these systems away and see how, can study the impacts that unfold. And this is, has a nice interface with WhatIfMap, and I think I saw Betty in the room also, and I'm delighted to listen to her talk then in a minute. And the idea is to do these kind of experiments across a wide range of domains, including Earth system models and offline models. And just to give you a flavor of, or an overview over the history of how this came about. So we launched TipMap in 2022, and since then had a series of many online and in-person workshops, most notably the one in November 2023, the Hereo seminar that we had close to Berlin, with many modelers, especially from the European context being there, but also some US delegates. And here you can also see Betty was also there. And yeah, then we had a series of continued workshops this year, most notably also the kickoff of the different EU's or workshops in the context of the different EU Horizon projects, TIP-ESM, ClimTip, and Optimism. And this is kind of the outlook that we have in alignment with the upcoming CMAP cycle. And so basically from this history of TipMap meetings, we are now looking on a large TipMap family. This is the rough structure that we have. So we have different domains, coupled systems, Earth system, coupled and Earth systems, ice sheets, permafrost, ocean, biosphere, and something like a cross-domain methods and risk assessment group. And what we try to map, and it's kind of difficult because there's so many MIPS and so many tipping involving initiatives, is that this connects very well to all these different initiatives. And what we're trying to do is kind of harmonize and find synergies between all these different efforts to make best use of our computing time. Just to briefly show you that we have a range of models that have self-assigned themselves to run the different TipMap experiments. If you're interested, visit tipmap.org. There you can find all the links for model sign up, newsletter sign up, and so on. Coming back to the structure. So we have these different modeling groups or different domain groups which have been organizing over the past couple of months. The ESM group is probably the most interesting one in this context of this workshop. As Gokhan said, unfortunately, Torben and Shuting couldn't be here. Same as for Chris Jones and Matteo, who have been taking the lead on this domain. But just to show you a brief outlook on the proposed protocol that we have right now is to follow this TipMap protocol that I've shown you earlier and align the models and the temperature ramp up. So to adapt the forcing such that we have an 0.2 Kelvin warming per decade in all the different models and translate what this means into the different emissions per model. yeah, in total, this amounts to about 1,900 years of simulation time, and this is what we have been converging to within the context of TIPMIP ESM. This is part of what the different European initiatives have now been aligning to. So we had a couple of meetings also this year. Last month we had this ESM 2025 General Assembly. This is also a project looking at system modeling, and we had a TIPMIP breakout there, in which we have kind of finalized the protocol. Some things are still open, so there's an open diagnostics list still to be amended, and details like the names of the runs, but basically it's the protocol that I've just shown to you. And we have a series of ongoing domain workshops, and what we plan for end of this year is a back-to-back event. So we applied for a session together with Betty, John Dunn, Anna Liddy, for a tipping point session at AGU. And in the week prior to that, so the first week of December, we are now putting together plans for TIPMIP General Assembly. So this is planned to be a 3-day meeting in the week before AGU, as I said, so the first week of December, so you can mark your calendars. So the details are still pending, and what we plan to do is to do this at the East Coast of the US, so close to AGU, which happens in Washington this year, to have this maybe in Baltimore or New York or Washington. So to see such that, it's not our turn to come to the other side of the ocean and not let you always have the long flights to us. Another news, so we have secured quite some funding and are hiring now a TIPMIP data manager. So this application is still open a couple of days. So if you have an interested person, interested to work at the interface of model intercomparison and big data needs and so on. So please direct them to us. We're still hiring, and soon we will start put online the job offers for different tipping point modeling scientists and risk analyst positions here at PIC and in Jena, which I should have said in the beginning, that TIPMIP is co-hosted by the Potsdam Institute and the Max Planck Institute for Geoanthropology. And we have put together a special issue proposal. What we want to do is to do this across different Copernicus journals GMD, Earth System Dynamics, and others. And so that the proposal is ready. If you have suggestions for a contribution, then we're still happy to receive them. For this, we would need a title, author list, and a preliminary abstract, ideally, which we could then append to this proposal for a special issue. And with that, I hope I'm still in time. This was it. Please go to to tipmip.org or shoot us an email. And happy to discuss.
Thank you very much. Any questions for Sina about TIPMIP? Protocol and all that nice stuff? And it's not, just to clarify, this is not going to be part of fast track, I believe, right? It's delayed in that sense.
Actually, so what we're trying to do is to have the first suite of models run already this year. So we have, I think, 10 Earth system models signed up within TIP ESM that would, that indicated the interest to run already the protocol this year. So this would be ideally starting soon.
I don't know whether people are familiar or not, but the chart that Sina showed is asking for certain degree C per decade, right? 0.2 degrees C per decade increase. And with the emissions driven systems, that is going to translate into different amounts of carbon that's being put into the system. So that's one proposal. And then the competing proposal was some sort of, what was it? Flat 10. That's the 10 gigaton, I believe, per year emission. And I guess instead of that, this particular approach was favored. Do you want to say a few more things about that?
Yeah, sure. Happy that you bring this up because this was one of the major discussion items we had over the past meetings. So the idea is to have, because in TipMap we follow this multi-domain approach that we want to have the same type of protocol, not only for the Earth system models, but also for the offline models. So for example, have the same type of protocol that drives the offline ice sheet models. And for this, it's hugely beneficial for us, which we have also seen in pilot experiments, to align all the models in temperature, because then we can derive like policy relevant conclusions that are aligned in temperature, both for the ice sheets, but also for the Earth systems and the other domains, which does not exclude the flat 10, which is, we're happy that this also is part of the CMIP family of things. So we've talked a lot, for example, also with Ben Sanderson, and basically agreed on, or this is the conclusion that I took from past meetings, was that, and for things that we're interested in for tipping points in temperature, this is where this TipMap protocol fits quite nicely with the temperature alignment. And for questions where we're interested in carbon budget and the carbon cycle, then the flat 10 would be more appropriate. So these are two nicely complementary approaches.
Very much. There are no other questions. We'll move on to our second speaker, and that'll be Betty, and she'll be talking about what if MIP.
So I want to introduce here a project called the What If Model Intercomparison Project. It's from the high-risk group of theme of the WCRP Safe Landing Climates activity. And this project is being developed by myself and Gabby Hegrill at the University of Edinburgh. So I switch. So Sinya has already introduced this a little bit in terms of these different ways of looking at tipping points from what he was talking about, see what happens, see if the models can produce these tipping points and what are the dynamics and feedbacks in between, make it happen. And then this project is, it has happened, as Colin Jones has named it. So we want to identify storylines of extreme outcomes in the future. In other words, high impact, low likelihood events, and then design CMIP-7 experiments, assuming a definitive tipping of some of these tipping elements. In other words, again, it has happened. And the idea is that these experiments will be simple enough that a number of models can produce them, and you may not reach a tipping point just by allowing the model to produce it. And so we hope to have a multi-model ensemble of CMIP-7 and probably also some CMIP-6 models as we get started with AOGCM models. So we've identified, again, some similar tipping elements to what you saw Sinya, in particular the boreal forests, its northern expansion and southern dieback, Sahel greening, browning of or deforestation of the Amazon rainforest, and then two ice sheets, the Greenland and West Antarctic ice sheet collapse. In addition, we're still working on, but we're thinking of a boreal permafrost collapse, and also we've been talking to the TipMIP and the North Atlantic HOSMIP people about an AMIC collapse. So we want to, again, assume the tipping point has happened and prescribe a tipping element change for each of these, and then look at the consequences. Some of the benefits is that models do not have to have these components interactive to be able to participate. They can be prescribed, they will be prescribed in their models. And we're hoping to get estimates of the uncertainties and the consequences by having a multi-model ensemble here. In terms of the outcome, this very policy relevant, both for local and regional adaptation and vulnerability, but also far field impacts on ENSO, for example, or maybe global risks where there's changes in the carbon cycle, and also aerosols. And we hope that these simulations will be used by climate services and all three working groups. So we've designed our proposal to be very much synergistic with TIP-MIP and some of the other tipping point consortiums and projects. So the plan is to use the CMIP 7 and, as I said, CMIP 6 emission-driven simulations with a very similar protocol here to what Senia showed on the right here. It's global mean temperature versus time. Each model will ramp up. In this case, this is just showing UK ESM 1.1 to get 0.2 degrees Celsius per decade and determine what the appropriate carbon input is to maintain that. And then starting from a PI control, which we call the global warming level of 0, and then branching off at different global warming levels. Currently, we're thinking at a 2 degrees Celsius warming level and a 4 degree where you zero out the emissions. Let the models run for about 50 years to allow them to kind of stabilize, and some preliminary experiments show that this will work. Then prescribe the tipping point element and then run the model for 100 to maybe 200 years. So relatively short simulations, which we've considered kind of the people and computing time that it takes to run these models, but also to be a little bit more carbon friendly by not having long simulations. And just as I mentioned, this is consistent with what some of the other proposed design experiments. So just to show you a couple examples, this is for the boreal forest experiment that is being developed. I should say this is still under development, and we have teams, some of the same people you saw in Senia's under their domains are involved in this. And this takes into account the fact that boreal shrubs and trees are expanding north currently and becoming more stressed along their southern margin. So we want to develop a storyline of what will happen at 2 and 4 degrees global warming levels for the boreal forest using modeling, some expert judgment. This is just one example, the figure on the bottom, from a study done by Gerten et al. With the CMIP3 models, where they showed here in red along the northern boundaries of North America and Eurasia, that at 2 degrees global warming level, you'd have significant changes. You'd have boreal forests expanding north. And then additionally, shown in yellow and green, there at about 4 degrees, you see southern dieback. So an experiment could be designed that adds on this at 4 degrees. And in terms of boreal forests, just thinking of the biodiversity, the people and the fauna, permafrost, temperature, those are all something they'll have to adapt to, that they're vulnerable. But there's also a global influence, as shown before in many studies. Abby for Swan, for instance, that when the boreal forests extend northward, you have impacts on global sea ice. We've shown recently on the Greenland ice sheet and its retreats, carbon cycle, wildfire aerosols. Another example is what we call the Sahel greening experiment. And we know that the Sahel is experiencing significant wetting and regreening. And if you look at the figure on the bottom from the last IPCC report, this is June to August frequency of 1 in 10-year soil moisture drought. And if you look over Africa, there's an indication that models agree that this drought, and actually you can look at soil moisture too, will decrease going into the future at 2 degrees warming in the middle, and even more so at 1 degree warming. So we want to design a Sahel greening experiment that includes this climate change, but also may possibly taking in consideration what's called the Africa's Great Green Wall Initiative, where they want to reforest the Sahel region to stop desertification. So again, for regionally, it's very important in terms of the monsoons, water recycling, and even some indications, not just of Africa monsoon, but the Asian. And there have been some studies with models that suggest with a greening of the Sahel and Southern Sahara region, it affects ENSO variability, decreases it, ocean productivity, and North Atlantic tropical cyclone activities. And I should have mentioned, with the greening, there'll be a reduction of dust. So that affects some of these other instances. And then finally, just one other experiment to show you that we're been developing. In this case, Bill Lipscomb is involved in this, and it's looking at the Antarctic ice sheet. And we know that the West Antarctic ice sheet is losing mass and is Antarctica's largest contributor to sea level rise over the coming centuries. So again, to design experiments at global warming levels of 2 and 4 degrees Celsius, this just gives you kind of an example of what possibly could be for kind of a moderate and extreme configuration of the Antarctic ice sheet in 2 and 4 degrees. This is not from experiments that have looked at that, but rather from a project called the Antarctic Buttressing Model Intercomparison, where they looked at standalone ice sheet model responses to decrease in the buttressing. In other words, the effect of the marine ice sheet instability. And the one in the middle is from our model, CESM, running with this protocol after 500 years. And the one at 4 degrees is from Elmer Ice. So these models are very different. They both have the same forcing, but it just gives you an idea of what could be kind of a moderate and extreme. Still to be determined, but it gives you one example. We will, for example, include the meltwater still from, or any meltwater from a negative SMB, if it's negative, from these configurations that are imposed. And we're still considering, and it may be kind of a dream at this point, but you do, when you have an ice sheet melt back, you have a fingerprint around the globe of this meltwater where it may be higher in some places and lower in the others. And so to be able to do coastal changes with that may be a challenge for models, but it is kind of a dream of ours because there are regions like Bangladesh that will be affected, actually New York City too. So I just want to finish there. I won't show you the next slide. It just gives you an idea of the fact that we are developing teams around each of these. And I should have mentioned Peter Lawrence and Monica for the, and Jean Zhu for the vegetation experiments. But just end here with, if you want to know more, we've registered this MIP. It's a community MIP. We thought of doing a fast track, and we may, like the TIP-MIP project, have a lot of model experiments done in time, but it's right now a community MIP. You can email myself or Gabby. And for those of you that know me, I also have a lot of interest in paleoclimate. And so we have a poster out there, and it kind of, when I was thinking of what if BIP, kind of these paleo instances or perspectives on these changes. We've seen this in the past and what it could mean. So please come see the poster if you like.
Questions? So Peter, go ahead.
So Betty, I'm confused. Your previous slide said tipping points have already happened.
This one?
Now the next one.
Next one. Oh, I went the wrong way. Sorry.
Tipping points have already happened, and yet you're proposing experiments about future and will it cause tipping points? So I don't see the difference between this and the previous talk that was talking about future tipping points. So I don't see what's the difference.
I guess I didn't clarify. This is about future tipping points. So, and this was something Colin came up with that if you run the models like ours, coupled, well, many models may not have coupled, for example, West Antarctic ice sheet. Not even sure we will at the time. But you may not reach a tipping point. You may have to run thousands of years. So instead, these are kind of, if it has happened, maybe, or will have happened, maybe we should have said will have happened. I'll have to tell Colin that, at different global warming levels. Let's say at 4 degrees global warming level, the couple of models will not have produced that change in the Antarctic ice sheet or the Greenland. So we impose it, assuming that the models still have some deficiencies and cannot do it naturally on their own.
So you haven't concluded that these things have gone past tipping points?
No, sorry about that.
Okay.
It's getting close. Yes, some are getting close. Some would say parts of the West Antarctic ice sheet and has gone.
Another thing that I was going to say that I was labeling in my conversations with Colin tip MIP as let's see what happens MIP, because these protocols do not necessarily trigger a tipping point. They may trigger it. And that's why I was calling it let's see what happens. This one is providing more certainty, somehow instigating those tipping points to happen and see what happens afterwards. Kind of a distinction in my mind, if it's, yeah.
It looks at the consequences if they had happened.
Tim?
So I understand, how you can prescribe a change in the boreal forest or a collapse of Antarctic ice sheet, but one of the things you mentioned was AMOC. How would you prescribe the collapse of AMOC?
Yeah, that's why it's below the line for mine. And we have been talking to Laura Jackson and others, who's the next talk. And but then it's almost make it happen with additional fresh water. But I'll leave that. I don't want to, Laura is going to talk about that, but Laura and Didier and Wilbur and are thinking about that. So it's kind of an in-between see what happens and it has happened in the future.
Any other questions for Betty? Okay, let's move on then. If Laura is available, so we are a few minutes ahead, but Laura, are you there?
Yeah, I am. Just a second. Okay, can you see my
It's coming
my
up right now. Yeah, we can see it fine now. Yep, go ahead, please.
Okay, brilliant, thank you. Yeah, so I'm going to talk about AMOC thresholds in CMIP6 models. So it follows on from the last question to Betty. Yes, this is particularly about this project, the North Atlantic hosing MIP. And there's been a lot of people who've contributed to this. So, slide. So the AMOC is the standards for the Atlantic Meridional Overturning Circulation. And there's lots of different processes and circulations which happen particularly in the North Atlantic, which are transporting upper water, up the upper ocean northwards, and then that water cools, it becomes denser and sinks, returning back southwards. And then this overturning circulation transports heat northwards and impacts the climate. So we know that future changes in climate, such as warming, increase in freshwater input, are likely to weaken or will weaken the dense water formation and weaken the AMOC. And so the IPCC has judged that the AMOC is very likely to weaken in the future, but there's medium confidence there wouldn't be any collapse before 2100. So the question about AMOC collapse comes down to these ideas about AMOC stability. So theory and also a number of models now have shown that the AMOC can have two stable states. It can have an on state and it can have an off state. and the transition between those can be enabled by fresh water. So these figures I'm showing here are hysteresis plots. So showing the AMOC strength and the y-axis against the freshwater input into the North Atlantic. And so you can see for some amounts of freshwater input, you can have these two different states. And then there's also been evidence from paleo observations suggesting that the AMOC might have collapsed in the past because of large freshwater input into the North Atlantic. So the future input of freshwater from the Greenland ice sheet melt, we don't think is enough, well, it's certainly not as much as we've seen in paleo data. But there are still questions about whether our climate models are too stable, and whether there still might be a possibility of the AMOC experiencing a similar collapse in the future. So we want to understand what affects the stability of the AMOC. So that brings me on to the NA-HOSMIP, the North Atlantic Hosing Model Intercomparison Project. And the aims of this is really to examine AMOC thresholds, tipping points in CMIP6 models in the presence of freshwater forcing. So firstly, to understand whether CMIP6 models have a threshold in the AMOC, and then to understand whether if we can understand the different feedbacks that are contributing to the different AMOC behaviour, whether that gives us an understanding what the implications are for the real world. So we had 8 different CMIP6 models which participated in this, which had varying resolution and ocean component. And then for the experiments, we applied fresh water to the surface, 0.3 sphere drops, uniformly north of 50 north in the Atlantic. And then we stopped that freshwater input, or which we often call hosing, after 20 years, after 50 years, or 100 years. So this is quite a idealized and a very large amount of hosing compared to the real input we might expect from the Greenland ice sheet. But it does help us to understand the model sensitivities and how they differ. So these are the main results. These are the 8 different models which participated, and these show the AMOC strength as a time series. So the black lines show the pre-industrial control strength, and then the grey lines show what happens when we're adding that hosing. And so in each model you can see the AMOC weakens. And then the blue and green lines show what happens when we stop applying that hosing. So if we look at the bottom panels, the MPI models, we can see that the AMOC recovers over maybe 50 years, maybe 100 years, for each of the experiments with the MPI models. However, there are some models, such as CESM2, where they reach this weak state where the AMOC doesn't seem to be recovering. So after 50 years of hosing, for the CESM2, you reach this weak state, which stays, which doesn't recover for 200 years at least. And that's true for half the models that we tested in CMIP6. We found that they could reach a state where the AMOC doesn't recover when the hosing stops. So to understand why this is happening, we can take all those different recovery experiments and put them all together. And that's what we're seeing here. This is against years since the hosing stopped. So you can see the models, the experiments rather, where they stay in this weak state for long periods of time. These are the dashed lines. They started from a very weak AMOC state, and then they stay in that weak state. Whereas the experiments where the AMOC has only, is still reasonably strong after hosing, the AMOC then recovers. We see a similar situation if we look at deep convection. So this is showing the March mixed layer depth after hosing. And the top panels show the models where the AMOC then recovers. And you can see that there's quite strong deep convection still in the particularly in the Gin seas. Whereas in the models in the bottom, we can see that basically that deep convection has been switched off in the dune seas, and then the AMOC doesn't recover. So can we tell why different models are behaving differently? So we looked at a number of different things, and basically we we didn't find an answer to this, but we can say what it isn't related to. So we didn't find any relationship to horizontal resolution. So the AMOC stays in this weak state in the 1/4 degree model, but also in several 1 degree models. We didn't find any relationship to the ocean model type. A number of the models use NEMO, but they show sort of differing results. We also looked at mean state biases. So we didn't see any differences between the two groups of models in terms of the temperatures, salinities, or sea ice extent, or in terms of the deep convection, its strength or its location. And that's what I'm showing here, the strength of the deep convection. And again, the models on the top are the models where the AMOC always recovers, and the ones on the bottom are the ones where the AMOC stays in that weak state. And then another thing we looked at was mean state biases in terms of this quantity called FOV. And this is the freshwater transport in the ocean by the AMOC itself. And this has been proposed as an indicator of stability, which is why we looked at it. In particular, looking at the sign of FOV in the south of the Atlantic, at about 30 south. And so this shows basically that the models where the AMOC always recovers are the blue and green dashed lines. And you can see that some of them have positive FOV and some of them have negative FOV. So this indicator of stability doesn't seem to work. So these particular results and the protocol have been written up in this particular paper. And then we've moved on more recently, looking at feedbacks. So in terms of the AMOC, the transport of heat and salt throughout the Atlantic and into those deep convection regions can be an important feedback. So this is looking at the heat transport in the ocean by latitude. So latitude is in the x-axis. And this is again showing those 8 different models. And you can see, yes, and then the control heat transport is shown in black. The first decade is shown in red, and then it goes through the rainbow through to purple, which is the 8th decade. And you can see in all the models, as you maybe expect, the heat transport weakens at all latitudes because, or most latitudes, I should say, because the AMOC is weakening, which isn't surprising. And we also see that the models on the bottom, which are the ones where the AMOC doesn't recover and where the AMOC has weakened the most, the heat transport is also the weakest. So that's consistent. Freshwater transport is maybe less obvious. We do see changes around 40 north in freshwater transport. And particularly, we're seeing more freshwater being exported from the subpolar North Atlantic. And this fits with the fact that we're putting lots of freshwater into the subpolar North Atlantic. Some of that's been exported, but it's not enough to compensate the hosing. So to understand the feedbacks, what we really want to know is how does the AMOC weakening then affect the heat and the freshwater transport? So what I'm plotting here, so I've calculated here is the regression of the heat transport and the freshwater transport against the AMOC. So in the top panel, we're looking at the heat transport change per AMOC change over the first 80 years, and then the same in the bottom except for freshwater transport. And so I've plotted the models where the AMOC always recovers are the blue and green lines, or the blue and green colours. And then the models where the AMOC stays in its weak state are the red, pink, orange, yellow coloured lines. And you can see that there's a split between the two groups of models in the North Atlantic, sort of north of 50 North maybe. So what we're seeing here is that in the models where the AMOC does recover, those are the blue and green colours, there's actually, although the AMOC is weakening, we see an increase in heat and salt import into the Jin seas. So this increase in heat and salt import then helps keep that dense water formation going and the deep convection going. Whereas in the other models, the red, orange, pink and yellow lines, there's less import of heat and salt into the Jin seas. So that then helps keep the AMOC of the deep convection, helps keep the deep convection off and helps keep the AMOC in a weak state. So we can also look, there also seem to be important things going on in terms of the sea ice extent. So we've weakened the AMOC, we've cooled the North Atlantic, and then the sea ice has expanded quite a lot in some of these models. So if you look at the models on the bottom, which are the ones where the AMOC doesn't recover, you can see apart from CANI SM5, the sea ice extent has grown massively, and there's basically this is the March sea ice extent. Yes, and that sea ice covering then inhibits the air-sea heat fluxes, particularly in the Jin seas. You can see that we've no longer got that heat flux in the Jin seas. Whereas in the models where the AMOC does recover, you've still got large heat loss in the Jin seas. So we're suggesting that there are, there are a number of feedbacks which are helping these two sets of models, either the AMOC recover or the AMOC stay in a weak state. So when the AMOC weakens in one set of models, you get more heat and salt transport into the Jin seas. That leads to less sea ice, and the increase in salt then makes it less stratified because we're making the surface saltier. And that encourages deep convection and dense water formation and encourages the AMOC to recover. Whereas the other group of models, when you weaken the AMOC, there's less heat and salt transport into the Jin seas. And then that leads to more sea ice and more stratification, which suppresses the deep convection and dense water formation and helps keep the AMOC in that weak state. So moving on to conclusions. So in half of the CESM models, we saw there was a threshold beyond which the AMOC didn't recover after hosing. And we found that the AMOC recovery after hosing is related to the strength of the AMOC and the amount of deep convection after the hosing. And we find various feedbacks. So in models where the AMOC and the mixed low depth recover, there's an increase in heat and salt transport into the Jin seas, which helps to sustain the convection and dense water mass formation and encourage recovery of the AMOC. So yes, the initial paper is published, and we are looking at a feedbacks paper, which is in preparation. Thank you. Oops.
Any questions for Laura? Elizabeth?
Thanks for the great talk. So that last result you showed,
The
that
microphone on there? We
Microphone
can't hear
on.
it very well.
how about now?
Yes, much better.
Yeah.
Thanks for the great
Yeah.
talk. So that last result you showed, that the models that recover are the ones that don't have as much sea ice. Does that imply to you that in a scenario where you actually have global warming going on, where there's warming as well as freshwater hosing, that the models that didn't collapse, the models that did collapse would actually recover better in a greenhouse warming scenario because there's not as much sea ice up there?
That's a very good point. So we haven't done these exact experiments yet with warming, though that's something we are intending to do. I think it's definitely true that we might expect different things to happen with warming as well as freshwater input, and it's unclear. It's unclear at the moment, whether the sort of stability that we see it would be the same.
Very nice talk, Laura. Did you look at the gyre circulations in these models and the transports by the gyre circulations and how they changed differently between the ones that it stayed on and stayed off?
Yes, no, we have done that. So we've looked at the gyre, well, both the split between the gyre and the overturning transports in terms of the freshwater transport in particular and heat transport. And we've also looked at like the barotropic stream function as well, because there are some changes there, but we haven't found anything very conclusive to separate the models. Yes, we have looked at them.
So Laura, could you maybe say a bit about future plans in particular? I know I've heard you and the others discuss kind of some draft ideas for experiments for the CMIP7 models in terms of the AMOC domain.
Yeah, so we do have, that's actually as part of TIPMIP, the AMOC domain TIPMIP. We're doing something slightly different from the sort of see what happens experiments, because I guess the AMOC is already covered in terms of the Earth system models that are experiments that are being run. So we are thinking of doing some experiments there where we're adding some hosing, and we're thinking of doing experiments where we gradually increase the hosing. Well, I'll say gradually. We increase the hosing, but we do it at a sort of rate which is doable by sort of ESMs and stuff. So instead of having what we're doing here, which is a fixed amount of hosing, we sort of increase it. And we're also thinking of doing some experiments where we combine the hosing and the warming sort of scenarios that are planned for the ESM. This is it's kind of overlapping a bit with the what if MIP as well in terms of the AMOC scenarios.
Other questions? We are very efficient in this, so we'll have plenty of time for discussions. So thanks, Laura. And if you can, stay around for the discussion at the end, but we understand if it's getting late there. So our talk now is a project overview of the Optimism and the TIP ESM projects, some EU projects, and Didier, correct me if I get your last name wrong, Swingedow will present for these two projects.
Okay, thank you. Can you hear me well? I assume.
Yes, everything is fine.
Great. So yeah, so I'm replacing and talking for Torben Koenig and Schottingen, who cannot make it today. And I will present the OptimESM project led by Torben Koenig. OptimESM meaning optimal high-resolution system models for exploring future climate change. And then I will also present TPSM, which means exploring tipping points and their impacts using Earth system models. And for this one, the PI is Schottingen from DMI. So these two projects are really related, so that's why we present them all together. So the first one is an EU project, and consequently, it's gathering a number of institutes in Europe that are represented there. But also it's having some international collaboration, notably with the US, with the NCAR that you can see on this map, and also in Asia and South Africa. So it's gathering 4 ESMs, so Earth System models developed in Europe, and also other models for impact study or integrated assessment. So the concept of this project is mainly to go towards CEMIP 7 and so to help the development of CEMIP 7 models. So you can see on this figure the models depending on their complexity, the number of components included and processes included, and the resolution of the models. And so OptimESMs will help to develop post-CEMIP 6 models to start upgrading process representation as compared to what has been done in CEMIP 6. And the target is to reach a CEMIP 7 configuration at the end of the project. And most notably, the innovation here will be to try to develop a hybrid resolution approach, which means that this project will try to increase the resolution in terms of dynamics for the ocean or for the atmosphere, since it's well known that resolution matters a lot for this type of processes. While for atmospheric chemistry or ocean biogeochemistry, which are costing a lot when you are increasing complexity, we will remain into coarse resolution, since it's assumed that resolution is playing a lesser big role than for the dynamics. So this project is also defining a few idealized scenarios that are represented here, and so this is really in line with protocols developed within TIP-MIP and also What If MIP. And so, of course, we are trying to align together and propose consistent framework. And so OptimESM, in a sense, is also providing first tests of this type of scenario. So the idea is to work in Earth system model emission-driven scenario, increase the emission to increase temperature, and try to stabilize temperature to follow, in fact, policy decisions, since now in the policymaker world, people are mainly talking about warming levels, so that's a way to cope with that. And also considering a few overshoot scenarios, since, for instance, the target of 1.5 Kelvin of global warming is now very difficult to reach, and so there are overshoot scenarios that are now considered. And so this will allow, also in a sense, when we are ramping down the emissions, thanks to new technologies, for instance, to see also if there might be some irreversibility. And so this framework will provide the core for ESM simulation, also for TIP-MIP, as mentioned, and also TPSM. So here are a few examples of Earth system models that already performed a few tests. So this concerns the UK ESM model and CNRM ESM model, so developed in the UK and in France for CNRM. So they are emission driven. So we are showing here on the left the change in concentration of CO2. So the target is really to obtain stabilized global mean temperature. So that's kind of inverse problem. So you are trying to find the emission and the concentration that are allowing you to have stabilized temperature. So that's why the protocol is model dependent, depending on the climate sensitivity of each models. So here are a few results obtained in terms of concentration, and we can see that the target of stabilized temperature is relatively well reached. And so within OptimiSM, there is also a full work package dedicated to the question of abrupt changes in the Earth system. And it's tackling the question of the existence of rapid transition within CMIP6 models. So this is mainly led by Sibron Dryfoot from KNMI. And so he has developed a kind of searching protocol using stringent classification criteria to be as objective as possible in their research of abrupt changes. And so this is a kind of an update of the PNACE paper published by Sibron in 2015, but for CMIP5, but here for CMIP6, and as I found once again a number of cases in a number of models where there is abrupt event or gradual changes, but concerning a kind of tipping element. So here are two examples of these abrupt changes in the Earth system, concerning here Arctic sea ice for the downward surface heat fluxes in GIS model, and here in the same variable, but for the Southern Ocean. So this is concerning quite a big area. This is part of the research criteria. And here is a kind of summary of what they found with a number of rapid transition found in CMIP6 models. So mainly in the polar region, so mainly related with sea ice, but also for dynamical variables like what's going on in the SPG or for the overturning. And so the next step is to explore a few more components and also explore the simulation when they will be all performed. And so this leads me to the other project that I would like to talk about, which is TPSM. So TPSM is also an EU project with similar partners, but not all of them are the same. It's a follow-up, let's say, or a companion project to OptimiSM. So with a bit more Earth system models, and once again, international collaboration, notably with NCAR in the US. So the main objective of TPSM is really to focus on just tipping point, not contrary to OptimiSM, who is also helping to develop models. So here we are really focusing on tipping points that are represented here nicely in biosphere, cryosphere, or ocean atmosphere circulation systems. So there is a number of systems that might be at risk. And so the primary objective of TPSM is to try to deliver a step change in our understanding of climate tipping points in the Earth system, including also their impact on ecosystems, on society, and also develop a set of early warning indicators, as well as safe emission pathways to minimize the risk of exceeding the risk of such tipping points. So the main novelty, let's say, is to use ESM to foster a more systematic assessment and investigation of the risk of and likelihood of tipping points, given that tipping points have been analyzed a lot of time using simple models, let's say. So here the idea is really to use state-of-the-art climate models to really to assess the risk and likelihood of tipping points. And in fact, the motivation is actually to try to to feed the IPCC assessment. And for instance, this paper has provided this IPCC view, I would say, of the risk of crossing tipping points, following kind of burning amber graphs, illustrations, and you have the different tipping element and the risk of crossing a key threshold. So we believe that this assessment might need further work using state-of-the-art climate system and Earth system models. And also try to develop reliable early warning signals, so not only based on a kind of theoretical approach, but also on a more process-based understanding and test them into models. So yeah, it's really focused on process understanding and also finding a rare event, if any, that can trigger a climate tipping point, and search for to what extent the occurrence of tipping events might depend on the rate, the magnitude, or the duration of global warming levels, and also to see if they are irreversible. So yeah, the idea is to be as systematic as possible, let's say, also through international collaboration, of course. Yeah, another motivation concerns the risk of so-called cascades of tipping elements, meaning that some tipping points can interact with each other and trigger other tipping elements. For instance, in this figure, the AMOC, which is very central, let's say, to this risk, since it can impact a number of other systems, but it's not the only one. Also assess the likelihood of the tipping elements, and for that we need coupled systems. So that's why the use of Earth system models is really necessary here to assess this risk of cascading impact. So once again, we will try to have a systematic investigation and focus on the mechanisms and consequences of potential tipping point and their interaction with the risk of cascades. Lastly, we would like to try to also focus on the impacts in terms of ecological and societal system, but also as represented in this nice figure from Maike, where the nation, the target from the UNU are represented as well, and so yeah, the idea of what are the impact of these potential tipping points, but also what threshold can be found in some key societal ecosystems, since both ecosystems can have their own dynamics, and the idea will be there then to find what are the climatic drivers and their threshold that might bring these tipping events in a few societal and ecological systems. And once again, looking at the impacts, and once again, trying to develop a set of safe emission pathway using the protocol that we discussed. So this is the kind of a concept of the whole project. So try to better understand the tipping points using ESM and impact models, looking into the consequences, develop synthesis using, for instance, risk register, emergent constraint, also observational constraint to improve our likelihood estimate, and then coming back to our models. So to finish, here are the few experiments that are planned within the project. So The TPSM core, let's say, in fact, is building on OptimiSM, in line also with TipMip. So this is this type of scenarios that are already presented. Then we are also thinking of TPSM ensemble, which is when we found tipping points within one of the models. And as Gökhan said, it's not necessarily the case, but if we found them, the idea is to perturb the initial state to better assess the likelihood and the risk of the tipping. There are also what is called TPSM domain, which are offline simulation, where we focus on one component. And the last type of experiment is also to force the tipping, if they do not occur, into the core. For instance, by putting fresh water into the MOC or modified vegetation within the Amazon, or to change the Antarctic. So that's also really in line with the other initiative, and the idea is really to work hand in hand to define together similar protocols, since we have a number of ideas, but we can still modify them since the project just started at the beginning of the year. So I will start there with a few conclusions. Thank you.
Are there any online? Is someone monitoring the online? Oh, thanks.
Hi, thanks for the great talk. You mentioned using a couple of different approaches for developing reliable early warning signals. And you said you were going to use some theoretical ones, and I'm curious for a bit more specifics on what kind of approaches you're thinking. Are you thinking things from like complex systems theory, like critical slowing down, or other approaches?
Thank you. So yeah, the idea is maybe to use this type of approaches, the existing approaches like critical slowdown, but really test them within models. It's not always done, in fact. For instance, we are just using this theory and apply them to data, to observation, and say we are close to a tipping point. But is this simple approach already true in models? It's not always the case. So first of all, to test them within the model world, at least it can show the false alarm signal. And then our approach is more process-based, let's say, and so we believe more into precursors of tipping points, and when we have understood the dynamics of given tipping points or tipping elements, the idea is to find the precursors in terms of mechanism. For instance, for the subpolar gyre, this can be the stratification, since it's very important for convection, and then the whole subpolar gyre dynamics. And we also have some ideas on developing some kind of space for time substitution. So looking at also patterns that might precede tipping points, looking into models, how it looks like, and then understand the dynamics also, and then apply them to observation.
Thank you.
Welcome.
Other questions? Hey, thank you, Didier. That was great. We'll have our final presentation here before discussion. And it's Peter Lawrence from NSF NCAR CGD talking about climate interventions with CESM.
Thanks, Benny. So this works. So, okay, just be patient. Okay, sorry. Okay, there we go. So yes, as Betty and Gökhan have said, like we're looking at climate interventions, but in the context of tipping points, as being a key motivation, and as Betty said, like we're involved with the what if MIP, but this is sort of like getting maybe a little bit more of the what do you do about trying to avoid some of those tipping points, and if the world does come to that point where we can't control climate change, So we have a project that we've set up here. It's a growing convergence research project with Arizona State University, Duke University, and Louisiana State University. And my co-authors, who are the principal investigators on this project, David Lawrence, Simona Tilmes, Andrea Smith, Monica Morrison, Michael Barton, Cheryl Harrison, and Tyler Felgenhauer. And the whole idea about this is, like, can we use CSM in the context of exploring climate interventions? By climate interventions, we're talking about both carbon dioxide removal, and that's through natural and also sort of industrial processes, and then also solar radiation modification. And just to get some little bit of sort of motivation, we're really like not on track to hit a 1.5 degree world as a maximum warming. And in fact, a lot of statements that have come out in the last couple of weeks have said within the decade, we will have a year where we're over 1.5 degrees of warming. So the question is, how do we go address this sort of challenge that we're facing? And we're looking at sort of large scale, sort of negative carbon withdrawals to try and get to 1.5 degrees. If you were to actually achieve some of these slopes, and we're not really on the task to do that. And one of the things that Will Stefan, who was actually part of the initial sort of setup of this project, was his real focus was the fact that, like, climate stability and thresholds are really important to try and address. If we look at the last sort of million years between glacial and interglacial cycles, which is that there's a stability sort of within the Earth system. And the big question, the big sort of challenge is, what happens if we hit some planetary threshold where we get into a different stability state in terms of we get into this hothouse Earth? And these are sort of like the tipping points we're really concerned with. Going beyond, so this is into Timberland again. Everyone's sort of been through this. I'm not going to go into too much detail, but the idea is that the cascades of tipping points, and then the carbon vulnerability associated with sort of like permafrost or loss of the Amazon, those sort of really sort of dire sort of outcomes. So on top of that, sort of the national academies and have been discussing looking at different ways of addressing climate intervention after you've pushed mitigation as far as you can. And so carbon dioxide removal in terms of natural systems, how do they pull carbon back out, is one component. But then we're also looking at sort of like global solar radiation modification. So this includes stratospheric aerosol injections and cloud modifications such as marine cloud brightening. We're also looking within our group at some way of understanding the impacts and suffering that would happen with climate change versus with impacts. So the idea is having a comparative risk analysis for those two. So I'm just going to quickly mention that, yes, we've got this growing convergence research grant from the National Science Foundation. It's over 5 years. We're the lead agency here at NCAR, but we have Arizona State, Duke University, and Louisiana State also are major contributors and partners on this. And beyond that, we have collaborators that we've sort of gotten from World Wildlife Fund, the Nature Conservancy, and we're looking at a whole group of researchers and climate groups. So the way that the project's set up is we have this core group of researchers that we're doing, which is sort of gone through, but we also have a community partner and advisory panel. And so the idea is we're building scenarios, we're going through and running them through CSM. We're building up a large data archive and a toolkit to go into that. From the toolkit, we can do impact assessment, assessments, sorry. And then the final element is trying to get tailored community partner comparative benefit and risk assessments. One other element that we do have, and this is Arizona State University is looking at a societal dynamics model, which will be coupled into CSM to be able to generate scenarios interactively. So what I want to do is sort of take it through and say, what are we trying to do with CSM? And so CSM, and we're using CSM 2.1.5 on derecho, which is the same as the Lens 2 experiment, but it's also the CMIP6 model. And what we're doing is we're using this in a fully interactive sense. In that way, we have emissions-driven simulation. So we have CO2 coming out. It's being fully simulated through the processes. We also have active fire and volatile organics or biogenic aerosols. And on top of that, we have a new ocean biogeochemistry that allows us to run the Feisty model and be able to do calcifying coccolithophores as one of the phytoplanktons within this. On top of this, we're doing 8 different climate interventions. So looking at from atmospheric solar radiation modification, land-based CDR, and ocean-based CDR. if we're going to build a model like this, we need to really test it and be able to evaluate what the impacts of running it fully coupled are, like having these elements. So here we were using the climate variability diagnostics package and comparing the model in it when you have prescribed CO2, prescribed aerosols over the historical period versus when we have this fully interactive model. And one of the things we see is that the model does perform in a very consistent manner, regardless of which configuration we're running. The other side of it is when we compare the model in its fully coupled configuration, we do really well against the global carbon project. In fact, we do a lot better than when we prescribe CO2 to the model. So having an active carbon cycle allows us to get a much better growth rate for CO2. So the red lines in each of these experiments are a fully coupled model compared to the black lines, which is the global carbon project. Or in the case of CO2, the CO2 tracer, that's the prescribed CMIP6. So what we can see is by adding a dynamic component to the carbon cycle, we actually improve our representation of the carbon cycle. For the land, it decreased some of quite a large amount of the excess carbon that was coming out of the land through land use and land cover change. But for the ocean, which is the bottom right panel here, we can see that it's actually almost completely spot on to the global carbon project, which was sort of an unexpected result. For me, it was anyway. Okay, I'm giving a talk tomorrow in the land biogeochemistry working group meeting, which I'll go into these experiments in a lot more detail, the components of those. This is more going to be about the climate intervention side of it. Okay, so these are the 8 climate intervention strategies that we have developed out, and we've got scenarios that go associated with them, which are being generated by consultation with like our community partners, but also Duke University, Tiger Felgenhauer is like an expert in scenario generation, especially in the realm of climate intervention. So we're building up this whole range of scenarios that will be applied against the baseline emission scenarios. Just want to get a little bit in how do we do some of these things. So when we do land cover change in the model, we can actually go through and prescribe the plant functional types as we're going through. So what we do is if we want to do reforestation or we want to do bioenergy with carbon capture and storage, we can change the plant functional types and the crop functional types as going through time. So we can actually reforest. And this is just an animation showing what a maximum afforestation would look like. We're working closely with Stephanie Rowe at the World Wildlife Fund. And we're also working with James King and other groups to make sure that these scenarios address conservation biology, they address needing to have agricultural areas maintained, urban areas, obviously. So the idea is to have projections and simulations that can push out the model's ability to draw carbon back down and then see a climate response, but also doing that in the context, the constraints of both conservation and societal needs. And so here we have just an idealized ramp up of afforestation, which is what you're seeing there in the maps going through time. We also have bioenergy crops added to CSM now, which is something that was being pushed through. We had a paper recently just came out in PNAS, and where we can have miscanthus and switchgrass as well as the normal crops that we have in our crop function in our crop model. In terms of looking at how do we do solar radiation modification, sorry, we're working off previous work that's happened here with the GLENS project, which is the global, the geoengineering large ensemble, but also mostly off what's called the ARISE simulations. So we're taking the output of these previously run models to get stratospheric aerosols, and we can then rerun our model with them without those stratospheric aerosols that have been added and their whole atmospheric chemistry prescribes. So here's just an example of what happens here is that the ARISE simulations were only run to 2070. And so what we're doing in this project is we're extending out those ARISE simulations. So we can see, and the reason why we're doing this is because WACM is very expensive. We couldn't do large ensembles of WACM simulations, but what we can do is we can take the forcings out of these previously run WACM experiments and see how an ensemble of CSM2 simulations with CAM6 would look. Okay. Finally, one of the nice things about the modeling framework with CSM is that we have all these embedded impacts. So we can do explicit crop modeling. We explicitly have fisheries being able to be modeled out of the new marble ocean biogeochemistry. We have an urban climate through our urban model. We have now wildfires and wildland and crop fires, but we now get emissions out of those as well. Not emissions, sorry. We get the aerosol emissions out of them now. We have water availability, irrigation demand, wood production, ecosystem health. So this is like a nice way to do impacts assessments. I didn't think I would be this quick, so I do have some extra slides. If I can just get to them. I really wanted to put up the core team. These are, really part of convergence research is building a team of people from different disciplines, different backgrounds, different institutions. And what's really exciting is we have built this team out of this group of researchers, which all have the same sort of focus of like, they're concerned about climate change, they're concerned about the interventions that are being discussed in both the public and I guess the research sphere. And this is sort of our stakeholder group. It's really nice to have people who've got buy-in and want to have the best available information when we're discussing both climate change and also climate interventions sort of discussions. And finally, I just want to say that this has been a process. It's not just like our small group of researchers. We've been holding workshops, and that's one of the most valuable elements, is just getting those workshops together. And yeah, I'll leave it there.
It and hold it.
Yes. You have to leave your finger on.
Push and hold the whole time. Okay. Make sure you don't hear me saying things when I'm not supposed to. So thanks, Peter. This is great for our session here. Questions for Peter?
Hi,
Hello.
Peter.
Oh, sorry. You first. I didn't realize you
No,
were.
go ahead. Go ahead.
Okay. Well, I have about a million questions, but I'll constrain myself to just one. This is a really, really interesting and ambitious project, and I can't wait to see what comes out of it. I think my first question has to do with, as you bring in all of these different methods, how do you deal with kind of the combinatorial aspect of this, where even if you drop Wacom and just do CAM, how are you dealing with bringing in these different methods together in different combinations of them, and even just the communication aspect of that, even if the modeling of it is possible?
Fabulous question. And it's actually part of the design of the project, is we're doing one-by-one interventions to start with. And I should probably have got into more of the design of it. So we have what are called a maximum feasible and then plausible scenarios. So we have two of those for each intervention. And so it's basically a sensitivity experiment to start with, to say, having the same framework, same emissions pathway, we apply just one climate intervention on either of those pathways. The second round, once we've done that and we've got an understanding of like the sensitivity of the model, is with our partner organizations start building a portfolio of multiple interventions. So where we have multiple interventions actually all occurring at the same time. So the interactions are really interesting, because if you were doing some form of soil radiation modification and doing reforestation at the same time, or bioenergy, or if you were doing something in terms of the marine CDR, those interactions will be really unknown at this point in time. That's the second phase of the experiments. The third phase is like getting really nuanced. So we get like one of our partner organizations say, we really are concerned about people talking about this. What would happen in the Earth system models if you did this? So yeah, but it's a great question. And so that is the iterative nature of this project. Is first time through is just sensitivity, see how the model responds. Yeah.
Cool. Thanks.
Peter. I think I understand your choice of CSM 2.1 as a modeling framework, but I'm wondering if you have considered, it looks like you're developing a lot of new interactions and new components or pieces of the model. And I'm wondering if you've considered a migration path to CSM 3.
So having Dave Lawrence as my boss is really good for that. He was actually excited for me to be doing this as a progression towards CSM 3. So how do we do emission-driven runs? And this is an area that hasn't really been fully fleshed out. for CSM3. You know, we don't even have the carbon cycle working yet in CSM3. So part of the reasons we need to do our research now, we can't wait until the model is developed and it's tested and it's finalized. So that's why we're using CSM2.1. The interactive fires and the interactive volatile organics is also another area that Dave's very excited to bring across to CSM3. So the whole idea is let's explore the system. And we saw benefits like with the carbon cycle that I frankly wasn't expecting. I thought we'd have a model that diverged from like the historical observed CO2 record. We wouldn't be able to reproduce the global carbon project. But what happens is when we have the fully coupled carbon cycle, it does a much better job than when we prescribe CO2 and those aerosol forcings. So having this exploration is really important for understanding our model and what we can use it for. So I didn't mention this, and I'll mention it tomorrow, is the fact that this configuration is being used for the HOPE ensemble, which is SSP 119. So it's like the idea is like, can we find what is the lowest pathway we can do in an interactive sense? And what's really nice about having interactive is when we plant a forest now, it'll draw the carbon out of the atmosphere and then the climate will respond. It's not something we have to back calculate later on, which is what most projects do when they're trying to assess a climate intervention. And we can also see the carbon cycle response to doing like some of the solar radiation modification. But yes, you're exactly right. Pathway to CSM3, absolutely. And it's all in GitHub, so it's all mergeable. Yeah, and the development stuff we're doing is like we're trying to use existing parts of the model, but parameterize them and be able to use forcing files. So minimize the development effort. Thanks, Jim.
I'll put Nikki on the spot here since she's here. Do you want to say a few words on the HOPE?
Always good to be called out while you're checking your email on your phone. So last year at this meeting, I proposed to the Scientific Steering Committee of CESM that we consider doing a large ensemble simulation with what was called a highly optimistic projection ensemble, or HOPE for short. So we've done a lot of ensembles using sort of middle of the road or high end estimates of what our emissions might be. And we'd like to see what might happen to the Earth system under something like an SSP 119, but we'd like those simulations to be emissions driven, not with atmospheric CO2 prescribed. But there are a lot of, I think, really interesting questions that other people in the community, besides the carbon cycle scientists like myself, might want to explore once this is off and running. For example, does internal variability change remarkably when we, for example, look at a negative emission simulation, right? So there's a lot of different interesting scientific questions that I think we can explore when this project is off and running. But the first step, I think, is getting emissions-driven simulations on the docket. So
thank you. And you can continue with your emails, I guess.
Yeah. Okay, so now we're to the discussion, and possibly could our great IT people put my presentation back up, because I have a slide that was an extra. I guess I could have shown it, that might help with this discussion. But what you've heard here today is, there's a lot of opportunities to partner, to take advantages of the synergies of many of these projects going on, and take advantage of the expertise, not just of the modeling community. And I'll get to it if I go fast enough. And Sinya hasn't seen this slide, but that's okay. I'll get to it. There it is. Oops. Can you put it, what did I, oh, I can go back. Okay, so I took the TIPMIP kind of scenarios here. It includes the domains that Senior already showed. You see a lot of these kind of make it happen, like NA hose MIP. There's also CLIM TIP. And I added what if MIP there at the bottom. So it goes across the different domains. An important thing to notice here is especially with TIPMIP, taking advantage of people that look at risk assessment and methods and such. So not just the climate or the Earth system, but the risk going forward. And just so thinking of just next steps, just the IPCC in their 60th session that they held in Turkey They identified high-impact climate outcomes and abrupt changes, including tipping points, compounding, and cascading events. They put this under Working Group 1, but of course, Working Group 2 and 3 in terms of vulnerability, adaptation, mitigation are also interested in kind of these high-impact climate outcomes. There's already been a call for nominations for experts to draft the outline. Hopefully some of you were nominated, but we'd like to hear from the rest of you kind of steps. Where should we be going? What should we be doing? What are your interests? Are there things that are missing from these projects that you really think should have been included? Because many of these are still in kind of the design stage, the draft. They're not final.
And when I was going through the efforts within the United States related to tipping elements and tipping points, there are really no coordinated efforts, if any. And it feels like European side, as you can see from at least there are 3 ongoing projects, ClimTip, TPSM, and Optimism. But there were previous projects also that ended. So there is actually quite a bit of attention to these tipping elements. And what Peter showed, it's essentially getting there. And I also chatted with Ruby from the DOE side. There is really, as far as we can tell, there are no coordinated efforts or sort of specific projects focusing on tipping points or tipping elements. There are perhaps some funded projects looking at sudden changes in AMOC or that sort of thing, but they seem to be quite isolated. So that's sort of another piece of background for this thing.
So yeah, if I could just come at that then from a European perspective. So I think where all these projects within that you've heard about today, Optimism, ClimTip, TPSM, where they've all been successful is through the coordination cross-project. So in terms of, if it was a recommendation for a US coordinated activity, that would be, one key bit of advice is in terms of, coordinating across projects in so much as you can in terms of minimizing the replication. So all these experimental designs are really replicated. So we're not reinventing the wheel in each of these projects. So we can utilize the same experiment structure, expand ensembles. And so I think that's really important. And that was like one question I had between, I guess, TipMIP and what if MIP is that, are you planning to use pick off in terms of where you prescribe your tipping element? Are you planning on basically building that on top of the same experiments that have been run within TipMIP? Because that would seem sensible and allow larger ensembles. Because I'm assuming, and there hasn't been much talk about ensemble size in this space, but I'm assuming we kind of need decent sized ensembles here as well. So just some thoughts.
Okay, yeah, I can answer this in a little bit, and if Sina has more, very definitely we want to build off of each other, which is why we have adopted the same protocols. We discussed Flat 10, we discussed the Optimism, and decided to go with the Optimism and its emphasis on temperature levels. The Flat 10 are still very important for carbon. So we've designed it specifically that way so that we may design other experiments. For example, what if MIP may branch at year 50 or whatever we determine looking at the models, and TipMIP may decide they haven't reached a tipping point at maybe 4 degrees C, but they may branch off it and do some offline models. And I think Sinya can comment on that. The other important thing I think that you kind of saw when you saw the Optimism is there are modeling groups that have been doing with their CMIP 6 models. There's Terra Firma project in the UK, and the, I guess it was the French model, where they've actually tried out some of these experiments to see if they would even work if you branch off this 0.2 degrees. So I think we have some excellent indication. And so in terms of that, in terms of your question on ensembles, we have considered that. For now, at least in What If MIP, we're initially proposing a multi-model ensemble, but if groups can run an ensemble with, I think that would be great to look at the uncertainty even greater within the models. So, Sinya, do you want to comment?
Just to co-sign basically what Betty has just said. Yeah, it's a great question, and I think it's worth to align all these different efforts because we all want to understand our models better, to understand our planet better, and it's good to not duplicate things and have a European version of tipping points MIPS and an American version, but maybe like bridge and make most use of our joint computing time. And so yeah, Betty, like you said, I haven't seen this version before, but I like it very much. I think it reflects very well our discussions that we had also in the past year, also with like the what if branching of the tip map branches that we would hope to get yeah, like the first runs done by this year. So this aligns quite well. And yeah, just to add that maybe this workshop or this general assembly that we planned for December and back to back with AGU is a very good opportunity to bring all the Europeans over, not all, but many of the modeling centers over to the East Coast and meet you guys there and then take this further. And what I forgot to say earlier was that we have also registered TipMap as a community CMAP. So all this is open, yeah, an open initiative. And like Betty said, not closed and not finalized, and it's all still shapeable. Thank you.
Discussion point was that if you look at what if MIP and tip MIP, this is like acronym soup. If you're hungry, just go to this, whatever, come to this meeting and then you'll be full with acronyms. The baseline global warming level, that's GWL level, is 0. That's the pre-industrial control simulation. And these MIPs, both what if MIP and tip MIP, are trying to serve, in a sense, or provide information for IPCC. So my sort of question was, who cares? In the sense that these are baseline simulations coming from pre-industrial cases, and then the global warming levels are off of that. In other words, they do not include a time-varying anthropogenic forcing component. And I do not know how that is going to impact the outcome of these simulations. So that was one concern. The second concern was essentially, well, how do you get to tipping points just by, you can't just do that essentially. And then the third concern that I had was, how do you define reversibility? Because single metric is not necessarily a unique metric. I mean, we talked about pattern effect yesterday. Maria, in her presentation, talked about importance of pattern effect and all that. So how do we essentially judge reversibility? So I believe Colin is looking at some of these aspects because UK Met Office has some of these simulations already. And I think he was going to add the sort of present day control or historical and then get a preliminary sense of those. So possibly some of these protocols can be still modified based on the outcome of what Colin and his colleagues actually find based on some of these comments. But anyway, these are sort of, I mean, I think both MIPs recognize sort of the challenges, and they are both stressing that these are in a sense idealized sort of experiments.
Yeah, I can just add to that. They're kind of what we've done for a long time, we'll do in the IPCCs or the CMIP still is the 1% CO2 idealized experiments, which started from pre-industrial. They also take advantage of the deck for the CMIP-7, which has an emission-driven for the pre-industrial. So they are idealized in that way, and they take advantage of experiments that are already being proposed for the IPCC. But it is an interesting question to think about, you know, other levels of starting from, I guess, and tipping points in terms of IPCC.
There are some also early results. Again, Colin and UK Met Office is quite ahead in some of these simulations. As you go to higher warming levels, there seems to be a nonlinearity appearing, particularly around 4 degrees Celsius and above. And that results in overshoots. And then there's some kind of oscillatory behavior and then tries to come back, but it's not necessarily leveling within the first 100 years or 200 years. So those are other challenges that we need to keep in mind. I guess broadly, is there interest within the community, within this, when I say community, this is the community sort of CESM, for us to pursue TIP-MIP and what-if MIP? And if there would this be useful for the community? I mean, you have seen where things are. And as Betty said, if you think that certain design elements are not sort of addressing some of the questions, so this might be, is it too late already, or there's still open room, I guess, right?
Senior can comment on TIP-MIP. There have been discussions, but of course it takes people to lead. So for example, within what-if MIP, you'll see some common names here for ice sheets, Alex Robinson, Robin Smith, that are involved in both projects. But there have also been discussions of tipping of corals or other, you know, and so are there people that are really interested in that and have the expertise and wanted to develop additional experiments? I should say all these experiments, in particular, what-if MIP, it's a menu of experiments. Not every group has to do all experiments, but the hope is that enough models, and by making this synergy across these different collaborations, that we will have enough models that can do it, and that either they have the interactive component like the Greenland ice sheet or vegetation that they'll run a long TIP-MIP experiment, or they are willing to prescribe it in their experiment. I know there's a lot of interest from CMIP, talking to Helene in that in terms of kind of the impacts and the vulnerability related to it. So we're open to more experiments, but we really need people to sign on, even for the ones we're doing. We still need to get more expertise, expert judgment to make sure our experiments are the best and the most useful.
I was going to say, but you have to agree on that AMOC is the greatest impact. That's the entry card.
And just to comment, and maybe there's people in the room that are more knowledgeable and engaged in this than I am, but I'm reviewing a report right now for the National Academies. There was a workshop on tipping points and cascading impacts and things like that, that the National Science Foundation supported as part of the Next Generation Earth System Science NSF report that came out a few years ago. And what that usually indicates to me, and I don't know if someone from NSF is in the room or on the call, but you know,
Eric just walked in. Yeah.
Okay. So Eric may know about this, but I mean, you know, often after these kinds of workshops that again, NSF sponsored at the academies, there can be like dear colleague letters and whatnot. So there's clearly an interest, at least from NSF, in this topic. And I just don't know if that leads to any pathways for the kind of things you're talking about, more US engagement, or if there's people in this room that are like, I'm interested in this, but I don't have the funding. You know, there could be those opportunities coming. So it's just kind of a comment.
Thank you, Jim. the reason I brought this up is essentially, both Betty and I think, I don't want to speak for Betty, but we feel like the European side and these efforts are well funded through several projects. And there is some maybe seed or some funding that Peter talked about, but a coordinated effort in terms of funding would go a long ways from the US side.
So for the see what happens experiments, I keep thinking back to a quote from Donald Rumsfeld from many years ago about the unknown unknowns. You know, is there a clear definition of when a model has reached a tipping point?
Good question. Do you want to answer that, Sinya, or are you still there?
I can make an attempt. So this is why we also have this methods and risk assessment group, because we have all the different people working on different ways of evaluating these systematic, these MIPS. So with respect to tipping points. So for example, the work by Sibrin that was presented earlier, I think by Didier, and we are also working on similar methods. So this is also something that we, not a MIP, not yet another MIP on methods, but maybe something similar to have something across the different initiatives that agrees on how to evaluate this and define on what constitutes a tipping in these runs. And all this again is open. Please sign up for the email lists, and then you're part of the loop.
And then the other question was, you know, how do you determine what the mechanism for a tipping point is? It's very possible that it could be a combination of methods that we've considered, or even something that we have not at all considered yet.
Yes, that's the case. Yeah, I mean, Laura was trying to sort of answer that question in a sense. We had 8 different models, and then 4 of them were different than the other 4. And the mechanisms is, I mean, for some of them, it's difficult to pinpoint. Yep.
I wrote down from the workshop that TipMIP had 2 definitions. I mean, there are many different definitions of it, and they've changed with time. So tipping point was a critical threshold beyond which the system reorganizes, often abruptly and or irreversibly. And for irreversibility, I kind of like this definition because we've struggled with it for a long time. A perturbed state is defined as irreversible on a given time scale if a recovery due to natural process takes substantially longer than time scale of interest. So we used to talk about the time scale of the forcing, but what we're really concerned about is our planet over the next decades and the next century. So some things may be reversible on millions of time scales, but that's not really probably at least my concern. I like that definition for that reason.
We'll be dead by then.
So yeah, am I right in you saying that most of these experiments are based on 1850 kind of control configurations?
Yes, the control is 1850.
I think I kind of share your negativity about that, based on the fact, you know, we're nearly 200 years into some changing attractor of the climate, for example, and having perturbations to that in the future versus 1850 seems somewhat less academic and more like relevant, I think, in terms of determining tipping points.
I mean, yeah, that was sort of my concern too. It is, I felt like there is, what is the right word, push and pull, being relevant for IPCC, but also keep everything simple so that people can run and idealize in an idealized way. I can see the point of 1850 being simpler, but then when you participate or provide information to IPCC, then the relevance becomes an issue. Yeah.
I can follow on from that. So we have thought about that in terms of, yeah, and we, in terms of that, yes, these are highly idealized 1850 based simulations. What we haven't quite managed to figure out is how best to deal with particularly the aerosol emission scenario. So how do you define it? Do you do a transient, or do you pick a kind of present day state? So I think, yeah, there's definitely some more work to do to do there. I think kind of ties a little bit, Airchem MIP has picked up on this a little bit as well from a forcing perspective. And so there's likely to be some changes in Airchem MIP 2 in that, in terms of, so all the forcings are defined relative to PI, and increasingly it's recognized that with future forcing, PI isn't the most realistic base state. So maybe there's something we can learn from what they decide to do in Airchem MIP as well, as what I'm kind of thinking, that we should kind of maybe apply something similar to kind of the tip MIP type of experiments. Might be an idea anyway, just a thought.
Okay, well, we passed our time. Let's thank all of our speakers one more time. And thank you for joining us. I mean, I wasn't expecting this crowd, so this is really great. So there's good.
All right, I think we'll get started. Welcome, everyone. This is the Earth System Prediction Working Group session. I'm your co-chair, Steve Yeager, and Kathy Pejan is here as well. So a quick reminder about the code of conduct. I'm sure you've all seen this, but just remember to be considerate during the session. Here's our agenda. We've had a slight change. Judith Berner is not able to give her talk. That was going to be the first talk of the session. So we can switch things around. I thought I would give the co-chairs update right up front, and then we can maybe continue it after the last talk of the morning session and follow that up with discussion. So we'll have 3 science talks here in the morning, and then another 5 in the afternoon. So I'll just launch right into an update from the co-chairs. I always like to start with an overview of legacy data sets. I know many of you have seen this, but there may be new people in the crowd who aren't aware of all the resources that the working group has available. You can go to this working group webpage to find links to these data sets, and they include CESM1 subseasonal, seasonal, and decadal hindcasts, including our decadal prediction large ensemble, which use CESM1. And then also some CESM2 hindcast data sets, including a full suite of subseasonal to seasonal reforecast sets that use both CAM6 and high-top WACM6, and that have a corresponding reference there in Richter et al. 2022. And then many of you have already heard about the seasonal to multi-year large ensemble SMILE data set that use CESM2. These are 24-month hindcasts that span this period from 1970 to 2019 with a 2022 paper for reference. This is sort of what we've been up to in the last year or so. So new data sets being produced that will be coming soon and will be available. First is the CSM2 S2S reforecast set that isolated different sources of predictability. So using climatological initial conditions in the atmosphere, land, and ocean, and then different combinations thereof. And this was published last year, or this year, actually, Richter et al. 2024, quantifying sources of subseasonal prediction skill in CESM2. These are not yet available from the web page, but we're working on that. And I think if you would like to look at these, we can certainly facilitate access. And then we've recently run an extension through summer of 2022. We've been working on Clivar tropical basin interaction experiments. So these are building off of the SMILE foundation. And these are coordinated hindcast pacemaker experiments in which we restore in the tropics of the Atlantic, Pacific, and Indian sectors for the February initialized hindcast. So we're looking at, how nudging to realistic conditions in different basins can impact global skill. These are 10-member ensembles. I think they go from about 1975 to present. I should have written that down. These will be coming soon, so we're trying to contribute these as part of a this international CLIVAR effort and get a paper out, and then those should be coming public. We've been putting a lot of work lately into the SMILE real-time extension. We call it SMILE XT. These are hindcasts from 2020 through 2023 for each of the months of initialization using a 20-member ensemble. Of course, we used this to produce the El Nino forecast for the 2023-24 event last year, but we've recently had to rerun them, and I'll talk about that because we found some issues with the land initial conditions. And then another SMILE extension is the backward extension. So we've filled in 1958 through 1969 initializations only for November, again with a 20-member ensemble, and then we can talk about whether there would be value in backward extension of other start months. We've also run a new decadal prediction hindcast set using CESM2. So this is extending SMILE November out through decadal lead times. So these are 122-month hindcasts initialized in November, spanning this full time period from 1958 to 2023 with a 20-member ensemble. So this is kind of the next generation building off of the CESM1 DPLE. Again, has full biogeochemistry in it. So that data set is currently, I would say, in the quality control phase. We're trying to make sure that we did everything correctly before releasing that. And then related to that, we are participating in an international effort to look at multi-decadal predictions. So we've got the CESM2 MDP hindcast set that are looking 20 years into the future, initialized every 5 years then from 1960 through 2023 with a 10-member ensemble. And then finally, most recently, we've been exploring S2S hindcasts with CESM2 using DART initialization in the atmosphere and land, and I'll show some preliminary results from that. So the S2S hindcast suite is generally 11-member, 45-day ensembles initialized weekly. And so we've done those initialization perturbation experiments from 2011 through 2020. All right, I just wanted to give you a flavor of what some of these new data sets look like, or what's coming out of them. So in the winter meeting, I showed off the Atlantic SMILE pacemaker experiment. Here's a view of what the Indian pacemaker looks like. So what you can see here, hopefully, is the SMILE control initialized in February. I've subsampled it to look at 10-member hindcast skill as a function of forecast season here going down. So you can see skill for surface air temperature decreasing with lead time. And then the column here is when we apply anomaly restoring in the Indian sector to SST. So we're basically pinning the Indian sector to have realistic interannual variability. So you can see that the ACC is staying quite high there. And then the question is, what does that do to global skill? So we can look at the difference between the Indian pacemaker experiment and the SMILE original. So it doesn't have much benefit here in the first forecast season, but as you go further into the future, of course, you're enhancing your Indian Ocean skill by design. What's interesting is that we see a degradation of El Nino skill. So in this first DJF, after you initialize in February, having better skill in the Indian Ocean does not translate into better El Nino skill. So this is an interesting thing to dig into. We might have expected it to be better. Mentioned the CSM2 S2S hindcasts with DART initialization. This is work that Sasha Glanville and Kevin Rader have been spearheading. So here we're looking at the skill of sort of the standard 22-year CSM2 S2S hindcast set for DJF 2-meter air temperature, weeks 1, 2, 3, 4, 5, 6. When we look at the 10-year skill, it's quite similar to the 22-year skill. We only have 10 years of this DART reanalysis that we can use for initialization from 2011 through 2020. So this is when we initialize with a DART atmosphere. This is replacing the NCEP reanalysis atmosphere with sort of a atmospheric analysis product that's native to the CESM model. And then when you look at the skill difference, it's quite minor. So we're not getting much improved skill by initializing from a data assimilation that is sort of native to our model. However, when we combine the DART atmosphere with the DART land, so now we are replacing our land initial condition that came from an NCEP forced simulation of CLM with the state reconstruction from DART. Now we're starting to see some impressive skill improvements over South America and Africa in weeks 3, 4, and 5, 6 that look promising. And I think, maybe merit a more comprehensive experiment of doing maybe a backward extension of the DART analysis that allowed us to perform this experiment. Currently only going back to 2011, but it sure would be nice to be able to go back to 2000 and really do a full S2S side-by-side comparison. All right, some preliminary results from this CSM2 decadal prediction set. Kathy, let me know if I'm encroaching on the next speaker's time. So what we have here is our new decadal prediction set using CSM2. It's a 20-member ensemble, comparing it to the CSM1 decadal prediction large ensemble that had 40 members. And I'm showing you here skill for forecast year 1 through 5 global precipitation. So this is annual mean precipitation. And there are some really promising global improvements in this field. Particularly noteworthy are these improvements over subpolar North Atlantic, and as you can see here in West Africa and sort of Indian Ocean region, with corresponding improvements in the mean square skill score. So we're getting, better amplitude of anomalies as well as better correlation. Right now, as I said, we're still kind of doing quality control. We need to reorganize the data. It's in a bit of a state of mess. It's hard to analyze, certainly not in shape to put out yet to the working group, but that will be coming soon. I just wanted to focus in on this Africa precipitation result because this is interesting. So I'm showing you here again this comparison of our CSM2 skill, DPLE, and then the difference focused on the Africa region, forecast year 1 through 5 and 6 through 10. So we have high skill in the African Sahel in both systems that extends out to these long lead times, but we're seeing this really persistent and robust improvement in West Africa that I think is an exciting development that we'd like to know where this is coming from. And then this is the skill improvement for surface air temperature. So these again are global maps. It's a function of forecast lead time, 1 through 5, 3 through 7, 6 through 10. And the difference in skill that we're seeing in the CSM2 system is quite interesting in light of the improvements that we've seen in high resolution decadal prediction, where we see this improvement in the Eastern Tropical Pacific, as well as the Southern Ocean. We're seeing those improvements in the CSM2 system at low resolution, but it goes away. It's only there at early lead time, suggesting that This may come from some improvement in the initialization in the CESM2 system. All right, so we threw together this CESM2 DP system, didn't throw it together, but we're under tight deadlines to try to get our decadal forecast submitted to the WMO, Lead Center for Annual to Decadal Climate Update. That was a deadline in February. So we submitted this decadal forecast initialized in November 1st of 2023. This is what our forecast of the future looks like. This is years 2 through 10. So this would correspond to 2025 through 2033, I guess, for surface air temperature, precipitation, and AMOC, predicting quite a substantial decline in AMOC in the next decade. So this system will be included then in the 2024 edition of the WMO climate update that's currently in preparation. We managed to get that submitted, and then Leon Hermanson at UK Met Office produced his multi-model plots, and lo and behold, when we compare our system forecast year 1 surface air temperature to all the other contributions, you can see that we're a bit of an outlier over Antarctica. And so, when we saw this, we had to go back and figure out why it is that we have such a cold prediction over Antarctica for 2024. And so this brings me to land initialization issues that I want to discuss, but if it's time to move to the next speaker, I can postpone this discussion until, again, it's 20 after, so we're ready for Xingying. We have our online speaker ready to go. All right, I'll come back to the land initialization after we go through the round of morning speakers. So our next speaker is, you lost the agenda. Can you tell us your name and where you're from, please? Sorry about that.
Oh, yeah, sure, no problem. Hi, my name is Xin. I'm from CGBM session. Yeah. Okay. I guess
Yep,
I will
you can
just go
start.
ahead with.
Yeah, go ahead. You're ready.
Okay, good. Okay. Hi again, everyone. Good morning. Thank you for host. And in this presentation, I will talk about the CSM2 model with story resolving capability to understand the heavy precipitation mainly induced by AIs over the West US. First, I do just to show this formation of the AIs over in general. So talking about the AIs over the West US, it is a typical AI event looks like. Here's how a typical AI events look like for observations. So that image is from a satellite cloud data. It shows this AI storm stretching from Hawaii to California, bringing this heavy flooding impact during February 2017. And on the right side, it's just these events in the eye-wide perspective. So it's important to understand the moisture flux pattern associated with these events. And also these events are very important along the US West Coast. So in this work, and the overall background and methods are summarized here. So the context is that coast resolution climate models, due to their limited spatial resolution and the hydrostatic dynamical, they are mainly capable of capturing this linking these large-scale processes to these very fine-scale climate features, essentially over very complex terrains. But in order to just understand the impact of the extreme precipitation events associated with these AIs, And to tackle this challenge, in this study, we used the non-hydrostatic model for prediction across scales, that's called MPath dynamical, into the CSM2 to simulate 5 winter season simulation of a covering West US. And we want to understand this AI-driven heavy precipitation with a regional refined configuration down to 3 kilometers. As you can see, this model mesh configuration on the top left, so it transitioning from 60 kilometers all the way to 3 kilometers. And this 3 kilometer domain covers not only the West US region, but also this nearby portion of the East Pacific Ocean area. And given this 5 seasonal simulations across scales, our goal is to understand how the large-scale moisture flux transport pattern behave in model, and how they compare to the analysis design, and also what is the fan scale features for wind dynamics and precipitation, rain versus snow. And before I head into the results, I want to introduce a little bit more about this story resolving capability in CSM2 model. So in recent years, a non-hydrostatic dynamic code called MPath has been incorporated to CSM and especially and the CAM6. The MPath refers to this model for prediction across scales, and this dynamic code solve this fully compressible non-hydrostatic equation motion, and it allows both the uniform and the variable resolution configurations. As you notice, it will be the variable resolution configuration I used for the studies, so that's 60 and the 3 kilometers mission. And the left figure here shows an example of how this refined grid mesh looks like over the North American. And overall, this new generation global resolving model allows for store resolve scales on the order of few kilometers. And here's the animation that actually shows part of the simulations we did for this 63 experiment. So overall, we applied non-hydrostatic MPath dynamic code into CSM, and we are able to simulate AI events across scales with this regional refined configuration of the West US. This first part of this animation shows this global view of the large-scale moisture flux transport pattern. And we then further zoom into this refined domain over the West US. There's all the way to 3 kilometers for this for the AI-driven precipitation. As you can see from this visualization, it shows the tracks of these AIs in terms of the integrated moisture flux transport pattern, and also the cumulative landfalling precipitation over the coast regions. And this is just like a subset of our simulations. And these refined grids can capture the terrain details and also the fan scale details of the precipitation over this heavily impacted region. I will let the animation clearly a bit. So as you can see, this heavily accumulated precipitation. And followed by that, we also look at the rain versus snow accumulation, again overlaid with this water vapor transport pattern over at this defined region. As the visualization gradually shown, the model actually can simulate to significantly enhance the snowpack distribution over this much better resolved compressed rains, and also the cumulated intense rainfall over the mountainous ranges and the downstream communities. It has a direct influence on the flood risk. And this simulation and the result shows the potential for us to study extreme storms and also its hydrologic impacts using this new boundary framework. So overall, we codified the visualization of the multiple scale across extremes under a high resolution integrated modeling framework using CSM paths. And next, I will head into the detailed result from the simulations. Let's first look at the heavy precipitation. And when I say heavy precipitation, I feel the precipitation about 75% higher based on all the daily results. And I separate the result over Northwest region and combining Washington State and Oregon State, and also the Southwest region has for the California region, because these two regions are actually related to different atmospheric features. And the compared results from KMM pass at 3 kilometer to the graded observation from PRISM at 4 kilometer, average over these 5 simulated wet seasons. As you can see from this spatial plot, the precipitation features are overall reasonably captured over these compressed streams, including the coastal and mountainous regions. And also the spatial features are much better improved at 3 kilometer compared to the coast resolution at 6 kilometer, which is not shown here. And then we then examine the mean integrated water vapor transport pattern, that is IVT, and this is a composite plot based on all the heavy precipitation days, again over both Northwest and California regions. And we compare the simulations upward to the reference data set from Matter 2. And this overall IVT spatial pattern are reasonably captured in campus. You can see these very distinct trajectories when landfalling over Southwest versus Northwest regions. And also as expected, the Northwest coast region receives more intensified moisture fast transport than the Southwest coast area. And let's look at the integrated water vapor, that's IWV itself. Look at this variable because I want to look at the thermodynamics component of the IVT. And of course, the IWV is not actually fully dependent of dynamics. I want to acknowledge that. And similarly, this is for the result over the heavy precipitation days. And overall, the composite spatial pattern for the moisture distribution shows that some expected transient feature from the subtropical ocean to the mid-latitude coast for both of these Southwest and the Northwest events. And then, in addition to the thermodynamics component, we look at the wind dynamics, in terms of both zonal and meridional winds. Here shows the cross-section profile for the zonal winds. And the top row is for the Northwest region and NW region. And the bottom row is for the California region. And we compare the campus estimation to Matter 2 analysis. So for the zonal winds, and we found that the model can capture the wind profile features over the West Coast region. And over both regions, the overall wind profile and the cross-section structure are well captured by the output. But we do notice some overestimation for the magnitude over the Northwest region for the wind, for the zonal wind, which is about 15% compared to Matter 2 reanalysis. And it could hint that the model has some systematic balance for zonal wind speed. And for the California region, the jet stream location and the magnitude wind statistics are overall close to the reanalysis data set. Next is for this meridional wind. As we know, like the zonal wind is dominant and the meridional winds are secondary, but it still plays a significant flow in these near coastal track directions, essentially for the air landfall impingement angle. Not that good as zonal wind. For the more redundant wind, the model did show some notable bands, especially over this California region. So for the California region, for the simulated wind, the direction for the simulated wind tend to be southward with higher intensity. But for the magnitude analysis, it shows both southward and northward direction. And over the northwest region, the balance is the magnitude is smaller compared to analysis. So this could imply that the overall capture of the IVT of California actually could involve both the overestimation of this moisture distribution and also balance of the wind dynamics. In addition to the wind dynamics, we also look at the space humidity profile. And this is this humidity profile is generally well present in the model. And like we expect, it's just this concentrated distribution of moisture compared to analysis. And we and expected like with the moisture is dominated by the low levels. In addition to the moisture flux transport pattern and wind dynamics and humidity profile, we also look at this mesoscale wind dynamics that's over this both near coast regions and the land regions. Since we know that the heavy AI events, they are not only induced heavy intense precipitation, but also bring powerful winds. And the much better improved mesoscale processes will be very critical for extreme precipitation and other meteorological features during AIs. And this figure shows the wind speed at 850 hectopascal, again based on the extreme precipitation days. And we still compare the CAMPA estimation output to the magnitude analysis data here. And it shows us the impinging airflow relative to the terrain barrier. And it from the CAMPA's estimation, you can tell, also actually from the magnitude, you can tell these strong low-level winds and convective instability that connects to the storm's landfall streams. And we do notice that these very notable differences for the inland wind dynamics between the CAMPA's S2 versus magnitude analysis set, which does highlight the critical role of high resolution in simulating this orographic phase forcing, and which directly links to the formation of extreme precipitation events. So I'm kind of over my time. This is my last slide. So we look at the rain versus snow accumulation over this refinery region, and I also show this in the animation, but this is more detailed spatial plot that shows a much better improved precision of spatial temporal rainfall and snowfall pattern of complex streams. And so it actually, these results are very critical in predicting the air-related hydroclimate impacts, because it actually can tell us how much precipitation the storm brings and how much rain and snow falls. Also, that how much water flows over the mountain surface and what that means for these hydrological impacts. And this is the summary slide. I was just like, I want to do this too, but yeah, if I have any questions, feel free to reach out to me. Thank you for your attention.
I think we could take a question. Looks like there are none, so we'll move on to our next. Oh, wait, here's one.
I was just curious if you were able to test any other regions of refinement, if you played around with different, maybe only refining over the land, if that made a huge difference, or if you were able to.
You mean refine over other regions for?
Just playing around with the extent of refinement. I saw that you kind of included part of the Eastern Pacific in your refinement region.
Yeah. So we actually include the Pacific Ocean part because we also want to actually like to see and to capture some fine scale features for the moisture flux pattern. But you definitely want to get the land portion over this refined region. I will say it probably doesn't matter that much if you shrink the refined domain over the ocean. So you can like still cover small portion of the ocean, but you want to cover the study region, like the land part at the street at your refinement for your refinement. Yeah.
Thanks.
Thanks for the question.
Okay, thanks. We'll move on to the next speaker, who is Ankur Srivastava.
Yeah, can you hear me now?
Yes, we can.
Okay. You should be able to see my slides and should be in full screen now.
It's good.
All right. Good morning, everybody. I am Ankur Srivastava from the Indian Institute of Tropical Meteorology, which is in Pune, located along the western coast of India, which you can see here. So just to give you a perspective from where I am, I will be talking today about the interaction of the freshwater from rivers with the upper ocean, climate modeling perspective towards better subseasonal to seasonal forecasts. So the inspiration for this work was from the Bay of Bengal monsoon experiment, which was carried out in sometime in 1999 during the summer monsoon season, which is during June, July, August, September over India. So what they did in this experiment was they collected some in situ observations from a ship at this location in the Bay of Bengal. So what they noticed was within a span of few days, within a span of about 6 to 7 days, there was a arrival of freshwater plume at this location in the Bay of Bengal, and the sea surface salinity fell by about 4 PSU within a short span of time. And what it caused later on was the shoaling of the mixed layer depth. So the mixed layer depth decreased from a depth of about 30 meters to 10 meters, and the mixed layer temperature remained in the range of about 0.5 degrees Celsius. So what you would expect from a shallow mixed layer is enhanced warming of the mixed layer. So mind you, the local rainfall could not explain the observed freshening in the sea surface salinity, and there are other studies which have shown that the sea surface salinity variations in the northern Bay of Bengal varies coherently with rainfall over the Indian landmass, specifically the Ganga-Brahmaputra catchment area on the intra-season timescales with a lag of about 60 days. So for those of you who might not be knowing, so the monsoon low pressure systems contribute a lot to the rainfall that occurs over India during the Indian summer monsoon season. So plot here on the left shows the black dots here shows the genesis of these systems, and the lines show the propagation of these systems along the Indian landmass. So along their track, they bring quite a lot of rainfall over the Indian landmass. And the shading here shows the sea surface salinity. And you can see that the upper ocean is quite fresh in the northern Bay of Bengal. So the enormous freshwater discharge from the Ganga Brahmaputra basin, which is somewhere here, makes the northern Bay of Bengal one of the freshest regions in the tropical basins, and the Bay of Bengal plays an important role in determining the monsoon precipitation by facilitating the genesis of monsoon low pressure systems in the northern Bay of Bengal, and they also control the air-sea interactions associated with monsoon intra-seasonal oscillations, which are nothing but northward propagating cloud bands from equatorial location to the Indian landmass. So this study was basically carried out with the climate forecast system version 2, which we have adopted in India for subseasonal to seasonal forecast. And of course, we have done a lot of physics modifications to this model. So what we realized in the CFS was that so the plot here shows the same tracks of low pressure systems. And if you look at the clustering of these systems by the intra-seasonal oscillations during the active phase, when there is a lot of rainfall over Indian landmass, you find a lot of systems generating in the northern Bay of Bengal and propagating northwestwards. But during the break phase, when there is suppressed rainfall activity over Indian landmass, you don't find a lot of these systems generating here. So the problem with CFS, and this problem is common across other models as well, is that the synoptic variability is underestimated. There are too few systems that form over the oceanic region, and the propagation of these systems in land is restricted. Along with this, the plot here on the right shows the 10 to 90 day filtered rainfall anomalies. The shading are the rainfall anomalies. This is observations, and the plot on the right is the model. So these Hawkmiller plots are for the monsoon active phases, and the problem in most of the coupled models is that there is a slower northward propagation of monsoon intra-seasonal oscillations on the BSISOs, and there are associated biases in the precipitation and air-sea interactions. So what we realized was that Indian Ocean dynamics are misrepresented here, and it needs to be improved. So how do we do that? Since we know that the freshwater in the Bay of Bengal is quite important, the climate forecast system does not have a river routing model as such. So the river runoff which goes into the ocean model is prescribed based on annual mean climatology, which is perhaps not a very good strategy, especially for CFSV2. So I thought of addressing this bias by coupling a river routing model to the CFSV2. While doing this work, I came across the CESM routing model, which is now upgraded to the Mozart. I thought of initially using that model for CFSV2, but I ended up using a completely different routing model, which is shown here. So how do you add rivers? You try to couple a river routing model to your coupled model. So basically, I used the RWIC model, which is used as a processor for the variable infiltration capacity model. So I set up this model globally for all the river basins from 60 south to 60 north. And you can see those basins here. So this model basically takes the topography. You delineate river basins globally, develop a flow network, and the runoff which is generated by the land surface model is passed through this flow network to give you the routed stream flow at land-ocean boundaries. So this is how I did it. So the routing model collects the early success of surface runoff from the land model and routes it through its routing network and passes it to the ocean model once every 24 hours. So this is an online coupling of this routing model with the CFSV2. So what I did was I did seasonal hindcasts, which are 9-month runs for the period of 1981 to 2017 using 10 ensemble members. The model was initialized in February, and the integration was from March to November. And I verified these simulations for the summer monsoon season, which is JJS. I basically looked at 3 things which are important for the Indian monsoon: the synoptic time scales, which is about 2 to 10 days or so, and the intra-seasonal time scales, which represents the 30 to 60-day variability for Indian monsoon and the seasonal mean monsoon. So first, if you look at the monsoon low pressure systems so basically RIV means the model where I have added the rivers, and control is the controller, and where the runoff is prescribed based on annual mean climatology. So if you look at the low pressure systems here, if you look at their track density, the difference in the track density, you can see enhanced genesis of low pressure systems in the northern Bay of Bengal. And if you do a LPSJS composite rainfall, you can see enhanced rainfall activity over parts of eastern and central India, which is about of the order of 1 to 1.5 millimeters per day. So there is enhanced LPS activity, enhanced synoptic activity in the northern Bay of Bengal, and the associated rainfall in the river run. What causes this? I looked at the so this plot shows the lag composite of the temperature tendency term of the mixed layer heat budget, which is basically for RIV minus CTL, and lag 0 here in the middle shows the day of LPS genesis. So there are enhanced, as you move forward in time from the genesis, you can see enhanced gradients in the Bay of Bengal, which is crucial for the simulation of these systems and enhance the moisture availability to these systems. And this is basically governed by the asymmetric surface heat fluxes. I also looked at how the mixed layer depth and the barrier layer thickness varies at intra-season timescale. So when a freshwater plume comes in the Bay of Bengal, you expect the mixed layer to thin or to shoal, and what follows is a thickening of barrier layer, which sort of cuts off the interaction of the mixed layer with the subsurface or the colder ocean. So here lag 0 indicates the days from meso peak. Day 0 means the peak rainfall over Indian landmass. So what you notice here is that when there is a large rainfall over the landmass, it will take some time to reach the ocean and cause the shoaling of mixed layer, which you can see here. The red curve is the control and blue is the RIV run. You can see the mixed layer depth is thinner compared to the control run. And after the rainfall over land region, you can see the thickening of barrier layers here. Though the impact on SSG and rainfall is not as clear as you would expect, but you can see some sort of strengthening of the break phase following the active phase. So what was the net impact on the intraseasonal timescale convection center? So these plots show the specific humidity, vertical velocity, vorticity, and divergence for the top panel is controlled and bottom is the RIV run. So these parameters are composited with respect to the convection center of meso. And there is always enhanced humidity to the north of convection center, which helps in propagation of these systems. So you can see there's enhanced specific humidity to the north of convection center in the RIV run. There is the vertical velocity is enhanced. There is the vorticity is stronger at the lower levels, and there is stronger lower level convergence and upper level divergence. So what the net effect is a stronger northward propagating mesopulse. So the coupled models suffer from this problem of slow propagation of the mesos or the BSISOs from the equatorial region to the Indian landmass. This speed and organization of mesos improves somewhat in the RIV. So this is my last slide where I have summed up the mechanism of how this works on the synoptic time scales. There's a stronger asymmetric surface heat flux forcing, which results in enhanced temperature gradients in the Bay of Bengal, which causes frequent LPS genesis. And on the other hand, at intraseasonal timescales, it causes the shoaling of mixed layer and the formation of thicker barrier layers. which then ultimately cause enhanced ERC interactions restricted to the shallow mix layer and a stronger meso-associated circulation. And the scale interactions between them result in better representation of convection at synoptic to intraseasonal timescales. And the Taylor plot here shows the seasonal prediction scale for this 37 years of hindcast. And if you note here, the blue dot here is higher. So these are the anomaly correlation coefficients. So the scale improves in the arrival to about 0.47 from 0.34. So so that's it. Thank you and if you have any questions, I'm happy to answer them.
I think we can take one question. Looks like there are no questions, so we'll move to our first in-person speaker, Dylan Amaya.
Hello. Kind of envy the folks online. It's very, very cold in here. My name is Dylan Amaya. I'm a research scientist at the NOAA Physical Sciences Laboratory. Is this one of the fancy things I can point and it'll show up? Top button. Maybe not. That's okay. I'll describe. I don't see any. Oh, there it is. Okay, cool. And today I want to talk to you about building seasonal climate forecasts from large ensembles. And I'm adding a plus here because we're going to do more than just build some forecasts from large ensembles. And we're going to be doing this by implementing a technique that's very computationally efficient. And it's something that we're really excited about, but this is very much work in progress. So I'm totally open to any comments or suggestions that folks have. So we're going to be implementing something called the model analog framework, which is a fairly old idea. It actually goes back to the 60s with Ed Lorenz when they were trying to predict weather forecasts or create weather forecasts based on matching the current weather state with some data library in the past. So this can be extended to climate timescales. Well, let's say we transport ourselves back to January of 1998. This was the state of the world in January of 1998. And we might be able to find two states in the climate system that are related in 1998 that are very close to each other, and we can call it an analog. So the way that we might do this is by comparing this map of sea surface temperature anomalies to a data library. And often it's a pre-industrial control simulation, but it doesn't have to be. And you compare January of 1998 to all the Januaries in that library, and you try to find the one that looks the most similar. And in that case, you have an analog. And so then you can use the model's trajectory of that analog state as a forecast. So it's a purely statistical forecast, but it has some benefits. It's very cheap, it's very easy, and there's no like initialization shock. So a fully dynamical system is often initialized fully throughout the atmosphere, the ocean, the land surface, and that often comes with shocks to the system because you're dragging the model away from its preferred part of the attractor to where the observations are. And so there's a drift back to that model biased state over the course of the forecast. Here, you're already in the model's biased state. You don't have any of that initialization shock. It can often lead to very skillful forecasts. So for some applications, model analog forecasts can be as skillful or sometimes in some cases even more skillful than dynamical forecasts. And this is just an example of that from Ding et al. 2018, just showing the RMS error of analog forecasts in the tropics of sea surface temperatures next to dynamical forecasts from the North American multimodal ensemble. And you can see that within the Nino 3-4 region, for example, you're getting skill that's at least as good as what's coming from these dynamical systems. But there's a caveat to that. Often these sorts of comparisons that you're seeing in this paper aren't always apples to apples. And that's because the skill differences that you can see between a model analog forecast and a dynamical system can be coming from a variety of different factors. It could be a different model that you're using. It could come from different initialization data. It can come from different verification periods. All sorts of things can factor into that. So it makes it very difficult to fully understand the added value of the model analog technique, or on the flip side, the added value of fully initializing an atmosphere, an ocean, and a land surface to create this dynamical system. Is it worth running this expensive integrated approach for a forecasting system? So part one of what I want to talk to you about today is, can we make this more apples to apples? Can we create model analogs from the CESM2 large ensemble using the same data that's used to initialize SMILE? And so the idea here is that we're getting much closer to apples, and we can actually see the added value of this technique. So just to remind you, I know we've talked about it a few times here, but SMILE is the single to multi-year large ensemble. It uses CSM2. It goes from 1970 to 2019, uses historical and SSP3 radiative forcing, specifically the smooth biomass burning forcing from the CSM2 large ensemble that was also used for the second 50 members of the CSM2 large ensemble. It's initialized with FOSSI, GA area 55 in the atmosphere, FOSSI in the ocean, and something called trendy over land, which is CLM forced with different atmospheric input. It has 4 initialization times, February, May, August, November, and it has an ensemble of 20 members. So an excellent data source, excellent hindcast for both, practical purposes of understanding predictability, but also hopefully in the future, real-time applications. And today I'm going to compare to what I'm calling CSM2 model analogs, or CSM2 MA, where I'm going to draw model analogs from the CSM2 large ensemble itself, specifically the 50 members with the same radiative forcing as SMILE, so the second 50 members with the smooth biomass burning. Same time period, 1970 to 2019. So because I have 50 members and 50 years, I have a data library of 2,500 years to compare to. And so I'm going to be drawing analogs based on the same ocean initial state as that is prescribed in SMILE. So I'll be using monthly mean FOSSI sea surface temperatures. I'll be comparing from 60 south to 60 north. Super importantly, both the FOSSI data was detrended linearly, and also the large ensemble ensemble mean was removed from every ensemble member, so that I'm matching internal variability. I'm not looking for trends in this case, although the trend is an important part of the forecast scale the longer you go out. So only looking at forecast scale of internal variability today. There are no computational constraints with this, so I could forecast all 12 months if I want to. I could have an ensemble size of 100 if I wanted to, but for apples to apples, to get closer, I'm going to do a 20-member ensemble. Okay, so how well does this work? This is a surface temperature skill in SMILE for November initializations, verified against ERA5 data. This is again from 1970 to 2019. Trying to get my cursor. There we go. These are for 4 different lead times. So it's the first 4 lead seasons. And just for brevity, I'm showing you the first year of the forecast. The number is telling you what lead month that season starts in for the forecast. So again, for SMILE, you're seeing that there's lots of skill near the initialization. And as you go further out, it gets slower, it gets worse over time, which is true of all hindcast systems. And this is the forecast skill from the model analogs. And so right away, you can see some really interesting things. You can see that the forecast skill, especially away from the initial condition, is comparable to what's coming on from SMILE. And so we can take the difference to sort of quantify this. And in the difference figure on the right, the stippling indicates when the skill is significantly better for that forecasting system. So, and that's based on a bootstrapping method. So positive values mean SMILE is a significantly better forecast. Negative values says that the model analogs are a significantly better forecast. And the point here, the take-home message I hope you can see, is that far away from the initial condition, and this is just giving you an example of one region where the initial condition is really helping SMILE, far away from that initial condition, the model analogs are largely indistinguishable from SMILE. And that's because they're the same models. They have the same attractors. Once they get away from the initial condition and they're back in their biased state, they're evolving in much the same way. So as long as you get an initial condition that's similar enough, you're going to get a forecast that's largely the same. So can we, I guess the question then becomes, can we improve the model analog forecast more by trying to optimize for early lead times? Can we make it a better initial condition so that we can capture some of this early forecast skill that SMILE has the benefit of catching because it's fully initialized in the atmosphere and over land? Oh, and just to say that this result holds for other variables. So this is the same forecast for precipitation. I'm not going to dwell on it for the sake of time, but I'm happy to go back if anybody's interested. And the same forecast for sea level pressure, where you can start to see again that far away from the initial condition, the model analogs are very similar, and in some cases better. Okay, so can we improve the model analogs further, try to improve the skill at those early lead times? I'm going to try and do that by changing the way I draw analogs. So now I'm going to be drawing not just based on FOSSI sea surface temperatures, but also JRA 55 500 millibar heights and trendy soil moisture, again from 60 south to 60 north. So this is sort of a statistical Earth system model at this point. Can we get it anywhere near to what SMILE is doing in those early lead times? So just to show you how each of those variables impact the skill of surface temperature, this is again November initialized 0-month lead forecast skill in the model analog world. And this is showing you the forecast skill for surface temperature, but based on drawing analogs for 3 different variables. So the top left you've already seen, that's from drawing from SST. The middle is from drawing based on 500 millibar heights, and the right is based on soil moisture. So two kind of cool things pop out right away. One is that you can get a lot of the way there just with 500 millibar heights, which is really interesting to me. The second is that soil moisture actually doesn't help as much as I thought it would, at least on these seasonal timescales. So that seems to imply that including trendy soil moisture initial conditions in SMILE may actually not be helping you as much as you think it may be. It may not actually help your forecast all that much. So now we can start to combine and mix and match these things. So these are just the same skill maps, but drawing analogs based on some combination of the different initial conditions, where you have like SST plus 500 millibar heights, or SST and soil moisture, 500 millibar heights and soil moisture, or all 3 combined. And in this case, without having an exact objective measure for which of these is the best, sort of my eyeball test tells me that you're getting the most bang for your buck when you include the ocean state in the form of SST and 500 millibar heights. In that case, you're starting to maximize what's going on over the ocean, but also you're starting to capture some of that early lead skill over land when you include something like 500 millibar heights. And just to sort of hammer home that point, this is the same difference map for November initialization, 0-month lead, for SMILE, the model analogs, and the difference. The top row you've already seen. That was before, when we were just drawing on sea surface temperature anomalies. And the bottom is drawing on SST and 500 millibar height anomalies. And again, you'll see this region over East Asia that I'm just highlighting here, that if you don't include 500 millibar heights in the model analog choice, SMILE is clearly, it has an advantage because you're fully initializing that atmosphere. But you can improve that forecast in the model analog space by including that information in the selection process. But it's not without its drawbacks. When you have a finite library size like we do, when you aren't optimizing for, say, SST, like we were before when we were drawing from SST, including another variable is inherently going to hurt the skill of the thing that you were originally looking at, SST. So you'll see basically that the differences in the bottom row are slightly bigger over the ocean than they were before. And that's just saying that your SST forecast is slightly worse, with the benefit that your surface air temperature forecast over land is slightly better. So there is some give and take with this, this selection criteria. Okay, so just to summarize very quickly, using mostly the same ocean initial state, model analog forecasts from the CSM2 large ensemble are largely indistinguishable from SMILE once you get far enough away from the initial condition. And I think this is very, very cool. I mean, it says that all this hard work, all the blood, sweat, and tears that went into the large ensemble are, worth it for a lot of reasons, but they can also produce really skillful and useful forecasts. Model analog skill at short lead times could potentially be improved by including the atmosphere as part of the selection criteria. So one other thing I want to talk about and just sort of highlight as another exciting result that we're really interested in pursuing further is this concept of a high resolution forecast in model analog space. High resolution forecasts are extremely expensive to run. For those of you that have used them before, you're aware. So we're going to be developing high resolution model analog hindcasts based on CSM HR. So the idea here is that we have this 350-year PI control simulation with a 10th degree ocean, 25-kilometer atmosphere. And we're going to draw analogs from that control simulation, where the analogs are selected based on detrended monthly mean sea surface temperature anomalies from 30 south to 30 north. And I'm actually going to do that at a lower resolution just because it's computationally easier at 1 degree. And I'll be drawing it based on an ocean reanalysis called GLORIES, which is actually a high resolution tool, but I've interpolated it to 1 degree just for the selection process. And then based on the chosen climate state, you create a 10-kilometer forecast. In this case, I'm going to show you ocean forecasts for a specific region, and I'll verify against GLORIES as my truth. And I'm doing this from 1993 to 2020, and I'll keep the top 10 matches as my forecast ensemble. Okay, so how do we do? This is a figure from a paper that came out last year by Mike Jaycox et al., which they used a dynamically downscaled seasonal forecasting system to produce 2 initializations of sea surface temperature forecasts for the California current system. So you're seeing the California current system. And this was a very expensive run that could only run these 2 initializations. And this is just showing you that the skill for 2 lead times, 1.5 months lead, 6.5 months lead for January and July initializations. And so we can compare exactly to our high resolution model analogs from CSM HR for a January initialization, a July initialization at those same lead times. Stippling in this case means an insignificant forecast. So right away, you'll see some differences. Obviously, the fully initialized run has more skill offshore in January for a 1.5 month lead. But within the nearshore environment, I would make the argument that the high resolution models are doing really well, as good, if not better, than this dynamically downscaled system. And that is really where we need to leverage this high resolution, is in the coastal environment where we want to take advantage of having those physics and making those forecasts. So the last thing I want to show you is just sort of summarizing that information within that coastal environment. Basically, I'm going to take the forecast from the high resolution model analogs, and I'm going to average them within 75 kilometers of the coastline, which is this brightest yellow here, and for 3 different regions, the South, Central, and Northern California current system. So then we can display the skill within 75 kilometers of the coast in these model analogs for something like SST in those 3 different regions. If you're familiar, this is a typical skill diagram where you have lead time on the y-axis and initialization month on the x-axis. This is not a skill diagram that we can actually make right now for other forecasting systems, because often those high resolution forecasting systems don't have more than a handful of initializations. They don't have all 12 months, for example. And we could play the same game for sea surface height and bottom temperature. So this is temperature on the seafloor right along the continental shelf within 75 kilometers of the coastline. And the take-home message that I want to leave here is, I understand that many of you don't have any context for whether this skill is good compared to other models. Part of the issue is that it's really hard to compare to other models that don't really exist. But compared to global models, just sort of take my word for it, this skill is really exciting and cool. You're getting a persistence forecast skill that's associated with like the first 5-ish months of the lead times. And you're also getting this really cool diagonal band that's associated with INSO. So you're getting a wintertime skill bump for having deterministic forecast skill associated with INSO. These are all characteristics that we see in dynamical systems that are being drawn out in the model analogs. Okay, so I'll just summarize there. Part 1 you saw before, but again, high-res model analog forecasts are very promising, and we're hoping to explore that further. Thanks, y'all.
Questions for Dylan?
Nice work, Dylan. About the first part, I know you want an apple-to-apple comparison. I wonder if you have tried a 50-member to draw your mono analogs from all 50 members or even more, because you might have better analogs from a larger library that might increase the skill for your approach. Have you tried that?
Yeah, so I should clarify, and sorry if I wasn't clear. I am drawing the analogs from all 50 members, but I'm keeping the top 20 matches as a forecast ensemble. So you could, in theory, improve the skill by keeping a larger forecast ensemble, but the further you reach down into that barrel, the worse matches you're going to get. And at some point, you're going to get matches that are so bad that you're making your forecast skill worse. So there's a curve you can draw, and you often want to try to hit the top of that. You want to hit the top of that hill where you have a forecast ensemble that's big enough to maximize your skill, but small enough to not have really bad matches. So I've drawn that curve for Nino 3.4. Turns out that number is about 50. So a forecast ensemble member of 50 optimizes your skill for Nino 3.4, but that may not be true for other regions. But, and to your point, we could also draw we could draw analogs from the full 100 members of CSM2 and possibly get better matches by having a bigger library. Bigger library is always better. Thanks.
I was wondering if you'd considered constructed analog approaches where instead of picking individual members, you have a weighted sum of near neighbors, and then you weight the forecast in that way. It could be a nice way to, find members with anti-correlated patterns of different variables.
Yeah, it's a good point. It's not something I've tried or considered, but certainly open to exploring that further. Happy to take any papers you have.
That was super cool. I was wondering if you'd considered any kind of initial conditions that had a better representation of the upper ocean state besides SST. So something like sea surface height or upper, 100 to 200 meter temperature or something, realizing that the more you add in, the, further from barrel you're grabbing.
Yeah, SSH is often one of the variables that's included in analog forecasts just because of its representation for upper ocean heat content. In this case, including SSH improves your tropical SST forecast, but it doesn't help the mid-latitudes all that much. If I were going to make a decadal forecast, for example, including some representation of upper ocean heat content is going to matter a lot because it's going to help you with your trend. It's going to help you with your overall lower frequency variability. But anyway, that's a long way of saying that, yes, we've tried SSH. It does help. but not so much that I felt like I needed to include it here.
Thanks.
Yeah. Thanks, y'all. Appreciate it.
Let's thank all of our speakers from this morning. Gonna pick up where I left off earlier, giving the update on activities from the head office, I guess, of hindcast generation. So we submitted this forecast to the WMO Lead Center. This was our decadal forecast, initialized in November 1st of 2023. And when they put the plots on the website, we noticed that we had the situation of being an outlier, particularly over Antarctica, in terms of our year one forecast compared to other centers. And so we are digging into that. And that brings me to the land initialization issues that it would be great to try to sort through as a working group. So what we did for SMILE and also for CESM2 DP is we leveraged this trendy 2020 forced land only simulation that had been run for the global carbon stock take, is my understanding. So this was a forced CLM integration that had been spun up to equilibrate carbon pools and then integrated from pre-industrial to present day using this special trendy forcing. Unfortunately, it only went through 2019. So to extend that to near real time, we extended it with a JRA 55 forced land only simulation, thinking that would be a reasonable way to initialize closer to real time. What we didn't realize is that when we did so, if you look here at the SMILE November, so the initialized November, zonal mean surface air temperature anomaly in forecast month 1, we significantly changed the background climatology of the land state such that Antarctica is much colder in the JRA 55 forced run than in the trendy run. So what happened? When we dug into this, we realized that when they run these trendy simulations, there's no forcing over Antarctica. They completely ignore it. So Antarctica is a completely unrealistic state throughout of all of our historical hindcasts, but it's a consistently unrealistic state. So we don't get anomalies. We don't get any signal coming from Antarctica. When we switched to JRA 55, we included Antarctica as part of the domain of the land model, and JRA 55 air temperature is quite cold over Antarctica, much colder than we were getting in our trendy simulation. So all of a sudden, our land state is anomalously cold. That becomes a prediction signal in our anomaly world. So this is where this cold feature came from. And, it really is drawing our attention to how do we initialize land in a consistent way and, avoid these discontinuities and, be able to spin up from pre-industrial to near real time. And we've seen a couple of talks now, and including some results that I showed from the DART assimilation initialization, that land initialization actually matters. And it matters not only for subseasonal, it matters for seasonal too. And I think we have to pay more attention to it. So what we've, kind of our fix for temporary fix for the problem for SMILE and for CSM2 decadal prediction is the following. There is a new trendy 2023 forcing data set that extends out through 2022. Now this trendy 2023 forcing climatology is likely different from this one because they changed the forcing data set. So, you know, a changed climatology in hindcast world is a signal. So we have to be aware of that. And then our only option for 2023 is then to do, you know, something ad hoc. Here we're doing JRE 55, but we're eliminating Antarctica. So we are not, you know, initializing Antarctica with an anomalously cold state. So here's what it looks like, you know, for 2020. Here's November 2020 from observation, surface air temperature, November, December, etc. And this is what we had in our old version of SMILE for 2020. We had these extreme cold conditions over Antarctica that then have an impact on the ocean state, right? This is a coupled run. You're changing the climatology of one component. It's going to impact others. So you can see the development of cold anomalies over the Southern Ocean. And then this is the difference from observation. So this is the forecast bias here. Here's our new solution. So we're now initializing from this green trendy 2023. We've eliminated cold Antarctica and some of the other kind of impacts over the Southern Ocean, but we basically retain the character of the forecast anomalies throughout most of the globe. You know, so this isn't a major issue. It's not impacting our ENSO forecast for this past year in any significant way, but it is something that we, you know, are suddenly now more aware of than we were before. And so, you know, ESPWG needs a better strategy for land component initialization, and we'd like to figure out what that should be. All right, I might be able to finish up the update here, and then we can use the afternoon time for pure discussion. So just a quick rundown of how we've used our allocation. We're almost to the end of our CSL allocation that goes through October 2024. So we've completed this 10-member SMILE pacemaker suite that I mentioned. We've completed a new CSM2 decadal prediction hindcast set. So this goes out 10 years into the future. Due to the land issue, we're having to rerun CSM2 SMILE and the decadal predictions over this recent 4-year period. And so anyone out there who has gotten early access to the SMILE real-time forecasts, you might want to be cognizant that we plan to overwrite those with these changes once we change the land initialization. We've completed CSM2 multi-decadal prediction set that we're going to contribute to a multi-model study. I have already shown you some results from S2S using DART initialization. Most recently, we've been, not we, but Yaga and Sasha have been running S2S sensitivity experiments to look at the different impacts of land atmosphere coupling strength. And then Judith Berner and Will Chapman are going to apply their online deterministic bias correction stochastic physics package and test it out in CSM2 S2S. So the bottom line is we've more than used up all of our allocation. We've received generous supplements from Dave, and we hope to you know, be able to do our part to use up any extra 4 hours that may be lurking through October. And then this is something that you know, is just meant to spark some ideas for what we can discuss this afternoon, potential topics for discussion. What do we do in the post-JRA 55 DO world for ocean sea ice initialization? Of course, there's an effort to develop an OMIP3 data set that will take some time. And I was just at a NOAA S2S conference last week, so I'm learning their lingo maybe we should try the replay method, which is basically coupled model nudging to off-the-shelf analysis products. We haven't done that. We could try that. We could save the nudging increments. This would be, maybe a first step towards testing out the benefits of fully coupled DA, just using products that other centers have generated, and then saving the nudging so that we can do these online corrections potentially. I've already mentioned this. What can we do about it? And then, hopefully get some feedback from the working group on what we should prioritize in the coming CSL proposal. And with that, that's all I have. So I'll take a question if there are any, or we can adjourn for lunch. Let's adjourn.
I wanted to pick your brain a little bit about that second bullet point that you just had about land initializations matter. In the context of, I guess, my presentation, I'm still trying to interpret the lack of skill added by including soil moisture in the model analog selection. And reconciling that with like the bulk of literature that says that like soil moisture is an important source of memory for precipitation forecasts. I guess I'm just not finding that. And so I'm trying to understand to what extent land initialization matters for these seasonal timescales. You mentioned that it does. What can you point me to papers? I mean, I'm trying to understand it better and help reconcile the results I'm seeing.
Well, Yaga has a paper where they've, withheld the land information, and you would think that would degrade the skill, but instead it proves it. So, I mean, there's skill sensitivities there, and that may relate to your result that, you're initializing your model analogs from the trendy simulation, which may not be a good initial condition. So, that maybe that's why you're degrading or not improving skill. And that may be also the case in S2S. Go ahead, Dave.
Yeah, please.
Yeah, I think a potentially significant part of this is the CLM5 land model and the parameterization of it, the parameter values we're using. And so when we moved to CLM5, we included this thing called plant hydraulic stress, which is a more physical representation of how plants use water based on gradients and hydraulic stress. And so, but what we sort of found is when we introduced that new model, plant hydraulic stress, there was a bunch of new parameters in there, which we didn't have good constraints for. And so we took kind of best guesses for what they should be. Subsequently, we found that most likely it's in a realm of the parameter space, which is not that sensitive, where the soil moisture is not having that big of an impact on the vegetation transpiration. And so we're moving, we've done for CLM 5.1, we've moved those parameter values like closer. We can look at where the curve kind of tilts over and move them closer to the stress point. And so we think that would probably have led to more situations where there's actually stress. And then you're seeing a feedback between the soil moisture anomaly and evaporation. And the second thing that happens with plant hydraulic stress is it also has a thing called hydraulic redistribution, which is roots basically moving water through the soil and sort of normalizing the soil moisture across the vertical distribution, kind of evening things out. And that also has a tendency to like reduce the sensitivity of models. So it's a real world process, but we think it's overcooked also. So it's doing it more effectively than it probably should be. And so again, that's like working against a soil moisture anomaly having an impact. So CLM 5.1 might be a bit better, and definitely for CLM 6, we're trying to have this in our minds as we kind of tune up the model to make sure we're not in that space again. But it remains to be seen. We're trying to calibrate for a bunch of things all at once, and we'll see whether we can come up with something. So those are two things to just keep in mind.
I also think where the land matters might be conditional on the kinds of events we're looking at, and just looking climatologically, we're not getting the whole picture. I think there was a talk in the machine learning session showing for certain weather regimes, the land was mattering. So it'd be good to investigate it more, I think, conditional on heat extremes or droughts.
Yeah, I just want to say thank you for the perspective. It sounds like that result in my work could just be very CSM2 specific. So I appreciate that.
Yeah, and I think to underscore Isla's point, the land seems to have an impact, at least plenty of studies have shown in terms of extremes, heat extremes, and that feedback that leads to heat extremes. So maybe, yeah, looking at it in an average sense, we're not getting a picture of what the land is really doing.
I agree with all those points, but my question is, how do we build confidence that we have good land initial conditions? I mean, can we identify, case studies of subseasonal extreme events that, we want to test out our system on? What would be the best approach for, ensuring that we're going to get benefits from land initialization? Okay.
I don't have an answer, but I wanted to ask about you showed the DART versus NCEP forced. Is that NCEP is different from trendy, or is that the same thing as the trendy? I'm just wondering if there are multiple land conditions that we could look at to see.
Yeah, there are. So Yaga, that was the S2S control that we swapped out in NCEP forced land state, I believe. So yeah, using CFS, right?
So do we know if like those degradations compared to DART over Africa and the Amazon are also there with the trendy, or we just don't have the right runs to look at that?
We'd have to run those runs to
Okay, because
determine.
those were sub-seasonal, right?
Yeah.
Okay.
Yeah, we could run those. Yeah. All right, let's break for lunch and come back for the afternoon session. Thank you.
I'll run the session. All right, it's 1:30, so I want to get started promptly so everyone has the time that's been allocated to them. Our first talk for the afternoon session is from Nikki Lewandowski.
Okay, welcome back from lunch. Hopefully you got more than a bowl of lettuce with some grains. I didn't. So I want to begin by thanking our co-chairs for giving me the opportunity to present today this idea to you. And that's indeed what I'm presenting is just an idea. This is not a paper that's been published. It's not even a paper that's in preparation. It's not even a proposal that's been written. In fact, it's an idea for a proposal that we're hoping to submit to the NASA Ocean Biology and Biogeochemistry program next month. And it seems a bit strange to present an idea for a proposal to a big audience such as this, but I think it's important that we do this first because it's helpful for us to get feedback from this working group on our idea, what things we haven't considered that we probably should be considering, but also because if we are selected for funding, which probably like a 50-50 chance based on my own personal history, the success of our plan will depend upon involvement of this particular working group. And so it's important that we just sort of lay it out there now. And even if we're not selected for funding, a lot of us are already thinking about it. And so we're probably going to go for another call to try to get this funded eventually. So that's why we're presenting it to you today. I want to acknowledge two graduate students in my group, Sam Mogan and Genevieve Clow, for providing model output and also for providing some of the plots that I'm going to share with you today. And I also want to acknowledge that this idea is not solely mine. This is an idea that we've thought of collaboratively, myself, Keith Lindsay, Dan Omrine, Moha Garamti, also Mike Levy at NCAR. So I want to acknowledge their contributions. Now let me figure out how to advance the slide. There we go. Okay. So our idea, as you can see in the title, is about a biobloom forecast. What we would really like to do is to use a forecast system to predict extremes in phytoplankton blooms. So I want to begin by talking about what those extremes look like. I want to demonstrate to you that they happen in the real world. And then I want to tell you our plan, which you'll be a little bit overwhelmed by because it is very ambitious. Okay, so what are phytoplankton bloom extremes? So here's a sketch and a schematic illustration, if you will, of a time series of a typical phytoplankton chlorophyll concentration as it evolves over the course of a year at a particular location in the ocean. And the black line is meant to be sort of the seasonal climatology, with the gray enveloping that black, sort of the 90th and 10th percentile, given the variability in that region. And chlorophyll is a light harvesting pigment that all phytoplankton and living organisms contain in order to perform photosynthesis, that all photosynthesizing organisms contain. And this chlorophyll, you can see in the ocean, is akin to the amount of phytoplankton biomass. It's not identical, but it's close enough. So let's think about larger amounts of chlorophyll as being associated with more phytoplankton in the ocean. And chlorophyll is something that we can detect from satellites because it reflects in the green, unlike the rest of the ocean, which primarily reflects in the blue. So at this particular location, you can see that the chlorophyll concentration achieves sort of a minimum here in the winter months, in the fall months, and then it achieves a maximum in the spring. This is a location in the ocean characterized by what we call the spring bloom. And it happens pretty much every year at this location that there's a spring bloom. And so you can see that the uncertainty or due to variability is very small here. So what would a phytoplankton bloom extreme look like then, superimposed on this kind of climatology? So here's just a sketch of one example of a phytoplankton bloom extreme. This is what I'm calling a super bloom. So the phytoplankton chlorophyll concentration exceeds sort of the 90th percentile here in the spring, but the bloom is occurring earlier in the year than a typical peak bloom might occur. So this is a super bloom, meaning that the chlorophyll concentration is much, much higher, but it also means that it's going to have some kind of impact on the ecosystem, right? Because phytoplankton form the base of the marine food web, and if their concentration changes significantly or is different than what the ecosystem is expecting to happen normally, there's going to be trickle-down effects on things that eat the phytoplankton and the things that eat them, right? So this is going to have some kind of ecological consequence. You could also imagine a situation like this, where the phytoplankton do indeed bloom in the spring, but the bloom is so small that you can hardly even see it, right? And the bloom concentrations are so low that they're well below the 10th percentile in terms of the typical variability of phytoplankton chlorophyll concentration. And so this would kind of be considered a bust or a low extreme in phytoplankton chlorophyll concentration. This would also have significant consequences for the marine ecosystem, right? Because the marine ecosystem is used to having this sort of seasonal pulse of food available to it. And that seasonal pulse of food is not coming this year, right? So this is going to have probably very detrimental influence on the marine ecosystem. So our idea is to think about whether or not it's possible to predict whether these phytoplankton bloom extremes are happening in advance. But before we do that, I want to convince you that these bloom extremes are not just theoretical, they're things that happen in the real world. So here's an example of the largest super bloom that occurred in the center of the North Pacific subtropical gyre back in 2010. So this is a false color satellite image of chlorophyll in the subtropical gyre for orientation. This over here, that's Hawaii. So you can kind of imagine where you are in the world ocean. This is the center of the subtropical gyre. The way I would describe this to the non-biogeochemist is that this is like the desert of the ocean, not because there's no water, obviously there's water, but because there's no life here, right? This is a place where the circulation favors convergence and it suppresses the thermocline and it suppresses the nutricline. So phytoplankton really don't have access to nutrients here. And so for most of the year, they can't bloom. There cannot be a phytoplankton bloom here. So certainly not at the surface and certainly not detectable by satellite. And yet here in the middle of June, which is sort of the most deserty month of the year, there's an enormous phytoplankton bloom that pops up in the center of the subtropical gyre, which is kind of crazy to see. And in fact, this is unprecedented in the satellite record. It's never occurred before, and it's never occurred since, as you can kind of see in the time series on the bottom, which is the June-July average chlorophyll concentration in this region. And although I would love to say that there were marine biogeochemists out there making lots of measurements during this super bloom, we were not. We didn't know this was coming. Nobody takes measurements of biogeochemistry regularly in the ocean. And so we have no idea really what happened to the ecosystem in response to this major bloom, but we can imagine that this probably had a big impact. If there's suddenly life in the middle of a desert that's sustained for several weeks, it's going to have an impact on the ecosystem in that region. What's interesting is if you go backwards in time from when this bloom occurred, this super bloom, you can start to see that there are hints of it already beginning to occur a couple of weeks earlier. as shown in this paper from Chow et al. So you can see here in the center of the subtropical gyre, a few weeks earlier, there's already some indication that there's about to be some kind of biological activity in the region. And so that leads me to think, at least, like if we knew information about this chlorophyll concentration in advance, could we have predicted this bloom that was about to occur, this super bloom that undoubtedly changed the local ecosystem? Another example of bloom extreme is here in the California current. We're in the northern California current. So for orientation, this is Washington state up here. This is Oregon here. And we're looking at chlorophyll averaged over the Newport line, which is this red line right here. And they have collected information about biogeochemistry in this region and ecology for several decades. So we have a pretty good sense of what the climatological chlorophyll concentration looks like here. And you can see that in the spring, there tends to be a bloom. And then in the late summer, there tends to be a secondary bloom. This is because the lights turn on here and they're photosynthesizing. The phytoplankton draw down all the nutrients, and then the nutrients get mixed back up in the late summer, and they again are able to photosynthesize. And then something dramatic happened in the year 2005. Here is the chlorophyll concentration in black, and you can see that there was no spring bloom. In fact, the chlorophyll concentration was close to zero in a time of the year when the ecosystem is expecting a big influx of energy, a big influx of food. And you can see that there is a fall or late summer or sort of early fall bloom here, but the magnitude of that bloom is nowhere near the climatology, right? So this is a failure to bloom. And indeed, mussel recruitment during this year was 85% lower than normal off the coast of Oregon. And this is unheard of, unprecedented in the record. So it had not only ecosystem impacts, but also impacts on the economy of this particular region. But then wait till you see what happens next. This is what happens in the 2 months subsequent to that failure to bloom. All of a sudden, there's this enormous bloom, right, that occurs following that. And the concentrations of chlorophyll in this bloom, like this is a crazy 75 milligrams per cubic meter. If you study chlorophyll, you're like, what is that even a possible measurement? It is. It's very, very high concentrations of chlorophyll. It's almost as if all of the nutrients that hadn't been used, that are usually used up during the summer months, accumulated just below the surface. And then something happened to bring all those nutrients up to the surface where it fueled this enormous mega bloom of phytoplankton. Unfortunately for the mussels and many other species, they're very dependent on what happens early in the season. And so this bloom was not enough to sort of save them, right, and to save the economy, but it nevertheless occurred. And it suggests to me that perhaps there's some information that preceded the super bloom that we could use to inform our prediction of whether the super bloom was coming. And perhaps there's even information over here that we can't see that might have informed our understanding of what was about to happen in terms of the failure to bloom the subsequent spring. So that's what I'm getting at with this project. The good news is that the current version of the model, CESM2, is capable of generating phytoplankton bloom extremes. So you can see this is one example of chlorophyll anomalies in the Gulf of Mexico, the Caribbean Sargasso Sea. This is a daily snapshot of chlorophyll anomalies or chlorophyll extremes on February 26th of 2019. And the colors indicate that there's higher than normal chlorophyll, and everywhere where there's a dot in this particular plot indicates that it's outside of the 90th percentile, so it's above that. So it's considered a super bloom, right? And this lasted for a couple of weeks in the CESM2. The other good news is that these bloom extremes appear to be, at least potentially, predictable in CESM2 SMILE. So what we're looking at here are plots very similar to the ones that Sam showed yesterday in his plenary talk where he got the grad student award. Hey, Sam. And the top left is showing the skill in getting an extreme phytoplankton bloom right 1.5 months after the initialization. So red colors here indicate that the model has some predictability. Blue colors mean it's bad, but you see quite a lot of red across the global ocean. And you can see that predictability lasts, it persists 3.5 months, 6.5 months, and even some places persist 10.5 months after initialization, noting that the period, the region I just highlighted, where we do see bloom extremes, is a place where there is quite a bit of predictability that's long-lasting in CESM2 SMILE. So taking all of this together as sort of motivation for the proposal that we haven't yet written but are about to write, the hypothesis that we'd like to test, or the question that we're trying to answer, is it possible for us to improve our ability to predict these phytoplankton bloom extremes in advance by initializing a set of forecasts with real-world chlorophyll data? In other words, can we take the satellite chlorophyll data, assimilate it into some version of CESM Smile FOSSI, and then generate a set of forecasts, well, that set of forecasts have better skill at representing these phytoplankton bloom extremes than a standard set of forecasts that doesn't include that satellite chlorophyll information. And that's what we would like to answer in this proposal. So you might be thinking already, gosh, that probably is going to involve a lot of work. It is. There's, I think 8 different people involved in making this project a reality if it's selected for funding. But this is the general work plan. So we'd like to take satellite chlorophyll observations. Now, note just for a minute that they're not equally distributed everywhere. We're missing quite a bit of these chlorophyll observations in places where there's clouds obscuring our view, and places where there's sun glint, and places where there's ice. So we need a way to gap fill them. Thankfully, we have a satellite chlorophyll emulator that Genevieve Clow in my group has developed that we can use to help think about gap filling. Once we have that, we'd like to assimilate that interpolated chlorophyll observation into an initial state CESM3 Smile FOSSI using data assimilation that Dan Ryan knows a lot more about than I do, but it's some kind of ensemble Kalman filter thing associated with data assimilation. Then we'd like to have this initial state used to launch or generate a series of predictions using CESM3 Smile. And then we'd like to use those predictions to assess our ability to skillfully forecast phytoplankton bloom extremes by comparing it back to the chlorophyll observations themselves. So not only is this plan complicated, but it also is obviously going to require quite a bit of computational resources, as well as the development of CESM3 Smile, which no one, even this morning, has even spoken about in this working group. So it's good that I'm bringing it up now. Okay, so our plan will require significant computational resources, as sort of detailed on the bottom here. And it also will build on anticipated CESM3 Smile efforts. That is to say, our group is anticipating that this will happen, and we're hoping that you are also anticipating that this will happen so that this will happen. What we'd really like to do is to create a chlorophyll assimilated initialized CESM3 Smile forecast system over the period of time for which we have satellite chlorophyll observations. So that's from 1997 to the present day. In order to do data assimilation, our low end estimate is we'll need something like 4 million core hours, although yesterday Moha and Dan said that we need to multiply that by 1.5. And then our estimate for doing reforecast using CESM3 Smile, assuming that there's already a standard configuration of CESM3 Smile, will require another 10 million core hours. So this is indeed very ambitious, and we do plan to request computing time along with our proposal in order to achieve our goals. So to summarize, I hope I've convinced you that phytoplankton bloom extremes are important. They can have significant impacts on ocean ecosystem health. CESM2 Smile indicates that the bloom extremes, well, that they're there, first of all. They're also potentially predictable and advanced. And it gives us some hope that perhaps forecast skill may be improved by the assimilation of the satellite chlorophyll data. And we are developing a rather ambitious and computationally expensive plan to assimilate this chlorophyll from satellites into the CESM3 Smile forecast system and to run that sort of alongside standard forecasts of CESM3 Smile. So with that, I will stop and take your questions. Thank you for your attention.
Just a quick question. I'm sure you said it and I just completely missed it. How does CSM2 Smile initialize the BGC fields to begin with? Is it just FOSSI?
FOSSI, so it uses FOSSI. So whatever FOSSI generates using the JRA 55 reanalysis is what it's using to initialize, which, by the way, is very different than the real world chlorophyll concentration. So there are significant biases in the chlorophyll. So the benefit of assimilating chlorophyll is quite high.
Okay, that was my second question. How does FOSSI do? And bad, I think.
I have a backup slide showing how bad FOSSI does. Let me just, there it is. There it is. Yeah.
Is this thing on? Yes, sorry. I'm curious, how or who will use bloom forecasts?
Well, I would hope that marine resource managers would find this of of high use. But I would also hope that our scientific community would find this useful. For example, if there were going to be some sort of extreme bloom event coming and we were able to plan in advance to go out and make sure we got our instruments ready and we are ready to sample that, I think the scientific community would benefit wholly from knowing this, because this is a place, ocean biogeochemistry is a very undersampled space, right? And so we have very few resources, and if we can put them where we'll be able to make the most use of them, I think that would benefit everybody.
All right, thank you. And thank you for presenting ideas. It's really fun. I'll have one more question. We can have one more question.
You want, this is really interesting, Nikki. So I'm thinking you presented 3 different locations, right? And then the question is like, what's driving that? Like in the upwelling system, is it upwelling winds? Are we resolving those? So in each of those, are we resolving the mechanisms? In the Gulf of Mexico, is it nutrient loading from the Mississippi and how that gets mixed? Do we have time varying nutrient loading?
Right. So these are all great questions I started to think about. Certainly, I think in the Gulf of Mexico, Sargasso Sea, Caribbean, there's something to do with ENSO and our ability to predict ENSO that has something to do with the chlorophyll predictability in that region.
Yeah.
The others could be upwelling related, right? The coastal California. I have no idea what's going on in the center of the subtropical gyre, the desert, where there's suddenly a bloom. Yeah.
Someone from Mike Barenfeld's group said it is underwater volcanoes, but I think this is controversial.
All right, we're going to move to our next speaker, Travis Aronson.
All right. Good to go. Cool. Hello, everyone. My name is Travis Aronson. I'm going to tell you a little bit about the work I've been doing. It's a part of a NASA EPSCoR funded project called the Global and Regional Origins of Water Stress, where it's really all focused on thinking about the ways that we can predict hydroclimate at a regional scale. So for the sake of this talk and for the sake of kind of the beginnings of this work, we're really focused on this region, the American Mountain West. So, marked boulder for us. So everyone here should care about this region at least a little bit. But as we know, this is a region that's characterized largely by its orography. It's very mountainous, which often can lead to some issues within our models. Additionally, just to give a little more background on kind of the hydroclimate of this region, I'm going to show this figure from paper from Gimeno et al., where they basically looked at the amount of precipitation that hits each region that comes from either atmospheric rivers in the orange or the low-level jet in the blue. And I've just highlighted in that red box this region that we're looking at, the American Mountain West. And as you can see, it really sits like right in the middle of the precipitation coming from both atmospheric rivers and the low-level jet. So I feel like for that reason, as well as the orography, it's kind of difficult to really be able to predict future hydroclimate in this region. It's kind of difficult for models. Like there's multiple processes that are incorporated. We have a lot of these, mountains that are difficult to see on our model grid cells. So it's a good space for us to be working in. And then just to give a little bit more background about like what should we care about in this region. So in this plot here, what I'm showing is the amount of runoff that happens from each of these regions. And the real point that I'm trying to make here is that in the American West, about 25% of the area produces about 90% of the runoff. And here on the right-hand side, I'm showing the fraction of the runoff in each of those like 25% area regions that originates as snow. And if you look in the American Mountain West, and really most of the American West, we're finding that most of these really high runoff regions are regions where you get a lot of snowfall. So for that reason in this work, we're really focusing on trying to predict winter and springtime snowpack, because that's really where the majority of our water comes from in this region. So we're focusing on this metric snow water equivalent. I'm sure many people in this room have heard of this before, but I'll explain it anyway. And it's the amount of liquid water that you could get if you melt the amount of snow that you have. And we're generally focusing in this work on the snow water equivalent, or SWE as I might refer to it, from ERA5 reanalysis, as well as CMIP6 models. And of course, we're at the CSM workshop, so that's including CSM2. And just for reference, I know that reanalysis is not observations, but I'm not going to show it in this presentation. We have done a fair amount of work to validate this reanalysis against the SNOTEL observations. So with that, I'll kind of get into a couple of the overarching goals that we have in this work. So first one is just trying to understand this fundamental question of how is the snow water equivalent, like the amount of snow we have available in the Mountain West, impacted by climate change? That's that very important fundamental question of, do we need to be worried about drinking water in the future? And then kind of that second goal is trying to really understand why there might be some issues in the model's representation of SWE, which is a little bit of a spoiler that the models are not perfect in this region. So with that, I'll start, showing some of my results. Or right here, what I'm showing is the seasonal cycle of the snow water equivalent in the Mountain West from reanalysis, where in the blue we have what we're calling our early period, which is from 1940 to 1959, and in red we have our warm period. And as one would expect from people who exist in the Northern Hemisphere, there's a lot more snow in the winter than the summer. And specifically, we see that the snowpack peaks in March, and then decays throughout the spring. That's really when we're getting our runoff and our melt during our melt season. And just looking at this reanalysis, it's pretty evident that there is a climate change signal in the historical record here. Like that 20-year period in blue has a significantly deeper snowpack than what we're seeing closer to the present day. So yeah, as I said, SWE is decreasing during historical climate change. And what's interesting that I want to point out is that if we look at a very similar plot, but instead of looking at snow water equivalent, we're looking at precipitation, we can see that this reduction in snow amount is happening kind of independent of a change in precipitation. Like there's very little changes in precipitation during the winter and spring months. And if anything, there's a little bit of an increase in precipitation. So it really seems like this decrease in snowpack is not attributable to the precipitation, and it's instead attributable to likely the runoff rates. So now we're going to start looking at the models. And yes, those light lines do show up. I'm very happy about that. So here in all of the faint lines, I've added in a large suite of CMIP models. And now if we just highlight CSM2, because we like that one, the point I'd like to make is that a lot of these CMIP models, including CSM2, are not getting the seasonal cycle of our snowpack correct. Like some of these models are having such a deep snowpack that's even off the scale. Some of them are not getting above an average of 30 millimeters at their maximum. And then there's others like CSM2, where at the beginning of the snowfall season, it appears to be doing relatively well, but its melt season starts too early. So the point I'm making here is that there's a lot of spread, and there's some things that these models are just not getting right. So now I'm kind of leading this question of, can we see if we can use a little bit of machine learning to try to improve this? Or even if we can't improve it, can we use some machine learning to try to understand these deficiencies at all? So to do this, we're going to use something called Gaussian process emulation. And I'm not going to really go into the details of how it works now. But what you really need to understand is it's basically fitting a multivariate line to your training data, which is kind of depicted in these red dots here. And then it comes up with this prediction that generally does really well when you're near the training data and not so well when you're far away from the training data. And that's shown by that blue line being further from the black line when there's not as many red dots nearby. And when that happens, you tend to also have much larger uncertainty as well. And so what we're going to do to actually emulate our snow water equivalent in this region is we are trying to predict the March snowpack, because that's the beginning of our melt season. That's really when the amount of water that we're going to have available in spring and summer is determined. And we're predicting that based off of the surface temperature from October to March, as well as the moisture convergence during that time. And we have tested this with a lot of different variables. We actually were able to find we could basically reduce our dimension space just to these two, and it works very well. So just to convince you of that, this is a validation plot where if we look at the data that we removed from the training set to use for testing, we can compare our testing data on the horizontal axis with the predicted data from our Gaussian process model on the vertical axis, and we see that those two kind of are very close to each other. When you fit a linear regression to these points, you get a slope that is almost exactly 1, and it's a relatively large R squared. So this model seems to be working pretty darn well for the reanalysis data. But we want to see how this impacts our climate models and see if this can help us predict changes in snow water equivalent. So what we're going to do is use that model that we've just trained on ERA5 data, and we're going to use as input data the CESM2 values. So it's that F here is from ERA5, but the surface temperature and moisture convergence are from CESM2. So the way you kind of think about this, at least I think about it, is we're using the large scale processes from our GCM. That's the input of how's the temperature going to change and how is the moisture convergence going to change, and then the small scale of the ways that this actually impacts the snowpack is going to come from ERA5. So we've done that here, and what we're showing in black is when we do that and apply it to the historical simulation, and then in blue is SSP 126. And I'd like to point out that during the historical simulation, there's very little change between the CESM2 raw output in the dark line and the Gaussian process emulator in the dashed line, which is kind of a big deal because that tells us that it turns out using this Gaussian process machine learning model that was trained on ERA5 doesn't really improve our model's predictions, which I do think doesn't mean this is all worth nothing. I think that it tells us that the issues in the model's representation of the seasonal cycle of SWE and the way that SWE changes is not because of the really small scale processes of the ways that temperature and moisture convergence impact snowpack. It's actually because of the model simulation of this regional surface temperature and regional moisture convergence. And additionally, if we go out and project in the future using this low warming scenario, SSP 126, we see again that there's not that much difference between the CESM2 raw output and the machine learning model. However, if we kind of up the stakes a little bit and look at SSP 585, that is when we do see some bigger differences between the two, where the dashed line, towards 2100 there really never approaches 0, while CSM2 predicts that at that time there will basically be no snowpack if we are on the SSP 585 emission scenario. And additionally, there's a really large uncertainty on the machine learning model's prediction. So much so that if you look at the high end of the uncertainty interval all the way out at 2100, you basically can't rule out the historical level of March SWE at that point. So it shows that there really are some issues in using a model trained on historical data to project into the future. And I just want to bring us back to this figure to demonstrate how this type of model works, to remind you that when you don't have much training data, like in the space that you're looking at, you get a really large uncertainty and you get a prediction that's kind of far away from your target function. And that's really what we're happening here. Is there's in our training data basically no years where there's 0 March snowpack, but by 2100, at least CSM2 is predicting that that is very likely the case. So this machine learning model is not particularly useful for that prediction. So again, just what can we learn from this? A very good thing here is that using the Gaussian process model using the Gaussian process model prediction of historical SWE with CSM input variables, it doesn't change CSM that much. which basically means that we're able to figure out that the errors in the model's prediction of historical climate change is really linked to the prediction of surface temperature and moisture convergence. So it's, even though it didn't work that well for predicting into the future, it's not all useless. We have that conclusion to draw, which is fairly nice. So with that, I will lead into kind of the final slide of my presentation and bring us back to those goals that I set out in the beginning, which the first of which is trying to think about how is SWE in the Mountain West impacted by climate change. And as one would expect, climate change causes snowpack decrease, which we find is the case even if there's no change in precipitation. And then the second part of what part of the model physics is responsible for errors in SWE predictions. And as we just said, it's really because the spread in the GCM simulation, like the issues with these GCM simulations of SWE is attributable to their simulation of surface temperature and moisture convergence. And they actually appear to be doing relatively well, or at least consistent with reanalysis when it comes to those really fine scale processes that determine the snowpack. And I just want to mention some future work that we're planning on doing on this topic, because there's a lot of work to be done, and it will largely include using a perturbed parameter ensemble to really try to dig into a little further about what aspects of our models are really modulating snow water equivalent in this region. So with that, thank you for listening. I'm happy to answer your questions.
Couldn't you train your GP model over the entire seasonal cycle so that you could sample states with no snowpack?
Great question. It's something we tried. The issue is snow water equivalent. It's a cumulative value. Like the snow that falls in October is still there in March, which means that you kind of you need to train your March value on not just the precipitation in March, but also the precipitation in October, November, January, February, all of those. And so that's where I guess in that sense, it kind of is still capturing that. And we have tried training other months, and like you can basically do the same thing for February or January, and it also works relatively well, but you do have to do it kind of this 1 month at a time thing. Once you get into the early months where you're basically like, if you wanted to predict October, it really doesn't work that well, because the main thing in your training set is like, did it snow early this year? Like there's just a lot of variance to that. And you're then training your model on only one data point per year. Whereas we're doing it now, we're training on, was it 5 data points per year? So that just gives you more degrees of freedom, which gives you more model skill.
I guess this is more an advertisement and a suggestion is that you may or may not be aware, we've introduced this capability to representative hill slopes within CLM, and it's available now in the latest version. And that allows you to sort of represent basically mountainous terrain within a grid cell sort of quasi-realistically. So you're actually doing downscaling within the grid cell for temperature, precipitation, and also aspects like you can do slope and aspect impacts. And so I think it's what we're seeing is a much richer representation of snowpack and how it evolves over the course of a season. And so you, for example, if you looked at those curves, it was melting out way early. I think you would, well, in this, there would be like 16 different elements within a grid cell, and some of them would be retaining snow into June, and some of them are melting out early. And I'm not sure what the mean looks like. So if you're going to go down this route of perturbed parameter, you may want to consider like also kind of testing out this new configuration, which I think is going to be hopefully like more interesting and kind of get away from the big problem in the mountainous regions.
Yeah, thank you. I was not aware of that, and I will definitely look into it and maybe send you an email about it. Yeah.
Okay, let's move to our next speaker, Jerry Neal.
One way to get up here. Okay, thanks everybody. And I want to acknowledge my collaborators on this work. And I also want to give a shout out to Warren Washington, who's actually joining this session virtually from his home in Denver. So welcome Warren to this session. So I'm going to be talking about the IPO here, and the IPO is the largest observed source of decadal variability in the Pacific Ocean. Has widespread teleconnections. One depiction of this is this plot here in the upper right. This is the second EUF of low-pass filtered observed SSTs. And in this sign configuration, this is a positive phase of the IPO with above normal SSTs in the tropical Pacific. And if you look at the PC time series of this EOF, which is sometimes used as an index of the IPO, you can see the IPO is negative from the late 40s to the late 70s, positive from the late 70s to the late 90s, negatives in the early 2000s. And this is why you can see that if you calculate trends from the late 70s to the 20 teens, you get a negative trend in the tropical Pacific. I've got an editorial comment about that, which I may add later if we have time. But is the IPO a physical phenomenon? Is it a thing, or is it some manifestation of ensomodulation? This discussion has been kind of going on in the literature for quite some time. I'm going to argue that there's evidence from long model control runs that suggests that it is a physical phenomenon. And the key elements of this are off-equatorial Western Pacific Ocean heat content, and that ENSO events can provide a trigger for transitions in the sign of the IPO. So in other words, interannual timescale variability can provide a trigger to change things on longer timescales, on decadal timescales. So the evidence we have from this is we looked at the long 1800-year control run from CESM1, and we came up with about 50 cases of IPO transitions from negative to positive and positive to negative. And if you look at these plots here in the upper right, you can see these are the composites. The blue line is the IPO index here going from negative to positive. And these two lines here are off-equatorial Western Pacific heat content that are above normal before the IPO transition. And then the heat discharges as the IPO goes from negative to positive. And going from positive to negative IPO, you can see the IPO index is positive, it goes to negative, and the off-equatorial heat content in the Western Pacific is below normal before the transition and then starts building up after. And so that kind of indicates that there is a key role for this off-equatorial heat content in the Western Pacific. And the other interesting tidbit that came out of this was that when you look at the transitions here, you're more likely to have an El Nino event transitioning from negative to positive IPO, more likely to have a La Nina event going from positive to negative IPOs. This is indicating that these ENSO events can actually possibly influence how the IPO how it transitions. So what's been happening with the off-equatorial Western Pacific heat content? If you look at this representation of what could kind of be close to observations from FOSSE, you can see that the off-equatorial heat content from the North and South Pacific boxes were pretty high here in the 70s, about the time of the 72, 73 El Nino. It started to discharge, it started to go down, the IPO went to positive. The 3-year La Nina event here in the late 90s seemed to have provided some kind of impetus for the IPO to transition from positive to negative with a buildup of off-equatorial heat content again. And we came up to a point where we were roughly back where we were in the 70s. You think, well, it's all ready to go if you accept that this is kind of a necessary but not sufficient condition for one of these transitions. And in fact, with the 2015-2016 El Nino event, you saw that the heat started being discharged. And that all seemed to kind of go according to what we thought was actually happening. But then something happened. Starting in about 2019, the off-equatorial heat content rebounded. And that didn't seem to be what we would have expected to happen with a positive phase of the IPO. The other thing that happened is if you look at this connection between tropical Pacific sea surface temperatures with the IPO and global average temperature trends, there's a well-known connection between the two, where we had this IPO in its negative phase here in the 2000s. The rate of warming was slower. When it seemed to transition to positive, we got a big increase in the rate of global warming. And when this IPO apparently went back to negative, it flattened out again. And of course, 2023 and 2024 are going to be pretty high with the big El Nino event that occurred. So what happened in 2019 and 2020? Well, the big thing that happened, or one of the big things that happened, were these unprecedented, huge bushfires in Australia. And you can see by the naked eye on satellite maps, big plumes of smoke coming off of southeastern Australia. And you see this animation of black carbon transport here. You can see that the smoke is coming across the Pacific. It's getting entrained in various synoptic systems. This is happening at about 30 south, so it's in the subtropics. There's not a lot of storms that are raining out the smoke aerosols, and a lot of them are making it all the way over off the coast of South America. So the question is, did this smoke contribute to an externally forced La Nina? And John Fasulo's paper with collaborators argued that it probably did make a major contribution. But then did this actually indicate that this was kind of a return to these negative IPO conditions? And that's what we're looking at in this work here. So we have these two sets of initialized hindcasts with two different models, CSM2 and E3SM2. Both were initialized in August 2019, run for 3 years, 30 ensemble members each. One set is run without the bushfire smoke. We're calling that the no smoke simulations. The other set is run with the observed Australian bushfire smoke emissions. That's the smoke experiments. And the two things about these experiments, setting up an initializer system prediction in this way, one is you're running initialized prediction as a sensitivity experiment, which is kind of a different way of applying initialized hindcasts. But basically, if you run these two in parallel and do the differences, smoke minus no smoke, that shows what the effects of the wildfire smoke were on that hindcast. So that's one interesting thing about this. The other is that by performing these differences of these parallel initialized experiments, they're both going along, initialized at the same point, going along at the same time. And by subtracting, doing differences, you're removing the drift identically. So you don't have to worry about a priori drift adjustment or anything else. Don's work showing the initial kind of impact of this smoke. And you can see here in October 2019, these are smoke emissions originating in southeastern Australia. And the cloud albedo at the same time, you can see these orange and red colors. That's the smoke particles are brightening the clouds. The smoke particles get over there. They form more and smaller cloud droplets, which makes the cloud brighter. Pretty well-known effect, the indirect effect. And you can see that this then through December 2019, you're still getting a lot of smoke coming across. Clouds are brighter. And of course, what's happening is the clouds get brighter, you're getting less solar to the surface. The SSTs get cooler. They're making their way up into the equatorial Eastern Pacific, and that is contributing to this La Nina onset. By February of 2020, the smoke's starting to decrease. It was pretty much done by March or April of 2020. And you're still seeing some brightening of the clouds over here in the eastern. So that was kind of the initial part of this, which was documented by John and his collaborators. I'm going to be looking at years 2 and especially year 3, because this is what ends up happening in the model simulations. So this is now from the 2 models. This is the CSM2 on the left, E3SM on the right. Smoke minus no smoke. This is the first year, and you can see that in both models, you're getting this La Nina-like kind of response in the tropical Eastern Pacific. Year 2 and year 3, the La Nina-like signal actually gets stronger. And this is fine. The other thing you can see is that there's a much bigger signal in CSM2 compared to E3SM V2. About twice the amplitude of the response in CSM2. We think this is related to the fact that the El Nino or ENSO amplitude in E3S and CSM2 is about twice the amplitude. So by giving it this kick from the wildfire smoke and initiating this La Nina response in the CSM2 compared to the E3SM2. For comparison, and this is not quite a direct comparison because this is observations from an anomaly from a climatology, but you can see that there was this 3-year kind of La Nina-like pattern. Grow and persist into year 3. Well, first thing you do is look at precipitation. I'm going to be talking about 2 sets of coupled feedbacks that probably kept this going and made it grow into year 3. They're both related to what we think could be contributing to IPO in the system. The first is that precipitation now in CSM2 compared to E3SM. Both are showing increased precipitation over the warmer water here over the maritime continent, and decreased precipitation over the western tropical Pacific. And of course, as the strong trade winds are advecting this warmer water to the west, you're building up warm water over here in the maritime continent. That's providing a moisture source for enhanced convection and precipitation. And for the observations, again, the color bar is not quite comparable, but qualitatively, you can see in observations there was reduced precipitation over the western tropical Pacific, increased over the maritime continent. So what that's doing, of course, when you have these warmer sea surface temperatures and greater precipitation, that's producing lower sea level pressure over here on the western Pacific. convection. That's strengthening the water circulation. That's strengthening the subtropical high. In both models, you can see that subtropical high is getting stronger trade winds, and you get stronger Bjerknes feedbacks, and you're off to the races, right? So you're getting this big cycle of coupled feedbacks across the Pacific involving the water circulation, Bjerknes feedbacks, increased upwelling, cooler SSTs. And the Walker circulation connection can be actually illustrated by 200 hectopascal velocity potential. Again, this is smoke minus no smoke. So the blue colors are upper level outflow. So you're getting this strong vertical motion from the increased precipitation. It's hitting the top of the troposphere and spreading out. And you're getting then stronger descent over the Pacific. That's strengthening the subtropical high. So that's a stronger rock circulation you see in both models, and of course stronger in the CESM. So that's one set of coupled feedbacks involving this large scale walk circulation, Bjerknes feedbacks, and all these things that keep the SSTs cool. The other one involves kind of an interesting set of processes in the Western Pacific. So if you remember there was negative precipitation anomalies in the Western tropical Pacific. If you put a negative convective heating anomaly in that area in an atmosphere only model and see how it responds, you see this kind of anomalous gill type response with anomalous highs to the north and the south, circulation around 15 or 20 north, anomalous westerlies here in 15 or 20 south. And of course, what this is doing, it's producing Ekman convergence at about 10 or 15 north and 10 or 15 south. Get Ekman pumping. You're pumping heat down into the off-equatorial Western Pacific, and that's building up the off-equatorial heat content. You see the deposits from the long control run. This is for negative IPO. See the same kind of response with these anomalous highs and the westerly wind anomalies to the north and the south. And you see it in both model simulations of these initialized hindcasts. So you get the anomalous westerlies to the north and the south here in CSM2 and E3SM. And that should give us buildup of off-equatorial heat content in the Western Pacific. And indeed, that's what's happening. This is ocean heat content in year 3 again. Top is CSM2. The red colors, of course, are increased heat content in the off-equatorial Western Pacific. You see it the same in E3SM2 with reduced amplitude. Stations are showing a similar kind of thing with the buildup of off-equatorial heat content in the north and the south. So that's a key element that we looked at as that's maintaining this negative phase of the IPO, at least in those composites. And there's evidence as what was happening out to year 3 in these kinds of simulations. This panel at the top here are the ones that John Fasula documented. Basically, the smoke comes across the Pacific, brightens the clouds, sea surface temperatures cool, make their way up into the eastern tropical Pacific, and Bjerknes feedback starts spreading this cooler water toward the west. And what we're looking at in this present work, getting out to years 2 and 3, is that the cooler water spreads all the way across the Pacific. You get warmer water over the maritime continent and increased precipitation that strengthens the water circulation. You get increased descent, strengthens the subtropical high. You get stronger trade winds that increases the upwelling, and you get cooler water. And this set of coupled feedbacks, if not stopped, can just go on indefinitely because there's nothing to stop it, right? So that's a way to maintain these kinds of coupled feedbacks over multiple years. The other set of coupled feedbacks involves what we saw in the Western tropical Pacific. The negative sea surface temperatures, negative precipitation anomalies produce these negative convective anomalous gill type response, which produces Ekman pumping at about 10 to 15 north and south. That pumps heat down into the subsurface ocean and primes the system once again for a transition period, right? So remember when we looked at those heat content plots at the very beginning, and it 2020, it looks like it's about ready to go again. If you think that the heat content in these off-equatorial regions have to be triggered by something like an ENSO event, you'd think that it may be ready to go. And if you think that the IPO had transitioned on its own with the 2015-2016 El Nino, and then was artificially forced back into negative IPO by this Australian wildfire smoke, maybe this 2023 El Nino event may have triggered a transition back to positive IPO. And whether or not that's happened remains to be seen. Thanks.
You mentioned that CSM2 compared to E3SM. CSM2 has a stronger El Nino, and that's why you thought it was different. I was a bit confused about which one is more right, because it looked like precipitation was more correct in CSM.
Twice the amplitude of the observations. E3SM2 is a little bit below observed amplitude. So I'd say in terms of just absolute ENSO amplitude, E3SM is probably a little closer to observations. But as with everything in these models, they don't seem to ever respond as strongly as you see in the observation. Being the CSM2, this kind of advantage of responding in this way to this kind of a forcing gives you a better signal. I think at least that's our interpretation so far.
Oh, we have an online question from Warren.
Jerry, Warren's here. Warren, you want to wave? Warren said, good job, Jerry. Of course, those are pretty wild ideas you have. So they need to be validated and evaluated.
That's what Warren always tells me. So some things never change, right? Thanks, Warren.
Good to see you. He said, good to see you, Jerry.
Okay, great. Glad you could attend virtually.
Thanks, Jerry. We're going to move on to our next speaker, Oliver Millen.
Ollie Millen. I'm a PhD candidate in the School of Meteorology at the University of Oklahoma, working with Dr. Jason Furtado. I'm going to be talking about some work that we've been doing today, looking at the role of stratosphere-troposphere coupling in a North American 2017-2018 colder outbreak. So just a bit of background into the event. So this was a really sort of impactful 8-day event, not just across the Great Plains, which is what I mainly focus on, but also the Eastern US as well. Specifically the 26th of December 2017 through to the 2nd of January 2018. And now the figure on the right-hand side here shows the 2-meter temperature anomalies from ERA 5 in the shading averaged over this 8-day period across the US, with the box there in the purple is what we previously used to define colder outbreaks in this region. And you can see that widespread across the plains, but also towards the Eastern US as well, really cold temperature anomalies. But something that was kind of, somewhat unique about this event is that it was strongly influenced by the stratosphere, not so much through sudden warming, but more stratospheric wave reflection. So just to briefly go over what stratospheric wave reflection is. So it's a phenomenon that can happen across the North Pacific. So it actually begins where you get these sort of large planetary scale waves with activity propagating vertically into the stratosphere from the troposphere. And what can happen is when it actually hits the stratosphere, rather than being absorbed like it does in a lot of cases, it actually gets reflected, kind of like a mirror. And then subsequently, the downward wave activity comes back over Canada. And then when this converges at the surface, you find that the wave pattern actually then amplifies, which is what can cause these colder outbreaks to happen. So with this study, we have a couple of objectives here. So first, to go over the evolution of the event to kind of understand it, but then second, to investigate the role of stratosphere-troposphere coupling through this method through wave reflection in sub-seasonal forecast nudging experiments. So first off, for that first objective, this is for the event evolution. So the figure on the right-hand side here shows 2-meter temperature anomalies in shading and 500 hectopascal geopotential height anomalies in contours, solid positive, dash negative, from ERA 5 at 5-day average windows from the 6th to the 10th of December 2017 in panel A, all the way through to the 31st of December 2017 to 4th of January 2018 in panel F. Now there's some pretty interesting features to notice here. So first off, you get this really sort of large scale Rossby wave train across North American domain and into the Atlantic in early to mid-December. Then you get this sort of amplification of this Alaskan ridging between the 21st and 25th of December, so going right up to before the event actually started. And subsequently, this type of weather regime, but also more West Coast weather ridging weather regime, actually tends to dominate the flow pattern during the colder outbreak itself. And so you can see that it's a pretty wavy structure in the troposphere leading to this event. And so we really want to see how does this sort of tropospheric evolution influence the stratospheric evolution before we dive into the forecasts. And so to kind of look at this, there's a reflective index from Missouri et al. 2022 that basically describes the strength of stratospheric wave reflection. So it uses the difference between the standardized 100 hectopascal meridional eddy heat flux over Siberia and Canada. So usually where you get this sort of positive reflective index associated with positive Siberian anomalies, so upward flux from Siberia, and negative Canadian anomalies, so downward fluxes over Canada, is where you can indicate this sort of up and down reflection type mechanism. And so the figure on the right-hand side here shows from ERA 5 with time. In the black line, the reflective index, then the dashed red line is the Siberian contribution, and the blue dashed line is the Canadian contribution to this index. And then the black dashed lines show our colder outbreak start and end dates. So you can see that really very highly reflective conditions through much of December, from early December through to the start of our event, with a couple of upward pulses of Siberian flux in the dashed red line there, and followed by some pretty strong negative fluxes into Canada before the start of the event. And so the question we want to ask with our forecast experiments really is, how is the reflection and its impacts represented in sort of these subseasonal forecasts? And so to do this, we do some model experiments. So we use CESM2 CAM6, so this 21-member ensemble, sort of initialized weekly with, like I said, the CAM6 atmospheric component. And we actually do nudging experiments. So the strategy for this is that we nudge in the zonal mean of the actual zonal wind and the temperature with a 6-hourly timescale. So essentially full strength at and above 100 hectopascal, and no nudging below 150 hectopascal, and then sort of a linear transition zone between those two levels to ramp up the nudging. And we do 3 different types of experiments. So the first one is the free evolution. So this is just where we don't do anything at all. The second is nudge ERA 5. So this is where we essentially apply this nudging, where we're trying to push the zonal mean stratosphere to the ERA 5, more observed evolution. And then finally, nudge CLIMO, which is where we basically nudge the stratosphere to a more damped climatological stratosphere conditions on the ERA 5 long-term mean 1991 to 2020. And so this can also then be applied to other events as well, this type of strategy, other sort of colder outbreak events that may have sort of stratospheric interactions. So first off, if we look at the 2-meter temperature anomalies between 26th of December 2017 and the 2nd of January 2018, averaged over the Great Plains, that purple box that I showed earlier, the figure on the right-hand side here shows as a function of this weekly initialization, so starting November the 27th in panel A and ending December 18th in panel D. This just shows the probability density functions across the 21 ensemble members for the forecast of this target 2-meter temperature anomaly period for the colder outbreak. So gray is the free, blue is the nudge ERA 5, red is the nudge CLIMO, and then the dashed black line shows the ERA 5 value in observation or reanalysis, I should say. So you can see that actually there's a few things to just note here. So these longest sort of sub-seasonal lead times, the nudge ERA 5 in the blue line actually tends to exhibit this sort of notable cold shift compared to this nudge CLIMO and the free simulations, where it's shifted more to the left-hand side. As you sort of go forward in time and you're getting closer to the colder outbreak, the ensemble forecasts tend to really show a more comparable outlook on that particular target 2-meter temperature anomaly period, but they all do shift colder as well. And so really the results from sort of this longest sort of sub-seasonal lead times really begs the question then, could the sub-seasonal representation of stratosphere have an impact on the reflection forecast, which then, as we know through observations, can actually impact the development of cold. So to do this, we then show similar plot in the same layout as before on the right-hand side, but this is for reflective index components during key wave activity periods. So for the reflective index in the top 3 panels there from November the 27th through to 11th of December, initializations average between the 14th to 26th of December. And then the Siberian and Canadian components, where we had those really large sort of contributions, average between the 14th to 20th of December in the middle 3 panels and the bottom 3 panels respectively. And so what we really notice is, so the Nudge Eero 5 subseasonal reflection forecast actually produced this sort of, on the longest subseasonal timescales, this sort of larger positive reflective index tail overall, and more of a shift compared to the other simulations. But also in terms of the Siberian component, interestingly, there is a modest sort of shift towards greater flux coming out of Siberia as well, and shown in that blue line. And then also, and I think this is the most notable thing, is that you can see that there is a really notable shift to the sort of stronger downward Canadian portion of the flux by that blue line. And you can especially see this in that's really sort of fatter tail in the November 27th initialization for the forecast for these sort of strong upward downward periods. And so, you know, this more accurately represented stratosphere circulation may actually result in sort of better subseasonal forecasts of these sort of downward wave response that you get in these reflection events that can actually enhance or even form these type of colder outbreaks. And so what I really want to focus on here is this November 27th, 2017 initialization for the Nudge Eero 5 experiment with that blue line with the much larger sort of response over Canada of these downward waves. And what we do is we take that particular run with our target period of the 14th to 20th of December, and we basically separate ensemble members in this run with a weak, so greater than -1, and a strong, so less than -1, downward area averaged Canadian 100 hectopascal meridional eddy heat flux standardized anomalies. And we find that for this particular run, there's 13 weak downward response members and 8 strong downward response members. And so the figures on the right-hand side here, so panel A shows basically the evolution during this run of the composite of the strong downward flux members of this meridional eddy heat flux over Canada versus the weak. And as you can imagine, since this is how we separated it, there's quite a clear difference. Obviously, the strong downward flux members have this very strong negative flux compared to the weak members, which actually come back up above 0 on average. But we also composited for these same strong and weak downward flux members the respective upward component as well during the run itself. And you can see that those that have the strongest downward response actually have this more sustained upward response before. And they're those that, you know, have a weaker downward response into Canada of this wave activity. It's more of a single pulse rather than a more sustained sort of preconditioning almost. And so what does this actually look like, you know, for these 2 different groups of ensemble members in terms of 2-meter temperature and geopotential height anomalies at 500 hectopascal? And so the figure on the right-hand side here shows the composite maps for these weak downward pulse members throughout the two-day averaging periods here in the model CSM2, CAM6, throughout the colder outbreak period itself. So again, 2-meter temperature anomalies in shading, 500 hectopascal geopotential height anomalies in contours, so solid positive dash negative as before. And you can really see that these weak downward response members actually have anomalous warmth across much of the US, which is the opposite to what happens. And this is throughout the whole of this colder outbreak period. But then if you compare this to the strong downward response members in this November 27th Nudge Eero 5, it's a very different picture. So here the hatching indicates where it's statistically significantly different from the weak pulse members in the 2-meter temperature field. So it's actually shaded where it's non-significant. So anything that's not hatched is significant, I should say. But you can see that actually throughout the colder outbreak period, these members actually show colder US temperatures and a very similar evolution to the actual colder outbreak that you see. And so this really shows that this sort of nudge to ERA 5 to a more accurate, more observed stratosphere can more readily produce this sort of stronger downward response over Canada, and is more likely to sort of bin ensemble members into that on sub-seasonal lead times. So just to really conclude, so so this event, this colder outbreak really featured the stratospheric wave reflection and sort of the development of Alaskan Ridge and West Coast ridging, which we know is can happen with stratospheric wave reflection. And we found that these sub-seasonal forecasts for nudge simulations actually show, that if you can push to an ERA 5 evolution that is more accurate of the actual evolution that happens, that you can actually get this more robust coupling at the longest lead times. And so this could really be important for sort of long leads S2S prediction of colder outbreaks in S2S models. But something that we're looking at doing is taking maybe a slightly more aggressive approach to the nudging and actually applying sort of windowing in the extratropical stratospheric circulation, but also the tropical tropospheric circulation as well, because we know that actually the MJO was reasonably active before this event as well, to kind of isolate whether one thing or another is really making the difference in this type of event, which is something we're doing now. So I think that was all I had. So yeah, I'll take any questions. Thank you.
Hi, thanks. Really interesting. I'm just wondering if you were thinking about improving the stratospheric representation. Do you think it's partly having interactive chemistry would be important, or is it really just the dynamics?
Yeah, potentially. I would imagine in maybe cases like this, it's more dynamical. Yeah, I can't really speak too much for the chemistry, but I would imagine that the dynamical aspect of it is important. I mean, cases like this have been done for where there's sudden stratospheric warmings and have shown to make a difference. But this is slightly different in the respect that it's a less long time scale response and more of a shorter time scale response. So yeah, I would imagine probably dynamical in this case.
Hi, that was a really great talk. Great to see someone else using nudging. I was curious, why did you pick 150 kilopascals as sort of your lower bound on the nudging?
Yeah, so we actually used those levels from another study as well by Kai Huang, who did some work with MJO QBO as well, and they seem to use those levels pretty successfully as well. So that's why we chose those at least, but we could definitely maybe look at other levels as well.
Ollie, let's move to our final speaker for today, Steve Yeager.
All right, so we're going to go from the stratosphere on daily time scales to the deep ocean on decadal time scales. So it's a nice illustration of the breadth and inclusivity, I think, of this working group. So this is work that I'm doing with collaborators John Robson, Hu Kim, and Nan Rosenblum. And it is relevant to the prediction question because we think that decadal Atlantic Ocean memory associated with persistent NAO buoyancy foresting is a key source of decadal prediction skill. And I'm going to just kind of walk you through some of the elements of that hypothesis. So it's pretty well established that winter NAO drives North Atlantic deep water formation. Here's the NAO in the blue line here showing this decadal upward trend from the 70s to the mid 90s. And then the green curve is the annual North Atlantic deep water formation simulated in one of these forced ocean experiments. You can see the high correlation there. When you form more North Atlantic deep water, the Labrador Sea density increases. And we see that in our forced ocean simulation. Again, the black curve is upper 1,000-meter lab sea density in our forced ocean simulation. I put on some limited observations here for comparison in the blue dotted time series. So we're doing what looks like a pretty decent job of simulating decadal changes in the Labrador Sea in these forced experiments. And these are what we're using to initialize decadal predictions with CESM. The red curve here is from our initialized decadal prediction at a lead time, I think, of years 1 through 5. And so what you can see here is we don't predict changes in lab sea density. We initialize, but we're not able to predict NAO or the formation anomalies that would give a match between red and black here. However, we are able to predict the southeastward export of those initialized North Atlantic deep water signals. And I'm showing you that by showing you time series from a box east of the Grand Banks, so southeast of the Labrador Sea. You can see that in Fosse, this multi-decadal variation in upper 1,000-meter density looks like a time-lagged response to what's going on in the lab sea, which is again associated with these NAO variations. And here's our prediction. So when we initialize those Labrador Sea anomalies, they're exported out, and that propagation is highly predictable in our 1-degree system. The ability to predict these sort of high to mid latitude density variations on the western side of the Atlantic gives us high predictability for decadal variations in thermohaline circulation strength. So I'm showing you here the gyre, this horizontal gyre circulation strength in that same box, which is again well predicted, and that's part of the overall AMOC mechanism, our changes in high latitude gyre. And associated with those gyre changes are changes in northward heat transport by the ocean that we're able to predict on these decadal timescales. And then finally, we're able to predict these changes in subpolar North Atlantic SST with a very high degree of skill. And you can see how well our Fosse matches observations for that particular quantity. So this is sort of the causal chain that we think is operating underpinning decadal predictability in the North Atlantic. But the decadal skill for impacts over land is much lower than for subpolar North Atlantic SST. And specifically, Isla wrote a really nice paper back in 2019 that showed this observed connection between low frequency North Atlantic SST, variations in North Atlantic jet latitude, and European winter precipitation, noting that it's too weak in our decadal prediction system. And so that necessitates this combined dynamical statistical prediction approach. And I just want to walk you through some of the analysis from that paper. So this is focusing on observations here. It's showing the covariability between the North Atlantic jet and Western European precipitation, which interestingly really pops out in March for low frequency periods. So this is a regression of U700 on U700 averaged over this box. And then this is the corresponding regression on March precipitation. So when you have a more northerly jet in late winter, you tend to have more precipitation over Scotland, less over Portugal. And this correlation between these quantities is very high. Correlations of order 0.8, allowing you to reconstruct U700 from observed precipitation all the way back to 1900. But the covariance is particularly pronounced on decadal timescales, where you get correlations of close to 1 between variations in the jet latitude and variations in the precipitation difference between these two boxes here. Now, this decadal variability in these quantities is closely related to AMV, and that's what's shown on this plot. So Atlantic multi-decadal variability, this mode of variability in Atlantic that we think we can predict quite well, even in low-res systems. But when you look at the actual prediction skill from the decadal prediction large ensemble for this, for say UK March precipitation, it's quite low. And so Isla came up with this approach where, you know, the SSTs that we are able to predict are used as are combined with the observed regression. So then when you do that combination, you get a really nice prediction for late winter precipitation over Western Europe. So we've been working on this project called Wishbone that is exploring these processes. And here's sort of the phenomena that we've been looking at. We start with anomalous atmospheric circulation, so NAO and other modes in the North Atlantic. These are associated with anomalous buoyancy fluxes over the subpolar North Atlantic that lead to anomalous density and ocean circulations in the subpolar North Atlantic. And then those circulations and heat and fresh water transports sort of teleconnect to lower and higher latitudes, and you can have then feedbacks from, say, high latitudes back onto NAO, or from low latitudes back onto NAO. So we think there's sort of a coupled atmosphere-ocean loop here, and clearly this resembles a wishbone. So it's a well-written proposal. And one of the key experiments that we've been doing in this project is one that we call the BSPNA experiment. And the aim is to isolate the ocean and coupled ocean atmosphere response to buoyancy driven AMOC change. And we're doing these experiments that were inspired by work that Tom Delworth and colleagues did, where a fully coupled model ensemble is run with perturbed forcing applied over the subpolar North Atlantic, corresponding to the NAO. And so what we're doing in these experiments is we're forcing over the subpolar North Atlantic region as outlined in this red box here, and we're going to impose the observed 2 sigma wintertime NAO net heat flux that we obtained from ERA5. So regressing the observed NAO index on ERA5 heat fluxes. That's what is shown in shading here. And then we apply that within a coupled model context for 10 years. So, you know, this is a strong hammer that we're applying to the coupled system for 10 consecutive years, and then we shut it off. So we're just going to hammer the North Atlantic with buoyancy forcing. We're going to get those density anomalies built up in the ocean. We're going to spin up AMOC, and then we're going to see what happens in you know, a coupled model context. So we that's the experiment. We run multiple ensemble members then to separate forced versus internal variability, where this is the forcing. And so we've done that, and Hu Kim led this nice paper that was published earlier this year. We did it in 3 separate coupled climate models. I'm showing you here the AMOC response. So years 1 through 10, again, is when we're applying the forcing, and then we allow the coupled model to respond for another 20 years. So this is the no forcing period. And what I'm showing you here is AMOC in sigma space. So we get a spin up of the lower limb of AMOC when we're applying the forcing, and then gradually this deep lower limb transport signal makes its way south and kind of fills up the high latitudes with the strengthening, overall strengthening of AMOC and influence on the North Atlantic current, which is this light northward flow here. And we see that consistent response across all these order 1 resolution models. And these are some of the broadly consistent responses that we found. And there was some evidence in the multi-model mean of AMV-like impacts. So in years 11 through 20, we see a warming of the subpolar gyre with some extension into the subtropical Atlantic. We see a northward shift of the ITCZ, and we see a weak NAO minus response. So what's new here in this talk is that we're extending this now to high resolution. So we're going to perform these BSPNA experiments in high res. So we're leveraging the IHESP configuration of CESM1, 10th degree ocean coupled to 1/4 degree atmosphere. And so far we've afforded a 7-member ensemble of these NAO plus simulations that have been run out for 20 years. So again, 10 years with forcing on, 10 years off. And we initialized these at different intervals from a high-res MIP 1950 control simulation. And we're going to do a direct comparison now between NAO plus at high res and NAO plus at low res. Quickly on the methods, I'm only considering in this presentation positive NAO forcing. I'm going to define signal as, you know, the NAO plus experiment minus the corresponding control averaged over the ensemble. That's the signal. The noise is just the standard deviation across the 7 members. And then I can compute a signal to noise, which is just the ratio. And if the signal to noise is greater than 1, then we've got an 84% confidence that the sign of the response is what it is. All right. Let me skip through this, and I just want to show you the AMOC response in high res and compare it to low res, and show you that they're fairly comparable. When we first start the forcing in years 1 through 5, we get a densification of the lower limb of AMOC, and in fact, at high latitudes, it's a wholesale densification of the AMOC stream function, not a strengthening. So you can force with NAO for 5 years and you don't strengthen AMOC at high latitudes very much. The maximum is here. The signals are really in the southward flowing lower limb, northward flowing upper limb. So it's a densification of those. And then as you progress, then that signal infiltrates lower latitudes and sort of rebounds back into the subpolar gyre with this growth in the strength of AMOC even after the forcing ends at high latitudes that persists into this fourth pentad. The overall signal in high res for AMOC is higher than low res. You can see here. The stippling here is where the signal to noise is less than 1. So we've got a more significant signal in high res. And this response that we're getting in this forced NAO experiment is very reminiscent of the sequence that we analyzed from the high-res PI control simulation when we were looking at how does multi-decadal AMOC evolve in high-res. All right, now we get to the interesting stuff. What's the surface climate response? So this is surface air temperature, and now I'm averaging over decades. So decades 1 through 10 where we're applying forcing, and 11 through 20. This is after the forcing ends. So you can clearly see in high res the development of this AMV-like SST or surface air temperature response, much weaker in low res, although we do get a warming of the subpolar North Atlantic. So there's some questions here that we don't know the answers to yet. You know, why is there a stronger surface air temperature signal? Could be due to greater heat transport efficiency or stronger coupled feedbacks in high res. And it's interesting to note that at this point, there's no specific response. There is one in high northern latitudes, but you know, we're not seeing an IPO negative response. It could be because it's not fully developed yet. Maybe we need to run this experiment longer. But a key point here is that the signal to noise is so much higher in high res than low res. So here I'm actually plotting the signal to noise ratio for surface air temperature, and you can see that development of AMV in the subpolar gyre, signal to noise ratio is greater than 2, and in low res it's substantially weaker. If we look at late winter sea level pressure response, we again see significant signal in high res and very anemic response in low res. In high res, we kind of have an East Atlantic pattern during the forcing that switches to a strong NAO minus signal after the forcing has ended. This is in response to AMOC-driven SST change. And again, just to make the point that the signal to noise ratio is much higher for late winter sea level pressure in high res, and there's almost no, you know, significant region of high signal to noise in low res. This is the U700 response, again in late winter. We're seeing, you know, some signs of a jet shift in high res that persists even after the forcing ends. We get nothing in low res. I think it's really interesting to point out that there appears to be a signal in the Southern Ocean as well in U700, and I actually forgot to point that out in the SLP. So let me, oops. No, I'm not. That seems to be going. Wow, I'm really sorry because I'm way off. Now go back to the beginning. Okay. Yeah. So what I wanted to point out was, in late winter, sea level pressure, boreal winter, seeing a significant SAM response to the full development of AMV. So this is a really interesting teleconnection. There's no sign of it in low res, and so you see that SAM response then in these stronger westerlies in high res. All right, higher signal to noise. So here's my final result. So this shift that Isla pointed out in observations that was absent in our low res decadal prediction system seems to be represented in these high res experiments, years 1 through 10. You have a slight southward shift, but also a strengthening of the jet. Here's the mean U700 jet shown in contour. So that's giving you more precipitation kind of right into this region. But then the delayed response, when AMV has fully developed, you're getting, a real shift in the jet that is giving you this dipole late winter precipitation response in high res, and there's just no sign of it in low res whatsoever. And again, these precipitation signals actually have high signal to noise, which I've never seen before in any kind of prediction experiment or any kind of ensemble experiment with low res. So to summarize, I think these perturbed forcing coupled ensembles allow for a clean study of this NAO AMOC SST impacts causal chain using equivalent forcing that circumvents any intrinsic NAO bias. We see a strong sensitivity to horizontal resolution of the coupled model response to persistent NAO heat flux, which implies an important role for small scale, generally unresolved processes in the ocean atmosphere and their interface. I showed a stronger subtropical AMOC response with greater meridional coherence in high res. And then just overall larger amplitude climate responses in surface air temperature, pressure, tropospheric winds, and precipitation, all of which have higher signal to noise in high res. And then finally, this more realistic relationship between AMV and the North Atlantic jet in late winter, strong implications for climate prediction over Western Europe. So there's still some unfinished work here, but we think that this is a really promising sort of experiment to maybe build on, because this is a relatively cheap high-res experiment, 20 years, 10 ensemble members. So it's a 200-year experiment that really can shed light on resolution sensitivity. So with that, I'll end.
I'm just wondering if you've compared the magnitudes of the sea surface temperature anomalies with the precipitation anomalies in high res. Do they kind of correspond with the relationship we see in observations?
Yeah, I'm gonna get messed up again with this thing. Oh, that's back. Oh, now I figured it out. Yeah, they do kind of correspond in magnitude, like, but I don't have your plots up. But if you look at the the sort of magnitude of the jet shift in terms of meters per second, or if we go back to SLP, this is hectopascal. So these are, this is an NAO anomaly of what, order 4 hectopascal. So it's not just that the signal to noise is higher, it's that the actual amplitude is more realistic.
Thanks, Steve. I liked the hammer experiment. I was wondering how you disentangle causation from correlation in terms of the AMOC response and the possible feedback. Because I guess there could be other mechanisms like the spin up, spin down of the subpolar gyre that could give you memory and possibly an overshoot in the subpolar gyre heat content.
I'm not sure what you mean by overshoot. Certainly there's coupled feedbacks here, right? So when we're applying the NAO forcing, we're actually getting a positive NAO response in high res. So it's like reinforcing the forcing that we're applying. And that's part of the signal that I'm showing you here. So one of the reasons why high res has a stronger SST could be due to these coupled feedbacks, or could be turbulent heat flux or radiative flux feedbacks. Is that what you're getting at?
Yeah, I guess I just wonder how you distinguish coupled feedbacks from just a purely passive ocean response. They might have long time scales.
Well, I'm mostly interested in the atmospheric response, to be honest. So I don't know how to answer that.
Okay. All right. Thanks.
All right. Thanks, Steve. And let's thank all of our speakers in this session. So I think we're out of time, which means our discussion session kind of got wrapped up in questions following the talks.
Good afternoon, everybody. I hope you had a nice coffee break and that you're all energized to this last session of the afternoon. This is a C-level session that was co-organized with Miriam Skeno, Monica Morrison, and myself, Gunther Legge. And before we start, I just want to remind everybody of our code of conduct here, that to summarize is like, just be friendly with one another and nice. I would like also to remind everybody there's still 2 posters that are up that's on the topic of sea level of this session. So I would invite everybody to go and take a look at them. And at the end of this session at 6 p.m., we're all going to, well, some of us are going to converge for happy hour at the Sanitas Brewery. So we'll welcome everybody to join us and continue the discussion that's going to take place during this session. So without further ado, I'm going to introduce our first speaker, Shena Sadai, who is going to talk to us about advancing coupled modeling to understand sea level change and inform climate actions through the courts. Forgot to say, everybody has 10 minutes for speaking, and please leave 3 minutes for questions. And when you go over, I'll give you a 2-minute warning if needed. Okay. Hi, Shena, and the floor is yours.
Hey, thank you so much. Okay, get this. Okay, thank you so much for inviting me to be part of this session. So I am currently the HITS Fellow for Litigation Relevant Science at the Union of Concerned Scientists. I work at the Science Hub for Climate Litigation. And the first part of this talk is going to be some research advances on some papers that I'm co-author on that are in peer review right now. And then the second half of the talk will be about a specific court case around sea level rise. And so, as we all know, sea level rise, just since I'm the first one in this session, is a long-term issue. It's irreversible on timescales that are meaningful for human and non-human life forms. It's accelerating over time, and it's unevenly distributed across space. So this is just some satellite altimetry data from the last couple of decades, and the IPCC AR6 Working Group 1 projections. And sea level is also an issue of climate injustice. And I think that all of us are motivated on avoiding climate injustice and working towards climate just futures. And so these are just some takeaways about the climate injustices of sea level rise from my dissertation work, which put into conversation the long-term temperature goal within the Paris Agreement and the long-term and spatially variable impact of sea level rise. And so this looked at recognition injustices. So sea level rise poses a risk of inundation, forced displacement, salinized freshwater, and all of these aspects infringe on the existence rights of human and non-human communities. It is also a distributive injustice, meaning that the impacts are inequitable with respect to emissions contributions, and both in space, looking at the Alliance of Small Island States locations, and in time, looking at intergenerational injustice. Sea level rise is also a risk under overshoot pathways because it is not reversible in the same way that global mean temperature is theoretically somewhat reversible. And it is a procedural injustice, meaning that the role of geopolitical power dynamics shapes global goals and responses. And so now I'm going to go into the research update section. So this first paper is one that was led by Natalia Gomez at McGill University in Canada, and it is looking at coupling ice sheet and GIA models. So the research gap is what influence does three-dimensional Earth structure have on Antarctic ice sheet evolution and sea level contributions? And in this work, we coupled an ice sheet model, PSU-3D, to which is a three-dimensional dynamic thermodynamic marine-based Antarctic ice sheet model, to a GIA model, CEOCON, which has three-dimensional mantle viscosity with lithospheric thickness, and it is coupled to a 3D GIA model. So this is a look at what CEOCON looks like and the viscosity structure at 120 kilometers depth. And this is just a shot from a PSU 3D simulation. And so one of the things that we're looking at here is the impact of sea level feedback. So sea level feedback means that the ice flux is sensitive to the thickness of the ice at the grounding line, which is proportional to the water depth. So a fall in sea level reduces the ice discharge across the grounding line. And this is a look at that. And then there's also the water expulsion effect. So as an ice sheet begins to shrink, the solid earth, it's sort of unloading on the solid earth beneath it, and that starts to rise up. And as a result, marine-based sectors that are freed of the ice have this water expulsion effect where water is displaced out into the global ocean, impacting coastlines at the far field. And so in a model that has a rigid earth structure, you don't really get these effects. But in a model with three-dimensional viscosity structures, you do get the sea level feedback and the water expulsion effects, which have influences on sea level contributions in both time and space. And so one thing that we found in this paper is that uplift of the solid earth due to ice unloading tends to reduce the contribution of Antarctic ice sheet to sea level rise under low warming scenarios, but it amplifies it under high warming scenarios. So the takeaway there being that reducing emissions in the near term by reducing fossil fuel emissions is really helpful, obviously, and that once we get into higher warming scenarios, we really increase risk, and we do not have any sort of like beneficial effect temporarily from the sea level feedback that we do get under the low emission scenarios that we looked at here. And because this model is capable of simulating gravitational, rotational, and earth deformational effects, we get a sense of the spatially variable sea level rise projections. And this is just one of the maps that's included in this paper under RCP 2.6 at 2150 when we account for the three-dimensional viscosity structure. So we look at a range of different viscosity structures and also different ice sheet physics and different emission scenarios in that paper. And then the second piece of research that is currently under peer review is coupling climate models to ice sheet models. And in this one, we're looking at how does ice sheet meltwater impact climate and how does meltwater perturbed climate impact ice sheet evolution. And again, this is using PSU 3D, and this is coupled to CESM 1.2. So this was the final chapter of my PhD dissertation, and I coupled the two models and with data being exchanged every model year. So the ice sheet model is passing freshwater quantities to CESM, and then temperature and precipitation, which allows the two models to co-evolve. And this is just a look at some of the surface air temperature fields under RCP 8.5 and RCP 4.5. And so the net effect of the meltwater forcing is a delay in global mean surface temperature rise. And that is, of course, spatially variable. And we have more of a cooling signal in the Southern Ocean and a warming signal in the North Atlantic. But the net effect is a delay in global mean surface temperature rise. And Yue Dong did an amazing radiative feedback analysis that's included in this paper. I won't go more into the details, but the net effect of that delay in global mean surface temperature rise is a delay in ice sheet contribution. And so we have lower sea level contributions in the simulations where we've coupled the two models together than in simulations where there is no freshwater forcing, or in simulations where these models are just coupled in one direction. So the ice sheet model giving freshwater quantities to CESM. And in this paper, we also went a step forward. And in addition to having the climate and ice sheet model be co-evolving on an annual basis, we also took the results of the ice sheet model simulations and fed those into Natalia's GIA model. And then we were able to develop these maps of the spatially variable sea level rise projections. And this is RCP 8.5 under 2200. And this shows that regionally experienced sea level rise can be up to 0.9 meters higher than the global average. So these coupled modeling advances are really beneficial. And I'm really very pleased to hear of all of the updates to the ice sheets within CESM that are coming in newer releases. And so now I'm going to switch to talking about climate litigation, which relies on scientific research. And so climate litigation has really been ramping up, especially in the last decade, and there are cases that are happening all over the world. The trends in litigation within the world more broadly are often around rights-based litigation, so showing that insufficient climate mitigation action violates plaintiffs' rights to life, food, water, liberty, cultural heritage. There's also cases that have been brought around domestic policy enforcement, mitigation action like Paris Agreement compliance, and then within the United States, we see a lot of cases about corporate liability, responsibility, and things like that. The case of the Torres Strait 8, which was one of those ones about rights-based legislation, and this was a win that came about in September 2022. I encourage you all to read up on that case. It's a really important one. But the case that I want to mainly talk to you about today is the International Tribunal for the Law of the Sea. And so this case was initiated in December of 2022 when the Commission of Small Island States on Climate Change and International Law submitted a request to the International Tribunal for the Law of the Sea to issue an advisory opinion. And what they asked the court to weigh in on was what are the specific obligations of state parties to the United Nations Convention of the Law of the Sea to prevent, reduce, and control pollution of the marine environment relating to climate change? And what are state obligations to protect and preserve the marine environment? And in particular, COSIS notes here to protect and preserve the marine environment from the detrimental effects of sea level rise, ocean warming, and ocean acidification. So legal briefs were submitted in this case in the summer of 2023. I worked directly on this case, and I helped co-write the legal briefs that were submitted by the nations of Sierra Leone and Mozambique. And oral arguments were then heard in this case in September 2023, and the court just issued its advisory opinion this past May, just a couple weeks ago. And so a few things that were notable from the advisory opinion that ITLOS gave was that anthropogenic greenhouse gas emissions do constitute pollution of the marine environment, and that obligations of state parties under the Paris Agreement are not sufficient to meet state obligations under UNCLOS. So if a state is doing everything that they are required to do under the Paris Agreement, that does not mean that they've met all of their obligations under the Convention of the Law of the Sea. And all states need to participate in mitigation action, but those with the most resources need to do more. So that's the ITLOS is saying that they are affirming common but differentiated responsibilities. And due to the irreversible impacts, the precautionary principle must prevail, and states need to enact national policy and particularly need to regulate private actors. So the fossil fuel industry would fall under that. And so science, sea level science informed this case. And within the legal briefs, states could submit all different types of science. And so they rely heavily on the IPCC, but they also have other peer-reviewed research that's particularly relevant to that specific location. But when the court, ITLOS, released their advisory opinion, they cited within the AO just scientific evidence from the IPCC because it is considered international consensus science. And a few of the things that they cited were AR6 Working Group 1, noting that greenhouse gas pollution drives climate impacts, including sea level, what the current magnitude of sea level is, the fact that it's irreversible over centuries to millennia, and noting thermal expansion and ice loss as drivers. And then in Working Group 2, they also cited the existential threat to island nations, and they also cited from SROC some of the particular impacts of sea level rise. And just to conclude here.
1 minute.
Yes. Just to conclude here, some sea level modeling advances that are needed are being able to capture those ice, ocean, climate, and solid earth interactions by coupling both marine-based ice sheets, but also 3D GIA models. Having model simulations and analysis that aid climate attribution. And in particular, I want to note for climate intervention researchers, as I said in the workshop a few weeks back, really coming up with ways to do attribution of both CI and anthropogenic forcing. And then just to skip ahead here, sea level rise researchers can help advance climate litigation. There's going to be a lot of cases that'll come out in relation to the advisory opinion, and you can lend your expertise in a variety of ways. You can also help fill current research gaps, and the Wentz et al. Paper in Earth's Future from 2022 notes specific research gaps that climate researchers can fill. So thank you so much for your time.
Thanks. We have time for a couple of questions.
Hi, thank you very much. It was a nice talk. This is not my area of expertise at all, so I'm just going to ask a dumb question. Was the ITLOS advisory opinion legally binding in any way, or are there repercussions if people don't do what they suggest they should be doing?
Yeah, that's a really great question. So the advisory opinions themselves are not legally binding. They are giving broader advice to the international community, and then litigators will bring cases with the AO guiding that new litigation.
And I'd like to remind everybody that there's no dumb question. Not here.
Yeah, there's no dumb question. That was a great question.
Anybody online?
You can also feel free to reach out to me after with questions.
I was just curious, you mentioned you were excited in this line of work about some of the upcoming advances in ice sheet modeling expected in newer generations of Earth system models. I was just curious specifically what features you were thinking of there.
I am specifically thinking of dynamic marine-based ice sheets and specifically interactive Antarctic ice sheets. My entire PhD work, in addition to the climate justice and geopolitics piece, was on doing freshwater forcing experiments with an Antarctic ice sheet model, feeding that meltwater into CESM. And then my last chapter was doing that dynamic, that coupling between an external ice sheet model and CESM. But I would love to not have to do that anymore. So I'm really, really excited for there to be just like fully dynamic marine-based Antarctic ice sheet model and a fully dynamic Greenland model just incorporated into Earth system models. I'm really looking forward to that.
All right, thanks a lot, Shanna. And we're going to move to our next speaker, Ian Miller. And he's going to talk to us about applying sea level rise models to coastal management, a case study from Puget Sound in Washington State. So, hi, Ian, go ahead.
Hey, all right. Thank you, Gunter. Can you hear me okay?
Yes.
All right, and I've got my slides. Okay. Well, thank you for having me. I'm Ian Miller, and I'm a coastal hazard specialist with Washington Sea Grant. Nice to have the opportunity to present remotely. I'm sitting in Port Angeles, Washington, about 3 hours from Seattle. I focus on coastal Washington in my work, and what I'm going to focus on today is an analysis that I was part of completing in 2022 that attempted to quantitatively assess sea level rise vulnerability in Puget Sound using GIS-based tools and data. And our study for the area is Puget Sound. I'm guessing many of you are familiar with Puget Sound. It is an estuary of national significance in the United States, home to about 3.5 million people. And this particular project was funded by dollars set aside by EPA to support ecosystem restoration in Puget Sound. So I think it provides an interesting example of the application of sea level rise projections in a management context. And from the standpoint of trying to understand and plan for the impacts of sea level rise, Puget Sound is a particularly complex coastal region, again, as many of you probably know, with significant ecological value, hopefully sort of expressed by these pictures of nice sort of coastal habitats, considerable coastal urban development. Seattle is a prime example of that. And sort of existing impacts associated with hazards like coastal flooding and erosion. And in Puget Sound, as is the case along much of the world's coastlines, sea level is rising. And what you're seeing on the screen here is sort of a Washington-specific observed sea level pattern. And projections suggest a high likelihood that current rates will accelerate in our lifetimes. So there's considerable interest in this area for planning for the impacts of sea level rise as it exacerbates coastal flooding and coastal erosion and other influences and impacts infrastructure, natural assets in Puget Sound, and the region's cultural values. So the fundamental goal of our project was to evaluate and rank the vulnerability of over 110,000 coastal parcels in order to inform things like restoration, land use and hazard planning that occurs in Puget Sound at a variety of governmental scales, tribes, counties, cities, for example. And so the idea of assessing vulnerability to any number of stressors is nothing new. And climate-related vulnerability analysis, some of you probably have been involved in processes like these, have been around for quite a while, typically leveraging these kind of like stakeholder expertise in workshop settings kind of environments. That's what the pictures are trying to communicate here. The limitations of this approach, though, led us to want to try to develop this quantitative data-driven approach that could be applied at regional scales. So we adopted this framework. Many of you are probably familiar with this framework. It's derived from approaches published over 20 years ago at this point by the IPCC, and that forms the basis for many vulnerability assessments, but it also provides a basis for sort of thinking about this quantitatively. So really sort of what we're trying to sort of quantitatively assess here is exposure to hazards like flooding and erosion, but coupling it with some assessment of sensitivity, which is intended to get at the sort of values in the places exposed to those hazards, and then modified potentially by social characteristics or individual characteristics associated with this idea of adaptive capacity. So just to kind of hammer on this idea a little bit more, and hopefully provide some insight about why this approach is so valuable from a management standpoint. It may help to sort of look at the results of the progenitor of this Puget Sound wide project, which focused on a relatively small area on the Dungeness River Delta in Washington State. This is a small river delta, but developed, and like a lot of low-lying areas around the globe, is considered to be highly vulnerable to sea level rise associated with flooding. And the idea behind this assessment approach kind of allows us to think about moving behind this view of sort of a traditional way of thinking about sea level rise impacts on the landscape, this kind of inundation map, which we generate from projections, which tells you where flooding is expected. And when we link that with other data that allows us to assess this kind of sensitivity component, it allows us to sort of move towards this type of map. And this is, in this case, sort of a ranked parcel map in which we really see certain parcels pop out as being vulnerable because of the particular characteristics of either their exposure or what's on the landscape, things like buildings, roads, infrastructure, potentially habitat impacts, things of that kind. And of course, a key input into this type of assessment is sea level rise projections. And as we obviously want to be able to kind of appropriately capture the possibility of future impacts, while at the same time capture the discrepancies between different parts of the landscape. In this case, for the Puget Sound project, we drew upon our 4 sea level rise scenarios from a locally modified version of Bob Kopp's 2013 probabilistic framework. I've sort of got the magnitudes listed here for the sort of time frames and probabilities that we focused on for this assessment. So this is really where that kind of sea level rise science really injects itself critically into processes like this. So my intent wasn't to dwell on our results because the focus is on, sort of this injection of sea level rise science into these management domains, but I did want to focus on a couple of things. And I really wanted to highlight two things that I think help to illustrate the value of this kind of process from a decision-making standpoint. So first thing is that we find that about half of our most vulnerable parcels in Puget Sound are clustered on large deltas. And what you're seeing here is this kind of big scaled out map of Puget Sound. I'm guessing you may be able to hardly be able to see it, with the parcels colored, deeper colors being higher vulnerability, sort of the softer colors being, or cooler colors being lower vulnerability. And we've got our highest 10% highlighted in blue. So you may be able to see those popped out here. And so you see those clusters on some of the large river deltas in Puget Sound. Not a surprise, given sort of the known vulnerabilities associated with those kind of landscapes. But what we also see is a considerable distribution around the remainder of the landscape. This is kind of a typically steep-sided, steep-sloped coastal environment. So places that we may not sort of intuitively understand vulnerability, we see it pop out in this kind of assessment. The second thing I wanted to highlight here is to sort of reiterate this idea that this kind of assessment really allows us to hone into where the problem places are, with the idea that we can then more efficiently direct management resources, whatever that may mean, whether it be policy, whether it be outreach effort, whatever it could be. And our results here suggest that a relatively small number of parcels, so this is a kind of a pie chart distribution of our results for all 110,000 parcels. And what I've pulled out is the small fraction, about 4,000 parcels, something like 2.8%, that fall into the highest quantile of the scores. And so what we think this really highlights is that a relatively small number of, a small amount of effort in Puget Sound directed towards a relatively small number of parcels really buys us a lot of resilience in this particular environment, which is a kind of a hopeful message we feel like derived from this kind of analysis. So I decided to end here just by putting up some of our key project documentation, just in case anyone has an interest in pursuing anything further. Project results, reports, we published a paper examining some of the results and assumptions. And we had an associated sort of social science effort that created a sea level rise specific social vulnerability index that some of you may find interesting. But with that, I'll sort of see if there's any questions and look forward to it.
Thank you, Ian. Any questions in the room or online? You can ask a question.
Hi, Ian. Thank you very much for that really interesting talk. So you cut out a little bit when you were talking about the, sorry, we had a bit of technical difficulty, but I'm just wondering if you can expand on when you were doing the vulnerability study, the characterization of sensitivity, because one of the things that you said was that allows for an appropriate treatment of the values that exists in the location that you're doing the assessment for. So I'm just wondering if you could maybe say a little bit more about that component of that way of doing the quantitative analysis. Thanks.
Yeah, so hopefully I didn't say that it allows for an appropriate assessment of values. It allows for an assessment of values. In our case, we had two elements. We had a infrastructure focused element, fairly traditional, like what are the buildings on the landscape, roads. In our case, we also incorporated data that we had that showed agricultural uses, which are particularly important in some of the low-lying deltas in Puget Sound. And then we had a separate what we call the habitat sensitivity analysis, which we felt like was kind of unique, basically in which we were able to use NOAA's marsh migration layer, which is a publicly available data set that they have generated to evaluate where existing coastal habitats may be squeezed by interaction with either features like dikes and levees and riprap shoreline defenses, or steep slopes. So we had these kind of side-by-side infrastructure assessment, habitat assessment that we coupled to create an overall sensitivity score.
Okay, thank you very much.
One more question coming. Go ahead, Peter.
Excuse me. So your observational record showed that sea level rise had been going up since 1940. So is that due mostly just to the water temperature increasing, or is subsidence in the land a significant factor?
Yeah, thank you. I should have clarified. So that particular record that I showed you is derived from tide gauges, but with land movement removed. So, you know, I think that that provides us with the best insight that we have about what the ocean is doing. You know, Puget Sound, near coastal ocean in Washington State is doing. Now, what drives that in particular, I don't have a great sense for. I'm hoping that some of the clever people in the room can help sort that out. But I assume that it has, you know, sort of like roughly equal components of thermosteric process and you know, additional mass, sort of equivalent to the global. But yeah, the land component is removed from that observational data set that you saw there.
Well, going back to the sensitivity question, I wondered if there is a possibility in the future for a human cultural aspect to the sensitivity. How much do people value a piece of land for cultural reasons?
Yeah, so you know, we in this particular approach, which was Puget Sound wide, we limited ourselves to publicly available data sets that were regional in scope. And so that's kind of a very limited sort of data set, although obviously there are a number of additional values that are not captured in this kind of like GIS-based approach, mostly because we don't have data for that. But certainly in Washington in particular and other parts of the world, the cultural values associated with the landscape are considerable. In our particular case, in our neck of the woods, some of that is associated with tribes, you know, that have sort of been on the landscape here since time immemorial and have, you know, deep relationships with the landscape in ways that, you know, GIS can't capture essentially. So we have to get at those kind of values in other ways typically. So can we envision a day in which we can incorporate that kind of information? Conceivably, but it's a long way off to having those kinds of data sets available to us.
Thanks a lot, Ian. Let's move on to our next speaker, Ricardo Riva. And he's going to talk about challenges in coastal sea level prediction that cater to secular scales and the need for coupled modeling of ice-ocean solid-earth interactions. Go ahead, Ricardo.
Yeah, thank you. Can you hear me? Welcome everyone from rainy Holland. And you will see that I've just slightly adjusted the title of my presentation. The coastal, actually, I meant more near field, ice sheet near field, sea level prediction, and I guess the decadal scale was also a bit optimistic. So now I reformulated to centennial scale that makes it's more suited to the ice sheet problem. And I would like to thank my co-authors, Karen Simon and Taco Brursen. Karen was at the time in Delft. So let me see, this is not, switching. So I will just have a quick 2 words, but it was already discussed in the previous presentation about the coupling, solid earth, especially component. And I will show then 3 examples, one from Greenland, from literature, one from Hudson Bay. And the last part is what we did ourselves about the Cordillera ice sheet retreat and transinterology there. So very quickly about solid earth ice sheet ocean coupling, I won't repeat what has been said already, but apart from Antarctica in general, the big component is the solid earth feedback is that if you load the surface of the earth, then the surface subsides. And then if you remove the load, it uplifts again. And this has a large impact on the surface mass balance of the ice sheet through the elevation feedback. And however, next to this elastic response, there is also a viscoelastic response. So like the mantle can flow. So if you leave a loaded ice sheet there for thousands of years, then there is an additional movement of the mantle material. And this isostatic response is modeled in different ways in the community, like locally, regionally, of like Natalia Gomez and co-author did this globally. What I'm showing here is just those old one of the first paper of decoupling. And this has been shown to have a large effect, as we said before, on marine ice sheets. So especially the community is focused on Antarctica. So I was wondering, what about other regions than Antarctica? And then what about Greenland? Well, in Greenland, there was a study by Khan and co-author in 2020 when they looked at the 3 major outer glaciers. And here I'm showing result for the 2 where this effect is important. You see they collected time series of mass change from the end of the Little Ice Age, like about the peaked 1880 as a starting date. And then you see that there's cartoon in the side here, then the grounding line really retreated by tens of kilometers over those 130-year time span. So what is the solidar response of that, or what is sea level change induced by the solidar response of that? And then if you look at this about, I hope you see my arrow, is about 3 meters at the grounding line for Jakobshavn, and almost 5 meters at Kangerlussuaq. And while those are big numbers, rates is average rates of sea level drop by 2 to 4 millimeter, 2 to 4 centimeters per year. And the reason I'm showing this is that actually the interesting thing is that what about the viscous response of the solid earth? So this low component, and then it really depends on the local properties of the mantle. Then for Jakobshavn, which is more stiffer mantle and standard layering, it's very little effect. This is in centimeters, so it's really like a fraction of the total signal. Whereas for Kangerlussuaq, is almost 2 meters. So it's actually, that's almost 40% of the total signal. This is because in this region here, it's really expected to be low viscosity, fast mantle response due to the presence of a former outspot, mantle outspot. However, for Greenland case, the author has said they don't expect a big effect on the stability because of the geometry of these outer glaciers. So it's an important effect for the modeler, but maybe not that relevant for like at least the short-term stability of the Greenland ice sheet. And then if you go back to other regions, then what about the Laurentide? It was a very nice paper by Helian and co-authors in 2021 in JGR. And then they studied the northern hemispheric ice sheets. So again, something else than Antarctica. And what they showed is what you see in this plot here is that when you compare the effect of this ice volume over the old glacial cycle of a rigid Earth, non-deformable Earth, and actually the forming Earth, then you see actually what they saw is that the solidar feedback, this elevation feedback is positive both in the melt and the grow phase. So the ice sheet actually melts more and grows more if you can adjust the elevation. However, when you have with or without, whether you include or not, a sea level response, which was the object of my talk here, is a very tiny difference. You see between the blue and red line is a very tiny difference down here, for example. But however, how tiny it is if you zoom in on the geometry of the ice sheets around this 80 kilo years ago, and you compare, you see that actually within a few centuries, the model without sea level feedback that misses the actual stabilizing effect retreats much more than the model which includes the sea level feedback. So that again is something that it confirms that it's not only Antarctica, but of course it happens in most marine ice sheet likely. But again, however, it's if now we wonder what about the properties that Earth properties that cause this effect, and then if we change the response of the mantle, if we change the viscosity of the model, then the response can be actually quite different. So this tiny effect here that go to retreat, that actually happens for a certain value of viscosity, but it might not happen for every case. And then the problem is we don't know what the viscosity is in fact, actually. And then to go towards the next, the last part of my talk, when I show what result we did, to make the story even more complicated about if you want to get those sea level response properly, is that what are the mechanical properties of the mantle, of the upper mantle. And then most of the GI model use linear rheologies. So linear means that linear dependent on stress changes. So if you double the stress change, you double the speed of the response. However, laboratory experiment, they show that much of the rocks in the upper mantle are probably responding non-linearly, which means that again, if you double viscosity, for example, you quadruple the response of the solid earth, and that will also be discussed tomorrow in the land ice session. And however, there is also another category of class of models. It's called the Burgers models. They are still linear, so they're kind of easier to implement and to apply. But they also show some transient effect, because the effect of the nonlinear models is if you change the stress, you locally make the mantle softer, and you can reduce, relax faster. And that's with the Burgers model. And what's showed in this plot here is the time response. You have to measure, this is viscosity. So low viscosity means fast flow. So if you have this Burgers model, the colored ones, then you can have a quick, fast response. And then there is a transition zone between one, depending on the parameters, between, let's say, 1 and 1,000 years, depending on the model. And then they converge the long-term viscosity we know from the classical J models that most people are using. Also the classical parameters people put now in the various LRA models. And what does that on the sea level change? We look at the Cordillera sheet, that the very quick retreat about 14,000 years ago. And there is the southwest margin, which was, again, Joe discussed the region, actually, this object of the previous talk. There are quite a few very good sea level data, a collection of data, and I'm going to concentrate on those two northern sites in the Strait of Georgia. And these results were published 2 years ago in JGR. And what you see here is what happens when you have these different Earth model properties that, let's see, we start with the data, like the red light, I hope that you see in the room well enough. The red symbols are terrestrial limiting data, so sea level should be lower than that. Then the blue symbol are marine limiting data, so sea level should be higher than that. And then there is also a bunch of index points, sea level index point, the gray points, and then sea level should be exactly that. And then you see that none of the model fits this delay. They're all too slow, but there are some models that actually do have a steeper curve here. And if you then remove the Maxwell model, so remove the gray line, take this as a reference, and we show relative reference with respect to this gray line, then what showing the bottom line figures, then you see that this is a bunch of models we tried with different parameters that they do fit this actual behavior quite well at both sides. But none of them fits this very big sea level drop at the beginning. That's likely because this model was using a standard Laurentide type of viscosity values, but actually when you are here in Cascadia, it's a subduction zone. So there is reason to believe that the local viscosity will be much lower. So the local mantle will react faster. And if you then adjust the viscosity to a more realistic values for the region, specific region, then indeed we see that we do match this 200 meters drop in over those since this LGM, let's say, since at least 14K. And then it's again, even the Maxwell model fits that, but then again, the story doesn't change the fact that the slope here is not sharp enough. So we need this very quick drop in sea level, and that we can only obtain when, sorry, I lost my mouse. Yeah, that we can obtain again by using this more complex rheological model. And this brings me to my conclusion that for modeling implication that for sea level coastal near field sea level, that sea level change action margin is really sensitive to local solid earth rheologies. So it's not even just the viscosity structure, but even the kind of how does this viscosity react to stress changes. So then would induce as a consequence means that if the solid earth response is too simple, that the ice sheet models could be biased, because especially the marine ones, because then the sea level feedback is really important and can have a lot of effects that we saw also in the first presentation. So my final point here would be that since the community now is moving towards coupling ice sheet and oceans more and more, I would argue that also the solid earth component should not be forgotten, and should not be assumed that if there is some isostasy that will be good, then actually we really need to tune our models to the local region, and even consider different solid earth response. Thank you.
Thanks. We have a time for a couple of questions for Ricardo. Questions? Is there any questions online? So thank you so much. And we're going to move to our next speaker, Yingli Zhu. And he is going to tell us about internal sea level variability along the US East Coast. And actually just stay here. You don't need to like, okay. This is to advance, this is to return, and this is a pointer you can point at the screen. And it will
Okay, today I'm gonna present our work on interannual sea level variability along the US East Coast. This work is done in collaboration with Wei-Ching, Mike, and Sonic. It has been well known that coastal sea level can be driven by both local forcings along the coast and remote forcings from the open ocean. Local forcings include local sea level pressure, wind stress, and river input. Remote forcings include the Rossby waves and western boundary current and sea level signals from high latitude. So the questions are, what are the relative contributions of local and remote forcing to coastal sea level? The second question is the role of local remote forcing changing with the time? To answer the two questions, we use observation and reanalysis data. The observed sea level comes from tide gauges. We further separated the tide gauges into 3 regions based on the locations and the sea level signal similarity. The locations are from south to north, South Atlantic Bight, Mid-Atlantic Bight, and Gulf of Maine. The method we use are analytical models and statistic models. For the local forcings, the sea level response to sea level pressure are approximated by inverse barometer effect, with the high sea level pressure corresponding to low sea level, and the low sea level pressure corresponding to high sea level. The wind effect is approximated by this barotropic model, driven by alongshore wind stress. River input actually are fresh water that can be carried along by a coastal current, reaching sea level along the coast. For the remote forcing, we use a simplified dynamic model developed by Minobi in 2017. As shown by the diagram, the coastal sea level along the western boundary can be affected by sea level signals from high latitude in terms of coastal waves, and also has impact from the open ocean forcing from the Rossby waves. These Rossby waves can propagate westward to affect western boundary current and the coastal sea level. These sea level anomalies then propagate southward as coastal waves. In addition to western boundary, we know that the Rossby wave can change the boundary current, but other factors such as wind stress curve can change western boundary current. So we need to take into account that effect by using this regression model. With this method, we can assess the contributions from local forcing and remote forcings. This figure shows the contribution from local forcings. Upper panel shows the correlation between the locally driven sea level and observation. The lower panel shows the explained variance by local forcings. We can see the sea level pressure are more important in the Mid-Atlantic Bight and Gulf of Maine. Longshore wind stress are important along the entire coast, but the river runoff has played a relatively small role here. Now we move on to the contribution from remote forcing. This figure shows the contribution from high latitude forcings. The blue line shows the mean coastal sea level driven by the high latitude forcing. We can see that in the southern, the black line shows the observation. We can see that the high latitude forcing are not highly correlated with the observation in the southern Atlantic bight, but it is important in the mid-Atlantic bight and the Gulf of Maine. As to the Rossby waves, the blue line shows the Rossby wave-driven coastal sea level. The Rossby wave-driven sea level are only important in the South Atlantic bight. They play a relatively small role in the northeast coastal region. At last, we need to examine the effect of Gulf Stream. We use altimetry data to derive Gulf Stream properties, and we further separate the Gulf Stream into upstream part and the downstream part. In the upstream part, we did the composite analysis of sea level anomaly across the Gulf Stream. We find that, as shown by the middle figure, the strength of Gulf Stream is important for the coastal sea level change, but the zonal movement of Gulf Stream did not suggest a significant role of the zonal movement. As the Gulf Stream moves northeastward, leaves the Cape Hatteras, the strength of Gulf Stream is no longer an important factor, but we found that the meridional location of the Gulf Stream can be an important factor for the coastal sea level along the southeast coast, which is related to the change of the large-scale circulation. We did an UF analysis to the sea level and ocean heat content, as shown by the left and the right side figures. The principal component of the UF analysis suggests that they are highly correlated with the meridional location movement. So the meridional movement of the Gulf Stream can affect the southeast coastal sea level through the change of the large-scale circulation. The next question we want to answer is whether the rule of local or remote forcing can change with time. So we use a longer time series to examine the contribution from local forcing. This figure shows the contribution from local forcing over 31-year moving window. Upper to the lower panel correspond to 3 regions from south to north. We also examine the contribution over 4 seasons. I want to draw your attention to the summertime and the northeast coastal region. The contribution from sea level pressure has increased significantly in recent 30 years, as shown by the blue lines. But the change of wind, in fact, did not change too much, as shown by the red line. So this sea level pressure change can be related to climate mode. So our further analysis suggests that the NAO has a very significant role in the change of the sea level pressure. Here we use a Bayesian dynamic linear model to predict the role of NAO. As shown by the figure A, the role of NAO has increased significantly from the early 1960s to recent decades. This model has a benefit that the regression coefficient can change with time, as shown by the figure B. We noticed that before 1990s, the NAO index are more likely in the positive phase, but in recent 30 years, the NAO index are more likely in the negative phase. So what's the impact of this NAO index change? We did a composite analysis of the sea level pressure and the wind stress induced by NAO. Before 1990s, high sea level pressure anomaly appears east of US East Coast. This high sea level pressure has a negative contribution to the observed sea level. After 1990s, there's an anomalous low pressure system that has a positive contribution to the observed sea level. So the sea level pressure system change related to NAO contributed to the increased role of the sea level pressure. In summary, For the first question, local and remote forcings are the most important drivers in the Northeast and Southeast coast respectively. Ross waves, Gulf Stream strength in the upstream part, and the Gulf Stream location in the downstream are important remote forcing drivers for the coastal sea level in the Southeast region. For the second question, the role of sea level pressure in the coastal sea level along the Northeast US coast has significantly increased in recent 30 years, which is related to the summertime AAO. Okay, thank you. I'd like to take your questions.
Have time for a few questions?
I've understood that sea level intrusion on the east coast of the United States is complicated by groundwater pumping and the I forget the word subsidence of the land.
Yeah.
But you didn't seem to account for that in this. How significant is it compared to these other factors?
In this study, actually, we focus on the interannual variability. So we did consider the trend, the long-term change. So basically, the land movement related to the water pumping actually are not examined. So, but these drivers can be important for the long-term change of sea level, which is not the focus of this study.
So from what I recall, Tony Lee has a group that's been doing this with the echo adjoint method. Are you familiar with his work, and what are the trade-offs of this approach versus using something like an echo adjoint?
Oh, yes. In this work, we use a simplified analytical model. That's but in the echo adjoint model, they use more complete model results. So I think we can do the comparison between these results. That'd be interesting. And I know there's some drawback in this study, but using more complicated models can be insightful, I think.
My recollection is that he was able to draw connections between variability in the loop current in the Gulf of Mexico and the variations of the Gulf Stream off of Florida and Georgia. So yeah, it might be worth checking out to see if it's consistent with what you found.
Okay, thank you. Yeah.
Let's move on to our next speaker. Thank you so much. And our next speaker is Wei King Han, and she's going to talk about sea level extreme and compounding marine heat waves in coastal and Indonesia.
Oh, geez. I need what's a laser pointer? Yeah. Due to time limit, I'll focus on discussing this sea level extreme part and the work from these two recent publications. Global sea level rise magnified sea surface height extremes and coastal flooding in recent decade. Most studies on the extreme sea level focus on storms and high tide on daily time scales. So hexes induced by climate model variability received relatively less attention. Okay. Located at the confluence of the Indian and Pacific Oceans, Indonesia is strongly influenced by climate model variability. At interannual time scales, there are ENSO and Indian Ocean dipole. So the strong equatorial westerly wind associated with La Nina and negative phase of Indian Ocean dipole
favors increasing sea level along the Indonesian coast. On intra-seasonal time scales, strong surface wind associated with Madden-Julian oscillation can also affect sea level. So the goal of this research is to detect climate-driven hexes around the Indonesian coast and understand their causes. So in this talk, I focus on the 30-year satellite altimetry period since 1993. Okay, first we discuss the hex event using monthly data, which assesses mainly interannual and longer time scale variability. So this is the linear trend of sea surface height from 1993 to 2018 based on satellite data. So along the Indonesian coast, sea level rising rate is greater than 5 millimeters per year, which is much higher than the global mean value. So the time series from the tide gauge data at this Java coast, this is the monthly mean, shows significant variability from year to year. Okay, and blue curve is tide gauge data, and which agrees so well, very well with satellite observations at nearest location. Due to its longer record, hereafter I'll focus on discussing this satellite data. So the monthly mean maximum variability of sea level is close to 0.5 meter, which is at the lower end of the sea level anomalies at the daily time scale caused by storms and high tide in this region. So total of 15 high extreme events we detected, and 10 out of these 15 concentrate on this 8-year period from 2010 to 2017. To understand why this is the case, we performed the OGCM experiment using both RAMS and HICOM. And to understand this wind stress forcing versus buoyancy forcing effect, we performed 2 parallel experiments using RAMS. The first main one here include both surface wind stress and buoyancy forcing, and these wind stress runs isolate surface wind stress forcing. To quantify the remote forcing from the tropical Pacific, we also performed the pacemaker experiment using CESM1 with prescribed sea surface temperature anomalies in the tropical Pacific basin. Okay. So the black line shows the monthly sea level anomalies from satellite observations averaged over the entire Java coast. The red line shows the sea level anomaly from OIS for reanalysis. The blue shows from RAMS solution and purple HICOM solution. And all of this actually agree pretty well with satellite observations, but by considering both trend and variability, RAMS performs the best. So hereafter, I'll focus on the RAMS results. So this black line shows this monthly sea level anomaly from RAMS mainline solution. And this blue line shows the linear trend. And this red line shows observational-based anthropogenically reduced global mean sea level rise. Actually, the linear trend and global mean sea level rise, as we can see, very close. Okay, and the blue line shows this sea level anomaly after we remove this anthropogenic global sea level rise and this regional decadal sea level variability. And when we look at the blue line, we can see that there's no preference of this 8-year period any longer after we remove global sea level rise and decadal variability. And this result suggests that global sea level rise, that's the anthropogenic component of global sea level rise, combined with decadal sea level variability in the region, are the causes for the increased number of hex events. Okay. To quantify this component, here we produce this time series of the sea level anomaly in this region, Java coastal region, and due to only global anthropogenic sea level rise and the regional decadal variability, this is red line. The black line is only the decadal component. So the difference isolate this global sea level rise effect. As we can see, both contribute to 7 to 8 centimeters at the end of this time period. To assess the importance of surface wind stress forcing, and this black line, okay, this blue line shows the ROMS solution that forced only by surface wind stress in the Indo-Pacific basin. So the good agreement between this black and the cyan curve suggests that surface wind stress forcing is dominant cause for this sea level anomaly. Okay. To isolate the tropical Pacific forcing, we produce this sea level anomaly due to this tropical Pacific forcing from the 10-member ensemble of this Pacific pacemaker experiment. This is the blue line. And this sea level anomaly here, blue line, will track this decadal variability of the ENSO index, these two, suggesting the importance of decadal variability of ENSO, which is highly correlated with IPO. However, this sea level anomaly caused by the Pacific comes down, but the observed one actually stays up. This is due to the upward trend of this negative phase of the Indian Ocean dipole. This is, as we can see here. So the surface wind, this is equatorial westerly wind associated with this negative phase of the Indian Ocean dipole, and La Nina-like decadal ENSO variability cause equatorial economic convergence, raise sea level. And this signal propagated to the east, raising the sea level along the Indonesian coast. Meanwhile, this northwesterly wind anomaly also increases coastal economic convergence, further increases sea level. So to summarize this part, 15 hexes are detected and 2/3 concentrate in this 8-year period. Anthropogenic global sea level rise combined with surface wind anomaly associated with decadal negative IOD and ENSO raises sea level along the Indonesian coast, which increasing the frequency of the hexes event. Okay, on intra-seasonal time scale, atmospheric ISOs, okay, which are dominated by the MGO, can contribute to about 0.2 meters to the hex amplitude. So this figure, the histogram, shows the number of hex events that occurs in different months for the entire period from 1993 to 2021. The red bar, like here, shows that ISO-induced sea level anomaly dominated the hex event. The blue one shows the other component, interannual to decadal component, dominate the hex event. And apparently, you can see that during the northern spring, the boreal spring, this is red line, red bars here, ISOs dominated this low frequency variability in causing this hex event. But during winter time, and the hex is mainly induced by the interannual to decadal timescale variability, the La Nina negative dipole, and the monsoon variability. Okay. And important role played by the ISOs during northern spring is because of strong equatorial westerly wind associated with the MGO during the spring, which are driven by the strong convection in the eastern equatorial Indian Ocean that drive this strong wind compared to the weaker wind during winter time. Okay, and with this convection mainly shifted to the south, the blue line, the blue contours show the OIR representing convection. So the strong wind causes stronger, okay, coastal sea level, as we see, which is increasing the frequency and the amplitude of the hex event. So in summary, this MGOs dominate interannual climate mode in causing hexes along the Indonesian coast in boreal spring, contributing to the amplitude of the hexes by about 0.2 meters. The stronger zonal wind across equatorial Indian Ocean during spring MGOs drive stronger sea level anomaly, resulting in larger contribution to hex event compared to winter. Thank you.
Questions?
So I was curious on your estimation of the anthropogenic component. You
I know you
used
would ask that question.
you used right. So you used the global mean, right?
Yeah, global
And
mean.
now we know warm water expands more rapidly for a given amount of energy, a given amount of warming, right? Higher expansion coefficient. You're in the Java Sea. Isn't it an underestimate to say that the global mean rate of rise is the anthropogenic component because there's a pattern of rise too, right? So maybe you're being conservative in your anthropogenic contribution. Mike.
One question. Oh, here. Sorry. Actually, you asked two questions. One question is how I estimated this anthropogenic global mean sea level rise. Second one is what's the difference between global mean sea level rise and regional sea level rise in this area?
Yeah.
Excellent question. So to answer your first question, I did two methods to estimate this global mean anthropogenic induced sea level rise. And first, they have data, right? It's global mean data I get from Church et al. And also, yeah.
Tide gauge.
Get tide gauge based. And that data I times 0.9 because they said, based on IPCC, 90% of the global mean sea level rise for this period of time is due to anthropogenic. That's the first method. The second method, I used part of your work and the acceleration of sea level rise in the past 30 years, about 0.084, if I remember correctly.
Right.
Okay, using that part and then combine the acceleration and to obtain the sea level value right in there and combine with the previous ones. So the two are almost identical. Okay, the first question. Second question, I'm not sure whether I have that figure here or actually over the Indonesian area, I have a few, this one. And we analyzed CMIP6 large ensemble model experiment, and we analyzed 173 ensemble members. In these regions, you have a huge uncertainty. There's no apparent like stronger or weaker trend compared with global mean.
Right. Yeah, the altimeter record would suggest otherwise, right?
Altimeter record, yes, but only 30 years though. Yeah, but I focus on these 30 years, but we did starting from 1960.
Okay, thank you.
Good question.
We have a question online. Chris, go ahead.
Yeah, hi, thanks for the talk, Wei Cheng. At the beginning of your talk, you showed the tide gauge and altimeter comparison. And you said the correlation was very high. Was the amplitude higher at the coast in the tide gauge than the altimetry, or were they comparable?
Yeah, very good question. Yeah, very good eyes. Yes, the tide gauge values are in quite a few regions, in quite a few years or months are higher. The total standard deviation, if I recall correctly, is very close. So I was surprised when first we compared the two. Actually, the satellite data was taken at the nearest location is 18 kilometers in the southeast of that tide gauge location. And they agree very well. It's yes, tide gauge, as you mentioned, is slightly higher, but overall they agree very well.
Okay, so it's not a simple answer like, maybe these are more amplified at the coast than they are offshore. It depends.
Depends. Yeah, you're right, because you have analyzed a lot of tide gauges, but it depends on location. What we are saying in the paper, saying that the good agreement between the two in this region, indicating, first of all, the local regional, like little eddies and those effects may not be that important. Second of all, this large scale circulation dominates the dynamics in this region.
Okay.
If we
and any easy answers on whether the models capture some of that tide gauge variability any better or worse than they do the altimetry? Or is that sort of out of the scope of what you looked at?
No, actually, we use altimetry because altimetry, no, they are similar. I know what you mean. Like the best performance the model is RAMS because you provide boundary condition as using ORIS4, so you have global mean part in it. Okay, ROMS is volume conserved, but they didn't impose that volume conservation on regional model. So we have the global mean effect, but ROMS does sometimes produce a higher amplitude than the satellite data. So I can't say it's better compared with, can't say it's better than satellite compare well with the height gauge data.
Right. Okay. Thanks for the answer.
Okay, great. So in the interest of time, we're going to go to our next speaker who is joining us remotely. So we'd like to welcome Jacob Steinberg, who's going to be speaking with us about the links between coastal sea level and offshore ocean heat content change. Okay, so we can see your screen and looks good.
Excellent. Thank you, everyone. I assume you can hear me okay. My name is Jake Steinberg, and I am a research scientist at NOAA's Geophysical Fluid Dynamics Laboratory. And today I'm going to share some work that I've done with colleagues who are listed here at GFDL, as well as from Woods Hole Oceanographic Institution. And in particular, like the title of my talk says, I'm going to focus on this mechanistic link between offshore heat content change, below the surface, and coastal sea level change. So I'm including a figure here that you've probably all seen before from the recent IPCC report that just shows roughly half of the sea level change that we've observed can be attributed to ocean warming and as a result of thermal expansion. And you can see that in these light, medium blue, and dark blue filled regions that by the end of this record, you can see they comprise almost half of the sea level change, globally averaged. And so the purpose of this work is to study how regional patterns of ocean heat content change affect coastal sea level. And to do this, I am using a regional model that was developed at NOAA GFDL by colleagues who are part of this work. And this regional model, as you can see by the figure, focuses on the Northwest Atlantic and US East Coast sea level. It is unique in that it's relatively high resolution. It's a 12th degree, 75 vertical levels, and was run for a 30-year period, forced at the surface and ocean boundaries by atmosphere and ocean reanalysis products, respectively. And so like a previous talk just showed, resolving the Gulf Stream and its position is really important. So this is a figure from Ross et al. Andrew Ross is the one who led the development of this model that shows this model does a pretty good job at reproducing the position of the Gulf Stream, the latitude at which it separates, turns east, and then its latitudinal position, the extension's latitudinal position over time. That's what this time series is in the lower panel. You can see the model in red and the observations in black. And what's plotted is this index in which positive values mean the Gulf Stream moves north, and negative values mean it moves south relative to its nominal position. And so what I'm interested in doing is relating, again, coastal sea level to offshore change. And to do that, I first decompose sea level into contributions or into mass and density change contributions. So this is a common decomposition in which sea level variance can be expressed as the sum of steric sea level variance, or change really, and a mass component. So the upper row shows total sea level variance in this model, steric sea level variance that due to density change, and then in the upper right is that due to mass change, sea level change due to mass change. The lower row shows the fraction of total variance. And so you can see close to the coast on the continental shelf, a majority of sea level change is reflective of mass change. And so what I'm interested in doing is asking, where is that mass coming from, and what are the physical mechanisms that drive sea level change at the coast? So to start off at low frequencies, this is kind of what has motivated a lot of this work. I'm considering the spatial patterns of these two terms, the density-driven term and the mass-driven term. So again, manometric refers to mass and steric refers to density. And what I'm showing are over 2 6-year time periods that don't overlap. I'm showing linear trends in manometric sea level, this upper row, and steric sea level in the lower row. And so if you look at the first column over the mid-2000s, you can see there's a relative loss of mass on the coast, meaning sea level declined, and that's associated in the lower row with relative decrease in density associated with cooling over much of the subtropical North Atlantic. Whereas in the 20-teens, kind of the opposite is observed. You see a gain of mass on the shelf, particularly south of Cape Hatteras, and offshore, you see this broad pattern of red associated with sea level rise associated with density change or warming. And so, yeah, the spatial patterns of both the near coast manometric sea level change and offshore steric change suggests a linkage. And with this model, I kind of tested or evaluated this hypothesis. And so the first thing that struck me was the, how do I want to say that? The kind of the spatial pattern of this warming trend it can be associated with a particular water mass in the North Atlantic. That being what has been traditionally called mode waters, which are a lens in the North Atlantic, or a lens of upper ocean waters that have typically been cast as 18-degree water. And what I'm doing here is I'm characterizing the spatial extent of this water mass in our model. In the left panel, I'm showing kind of the lens, how it's distributed area-wise, and then the middle and right panels show the deeper depth and the shallower depth of this lens of water. So it spans about the upper 500 meters or so. And what I've done is I've tracked the heat content change of this water mass in particular over time. But before I get to that, sorry, I need to introduce this idea that's kind of the crux of this story. It's one in which these changes offshore, where I've identified subtropical mode water as being an important water mass to keep track of, I want to relate that to coastal sea level change. And to do that, I invoked this model that was really explored in a paper by Felix Landerer from 2007. I applied it in the Gulf of Mexico in a paper that came out earlier this year. And the equation is down on the left. I'm not going to explain it in too much detail other than step through this schematic, in which if you imagine looking cross section at some 4-layer slice of ocean, this is the coast on the right. If you were to imagine warming in some subsurface layer, that's this red band, you would cause a sea level response, a steric sea level response in panel B that would result in some adjustment process where sea level in an equilibrium state has risen everywhere of the model, everywhere over the domain of this quote model, contrary to panel B, where you see this kind of sea level gradient or stepwise decrease. And importantly, in this equilibrium state, you would see a signal in ocean bottom pressure, or a signal in manometric sea level, if you can equate the two, which shows that for a given amount of subsurface warming, you would expect sea level rise at the coast that would imprint as a mass change. So putting this idea together with kind of what I was saying on the previous slide of tracking subtropical North Atlantic mode waters and their heat content change over time, we test this hypothesis. So this is a time series of subtropical mode water volume mean potential temperature over time, over the 30-year run of this model. And you can see a strong seasonal cycle. That's what all these higher frequency wiggles are. But the lower frequency, you can really look at any of the colored lines here. They're all almost the same thing. There's this lower frequency pattern of variability that, again, like previous talks have identified, are related to the Gulf Stream position and NAO. But when we apply this redistribution model that I was just describing in schematic form to try to estimate a coastal response to these offshore density changes, we find really, really nice agreement. So what's being plotted here in this time series is coastal or near coast manometric sea level in blue, and my redistribution model in orange, meaning we expect changes in near coast sea level to be driven by offshore changes in heat content that drive steric sea level anomalies. And importantly, this redistribution occurs only if and where density change occurs below the continental shelf break. So if you go back to that schematic that I was describing, you only get this redistribution if you have subsurface warming that doesn't fall over the entire areal extent of the region being considered. So if we go back and we compare, or if we correlate this predicted near coast sea level change with sea level everywhere, we get this map where the correlations are in both panels here, but the right panel removes the seasonal cycle. And so when you consider interannual changes, you can see this break at Cape Hatteras really appear, where north of Cape Hatteras, there's really no correlation, no positive correlation with offshore subtropical mode water heat content change. So the final piece that I will show today, I'll skip this figure and show spatially, going back to those two periods over which I fit trends at the beginning of my talk. The upper row shows the same figure zoomed in, or the same fields are being plotted. This is manometric sea level change over the earlier period and the later period. You can see pretty strong contrast between the two. And the lower row shows the anticipated manometric sea level change that's a result of this mass redistribution. And so you can see the spatial patterns of this predicted change. Again, this is a trend over a 6-year period, really aligns nicely with that of that we diagnose from the model output itself. And so to conclude, I'll just say that we, having realized this connection between coastal sea level and offshore density change, and this mechanistic connection, I should say, with that, we can better understand and anticipate lower frequency coastal sea level changes in the future, and work towards better observational monitoring using float measurements from Argo, and really improve our projections from a mechanistic standpoint. So thank you very much.
Thank you, Jake. So I believe we have time for one question. If there's anybody in the audience that has a question, or anybody online, you're welcome to raise your hand. Peter, go for it.
So your schematic was looking like the influence was directly to the west on the coast. Why isn't the influence spread out on the coast? Can it go north and south as well as due west?
Yeah, thank you for the question. That's a good question. One of the difficulties in applying this model, this kind of schematic idea of mass redistribution, is that it's a one-dimensional model. It doesn't accommodate or allow for horizontal variability in any of its diagnosing of density change and then predicted coastal sea level change. And so the difficulty in applying this model to like the entire North Atlantic is defining an appropriate region in which changes outside of that region are unaffected by changes within the region. And so in the work that I've done, I've argued that say north of the Gulf Stream, or the Gulf Stream serves as kind of a barrier to signals propagating north and northwest from the subtropical North Atlantic. Yeah, I'd be happy to talk more about it and hear your thoughts if you have any suggestions. But yeah, it is a limitation of this model is that it is one-dimensional.
Hey, thank you. So we're going to move on to our next speaker, who's Chris Little, and he's going to be talking about insights into the representation of coastal sea level variability in global high-resolution models. So right now we are seeing your speaker view. Yep, that looks great. Go for it.
Looking better. It's never on the right screen, but I'll do my best. Okay, so yeah, I am targeting this talk to the audience and to the CESM workshop, substituting CESM 1.3 in here. That is a model that's been talked about a lot in the workshop so far. That should save a little bit of time. We have a set of simulations, great set of simulations that have looked at this model in both high and low resolution configurations. And right now I'm going to be talking about the representation of coastal sea level variability in observations and in the high resolution, well, actually comparison of high resolution and low resolution CESM 1.3. So I want to thank co-authors, especially Steve and John, and also the NOAA Coastal Inundation Task Force, which we're doing some new work that is helping sort of give some guidance into how to think about high resolution modeling in the context of seasonal to annual sea level prediction, which is giving some direction and some application of this work that I think is interesting on its own, but I want to make it relevant. Okay, so why do we want high resolution when we look at coastal sea level? The first has been talked about often over the course of the workshop. These small-scale processes, whether they're ocean-only or coupled, can influence any large-scale quantity of interest, right? We can get different solutions, and hopefully they're better. But then when we talk about coastal sea level, and I think the talks that we've had so far have kind of alluded to this, we have physical constraints and local forcing, which can impose sort of dramatically different sort of small scale constraints on the ocean circulation. And because the water column is thin, that local forcing can have a significant effect. So if we look at this animation, you can notice right off the bat, so this is monthly sea surface anomalies in CESM 1.3 HR. Very coherent sort of eddies in the open ocean on monthly timescales. But then when you get to the coast, you see a much more sort of coastally coherent variability. And if you look in detail at the coast, you can see trapping of signals in the along coast direction, where you can have variability that's expressed that's much different close to the coast than when you move offshore, even if you're still on the shelf. And so the idea with high resolution is that we're going to be able to see those coastally resolved or coastal near coastal processes, be able to compare to tide gauges, and we may actually have a better ability to study these cross-shelf variations using high-res models than we do using data sets like altimetry, which actually degrade near the coast. So when we use these models, especially when they're in a global configuration, we can look at short spatial scales. So these coastal small scales or coastally trapped phenomena over long time scales. And we can see from the studies that have come out so far that you can end up with quite different results. So if we look at one from Dapeng Ling a couple of years ago now, but using these same sets of simulations but run into the future, you can see that in the low resolution configuration at a degree in a couple configuration going forward to the 21st century at a degree, you have sort of systematically higher sea level change or trends in sea level north of Cape Hatteras and lower ones south of Cape Hatteras. And if you go to high resolution, you can get a dramatically different sort of spatial structure, including the offshore to coastal gradient. And if you look at that along shelf gradient, you have a much more uniform rate of sea level change over that 100-year period. And it can be actually much more dramatic if you look at the time series. So anyway, I think that there's a lot of opportunity, but because there are trade-offs to using high resolution, computational expense, uncertainty quantification, and those models may also still be biased, we want to quantify and understand these resolution-related improvements specifically at the coast. So I'll talk briefly about this paper today that gets at that question. So this paper was submitted almost a year, actually over a year ago now, and is still in review after just one round of review. So I don't know if it's ever going to come out, but would love to share it with you. I can send a draft if you're interested, and I'll give a quick synopsis today. So anyway, we're comparing these forced ocean sea ice simulations, just looking at differences in resolution that are resulting from the ocean model. Two configurations, one at a 1/10 of a degree, one at a degree, both forced with JRA 55 forcing. We look at 3 different forcing cycles 2 to 4 in the OMIP2, following from the OMIP2 protocol. Forcing applied is identical. We're only looking at sea level variability over the 93 to 2018 period. I'm looking at annual and longer sea level variability, so annual to multi-decadal. We can talk about other frequency bands. I've done some analysis at monthly and shorter timescales as well. And then we're correcting the tide gauges to give us as close as possible match or consistency with SSH in the models. And to do that, we remove inverse barometer effect and global mean sea level. Okay, so in this study, we do a point-wise comparison with 300 global tide gauges of the detrended low-pass filtered sea level. So I'm just showing an example of that here. We're looking at sea level along the US East Coast, looking at all the tide gauges, which are shown in black stars along the coastline, and then taking the closest grid point from each simulation. So LR is a degree, high resolution is a 1/10 of a degree, so the points are a little bit closer, or a lot closer in the high res case. And then most of what I'm doing here is just simple aggregate metrics, comparisons of variance and of correlation in order to sort of elucidate what's happening at a global level. But we do have time series and mismatches, misfits at each location. So there's a lot more information than what I'm going to be presenting here. When you do that comparison, which I'm showing the time series from 1993 to 2018 off to the right, you can see that tide gauge variability with the black line, low res in blue, and high res in orange. And you can see that the high res variability is much more enhanced. We're matching some of the wiggles, and I think we're matching those wiggles better. We'll quantify that later. But the other thing that you notice is that depending on the different cycles, you can have a much significantly different temporal evolution. And that's because even though the forcing is the same on the ocean has intrinsic variability, and that's brought out much more when you resolve down to these scales, so eddy resolving scales. We have better agreement in some respect of this Charleston tide gauge with the high res, but also some decrease in the correlation due to the fact that we have this unphased variability. So in order to summarize for this brief talk, the results of the paper, I'm just going to show this main this figure of sort of primary results. So what I'm showing is the normalized increase in the variance at each tide gauge. So the high res variance minus the low res variance over the tide gauge variance. So how much of an increase do you get? Up to 100% here on the scale. So the red regions that you see, the red tide gauges, are regions where you dramatically increase the variance. Greens and blues, you have a decrease in variance when you increase the resolution. The panel down to the lower right side shows correlation. So how much does the correlation increase or decrease when you increase the resolution? And again, you see some red areas where you have an increase of 0.4, 0.5 in terms of the correlation. You're phased much better with the observations, but then you also see some decreases. So there's a lot of information here, but a couple points that I want to bring out are that you tend to have agreement or disagreement between models and observations at regional scales. So most tide gauges are pretty good indicators of what's happening regionally in terms of whether you're improving or degrading your with respect to your metric. The second is that in marginal seas and in western boundary currents, you see a much a much more enhanced variability in sea level, which is kind of what we want to see. We want to see us resolving those enhanced regions of variability as you get near the coast and just eddy-rich regions of the ocean. So you can see that in the top plot, areas of red in the Kuroshio and in the southeast US, for example. And in general, you have an improved correlation. Some places it's larger than others, but in some places like the Kuroshio off Japan, you have a degraded correlation. And that's coming from the fact that even though you have the forcing the same in both models, that high resolution model has increased intrinsic variability that might be unfazed, and you can result in a degraded correlation. And so, you have these discrepant regions or west boundary current regions in the Kuroshio and the Gulf Stream, and in one you're increasing the correlation when you go to higher resolution, in one you're lowering the correlation. And my suspicion, which I'm working on in another project, is that that relates to the degree to which the variability that you're seeing is intrinsic or forced, and how important those relative contributions are in these different regions. So just diving in a little bit more into these representative tide gauges in each region, if we look at Helsinki, which is in the Baltic Sea.
I'm going to give you a 1 minute warning. Sorry.
Wow, I always go long, even though I try to cut it short. Thank you. I think I'll jump through these, except I will leave with the point that in San Francisco, you have relatively almost the same result in the SSH time series and the low resolution and the high resolution. So there's places where even you have 100 times increase in the horizontal resolution, you're not actually improving your variance or your correlation that much. So which brings me to the general conclusions, which are there are regional scale differences in the improvements that you get at a high resolution, at an increased resolution. You generally have improvements, but you introduce this intrinsic variability at high resolution, which poses challenges for model evaluation. And also we have to think about it in terms of predictability and forecasting. That's a different talk. And then many regions don't see substantial improvements. And so most of this work was focused on tide gauges, but we did look at comparisons with altimetry. And when you look at the upper left, this is the ratio of variance in high resolution versus low resolution. You see the greatest increases are in western boundary currents, the Southern Ocean, but you have a large region of the sort of low latitude ocean where you don't have very large increases in the variability in high resolution. And then if you do that comparison with altimetry instead, you have a lot of greens and yellows or greens in the lower latitudes, which means that the variability in sea level, even though we've increased the resolution by a factor of 100, is still underpredicted. And so that's a question that I haven't gotten out yet, but I'd love to talk about with people who are looking at CESM in new versions. We've done a couple things to look at it, but I think it could use a little bit more exploration. All right, I'll just leave the acknowledgements and thanks for your time.
Hey, thank you, Chris.
Mm-hmm.
So we do have time for an extremely quick question. If anybody from the audience might have a question for Chris, yeah, please.
Hi, Chris. Thanks for the nice talk. You had mentioned that you looked at shorter timescales. I'm wondering if you could just give like a one bullet summary of what you saw for, I don't know if you looked at sub-seasonal timescales or seasonal, something shorter than a year, maybe shorter than a month.
Yeah, I mean, one thing, if we could go, I actually can't go back to that animation there, but you could definitely see that as you, in that one region that I was focused on, that you have a lot larger variability in that coastal zone in the high resolution model. And it does match up well with the tide gauges. So I can't give like a systematic answer across the global ocean. But I do think that the improvements at these lower frequencies, you're also seeing improvements at higher frequencies too.
Thank you.
Yeah.
Hey, thank you again, Chris. So next up, we have John Fasulo, who's going to be provocative title, CSM suggests an underestimation in current regional sea level rise projections. So, yeah.
Right.
Okay.
Great. So not only has this talk not been in review for a year, but I actually started this work shortly after getting the invitation to present here about a month ago. So it's a bit of a younger presentation and material, but it touches on a number of issues that both Steve Neerum and myself have been thinking about in relation to the regional pattern of sea level rise and how it relates to altimetry and the data that we see from altimetry. So it also touches on a couple of the issues we discussed yesterday in the plenary, such as the pattern effect and also the benefits and trade-offs of high resolution modeling. So I think it is relevant to our session. I'm not getting any. Here we go. All right. So for people who aren't aware, this is the altimeter record, the long-term trend in sea level height since 1993. As measured by a series of radar altimeters in orbit around the Earth. People are probably very familiar with the global rate of rise of average of 3.6 over this period, millimeters per year, but actually that began as around 2+ millimeters per year and is now over 4 millimeters per year. So we have this acceleration as well. And then on top of that rate of rise, you have a strong regional pattern of rise as well. And this can double the effective rates of rise in some locations, and it can offset them entirely in other locations. And so the top plot here is with the, is there a laser pointer on this? Great. Nice. Okay, great. So the top plot is the raw altimeter data, and the bottom plot is with the global mean removed. And so that really emphasizes these regional features that you see in the satellite data. And then the trillion-dollar question is whether or not this pattern is forced. Is it indicative of an inherent climate response to forcing, or is it merely the reflection of internal variability, such as changes in the phase of the IPO? Because the consequence of those two interpretations is one, it will reverse in the near future to make an even pattern of rise everywhere. And then the other interpretation suggests that this pattern will continue. And I think if we were to bet on it, we would bet on this pattern continuing for some very fundamental physical reasons. And then the other thing you see in the satellite data that I think is very important is the fact that you have lots of structure, not just kind of broad wave number structure, but actual structure representing fronts in the ocean, currents like the Kuroshio and the Gulf Stream, and then eddies even. And so you can see areas of standing eddies coming off of certain features near the Agulhas here that project onto this pattern, the sustained pattern of rise. So this is not noise, but probably signal related to climate change. And then, given this, how well would you expect a 1-degree model to do in simulating trends in sea level? These are all open questions, and certainly the pattern effect that we talked about yesterday comes into focus here in the Eastern Pacific, where you see a very La Nina-like pattern. So what are the answers to these questions? I figure I will start at the end and give you my bullet points that I can then fill in as we go. But shortly, to summarize, CSM 1 and 2 both suggest that the forced regional sea level rise pattern is emerging from the noise of internal variability. And the big question is, can we estimate this pattern to predict things into the future? And the main point I'll make here is that, yeah, we can do that with models, but actually the models have major biases. And the multi-model mean from CMIP 6, which is currently what's being used, and this relates to what Wei Jing was saying before, it actually has large structural differences across models, and that results in an underestimation of the magnitude of the forced response when you average models together. And then the patterns are also systematically biased, so they're not very useful for projecting the future. So you have this large model and structural uncertainty, which is issue number 1. You average together different models, you come up with a very muddied, bland pattern that doesn't reflect the actual magnitude in nature. And then most of the standard resolution models I'll show will fail to generate the spatial variability that we see in the pattern, and also the broad feature of the pattern as being La Nina-like. And we have these tools now that we can use that are related to CESM. We have large ensembles that we can explore this topic in, and we also have high resolution that Chris was just discussing. So those are the tools that we're going to use. So just quickly, the method used by AR6 to estimate the future pattern of rise, what's called also the dynamic sea level pattern, is based on the facts framework that's summarized in this manuscript here by Bob Kopp. This is I think I'm going to jump forward. Okay, good. So basically, this takes the multi-model mean from CMIP6 and it scales it by the global thermosteric sea level change. So the pattern is this average across many models. And of course, if you're involved in large ensembles, you know that getting at the force response by averaging lots of models together is not a good idea. But that is the path that's been taken here. And implicitly, it really relies on the assumption that both the force response and the internal variability across models is consistent. All right, because otherwise you average them together and you're just going to get a meaningless pattern as a result. Some of the background here is we have this altimetry pattern in the top with all the features that I mentioned before and the global mean removed. You have this La Nina-like pattern. Now at the bottom is what you get from CMIP6 multi-model mean. Two main points here. One is the ratio of spatial variance, this 1.4 number in the altimetry, and the multi-model mean is vastly different. So, you know, you're more than a factor of 2 greater than the altimetry. And now this is 1 member versus what's an estimated force response. So you expect some difference, but is that reasonable? And we can test that in the large ensembles. And then the other thing is that the pattern in the bottom panel really doesn't resemble the pattern in altimetry much at all. The pattern correlation is about 0.18. So are these things plausible? One way of summarizing many different spatial patterns is with Taylor diagrams, and people may not be familiar with Taylor diagrams here, so I'll quickly go through them. This is a polar plot where this angle indicates the degree of correlation with some reference benchmark, and this distance through here, you know, the distance from the origin, represents the relative magnitude of a pattern. So this is all against some reference here for the CSM1 force response. And here you have the individual members of the large ensemble. So this is how much internal variability can cause deviations in the pattern correlation and the strength of the pattern, the spatial variance in the pattern. And so you have this very well-defined area here. This is where a VISO is, right? So we're only correlating at about less than 0.1 with the force response. And our variance is more than a factor of 2 greater than the force response. It's greater than any ensemble member. And like I said, it's way out here with the pattern correlation. So you can't interpret the differences between the CSM1 force response and the aviso pattern by internal variability. Now, you can't make statements about how these individual members relate to aviso, so that's more of an apples to apples comparison. So on this plot on the right, we have comparisons where our reference is now aviso. And you could ask very, simply, what is the pattern correlation and what's the variance of these individual members from the large ensemble relative to the satellite? So now we're looking at 1 member versus 1 member, and there's almost no correlation between the two. And the spatial variance is actually quite different. So aviso is a factor of 30% stronger than the average member from the large ensemble. So you can do the same thing with CSM2, and now you have 100 members. You have this well-defined cloud of what internal variability can get you in terms of these disagreements, and then you have aviso out here. So it's very distinct from anything you see in the behavior of the low-resolution CESM2. The CSM2 force response actually should be here. Sorry, that's offset. But same question. Okay, well, what if we use aviso as the reference? We get very little spatial correlation. And in fact, the average spatial correlation is negative between members of the large ensemble and aviso. So these things seem to be completely from different worlds. And there's a reason for this. And that is, I think that in part, at least, these are low resolution models. You can do this for all CMIP6 members. So now I have 300 different members from CMIP6. The vast majority of these are at 1 degree or less the resolution. And some of them are high resolution, actually. And so you start to get greater variance from the high resolution members out here. There are enough members of some of the models that you could consider them their own force response. And this is the CMIP6 multi-model mean. So the take home from this figure that you want to get is the fact that the force response from individual members don't correlate that strongly with the multi-model mean. Therefore, they average out. Their variance is on the low side, certainly relative to Aviso. And you have this broad scatter of CMIP6 simulations, again, with not a very strong correlation to the altimeter data. And so what gives, right? I think one of the things that is going on here is the fact that you get fundamentally different behavior from the high resolution than from the low resolution model. So this top right is one member of CESM1. I call it low resolution. It's 1 degree. It's a standard pop model. This is what you get from IHASP. So we've now gone to 1/10 of a degree ocean. It's the same sort of spatial pattern, and the change in magnitude is greater than a factor of 3. So significantly more spatial variance. According to Dave Lawrence yesterday, member 10 actually has a pattern that resembles the observed pattern, at least in SST, that does have a bearing on SSH. So TBD, I can't get my hands on member 10. But I think right now the jury is out on what high resolution can get us. But we do see this kind of consistent behavior across CMIP6. So 1 minute. Great. So top right here is a 1/2 degree model from CMIP6. The spatial pattern is unremarkable. It's maybe a little bit stronger than your average CMIP6 models. These other 3 fields are from ocean models that have a 1/4 degree resolution. And you can see this massive jump up in spatial variance in all 3 of these models. And likely they overdo it. And it also seems like CESM high resolution overdoes it. And so this will be maybe a way of tuning the model going forward. If we could aim for the altimeter pattern, it certainly would help sea level research, but it's just one probably target we want to take. So just to conclude, this is what I've already told you basically, is that we have this problem with the pattern in CMIP6 models. The multi-model mean does not resemble the altimeter data. Individual members do not resemble the altimeter data. And there's a lot of evidence suggesting that we're underestimating the magnitude of the forced response using those simulations. There's also the systematic error in the pattern and magnitude, perhaps, from some of the high resolution simulations, and they really fundamentally change the way that sea level is represented in the model. And so it's something we have a lot more work to do. These are, like I say, this is all a month old, but it raises a number of questions. And the chief question is, how do we go forward from here? And I think this relates to our next talk. I think it's an open question what high resolution modeling can get us with sea level. We'll see. People are going to look at IHASP very closely. But I have my doubts. And I think that other approaches are to use statistical methods or even machine learning methods to directly extract the forced response from the altimeter data. And so that's also a promising path forward. So with that, I'll just stop. Thanks.
Okay, we do have time again for super quick question. Anybody have a question for John? Oh, Peter is up on his feet.
So you've only got 10 members with the high res. Do you need as larger ensembles with the high res to get the variability that's possible?
Right. I mean, so in terms of narrowing the forced response to within a given error bound, we don't know yet the relative contribution of the additional variability to the noise and the forced response. So if it contributes primarily to more noise, you're going to need more members, right, to actually resolve the forced response. If it increases your signal to noise, which could happen, we don't know, then you need fewer members. Ultimately, the number of members you need depends on your science question, but it's that offsetting influence that we don't. I don't know the answer to yet, but my understanding is September 1st. So for IHAS 10 members for the community. So, right.
Okay, so I would like to welcome up our final speaker for the session, Ashley Bayless-Manley, who is going to be presenting on using CSM2 large ensemble to evaluate CSEOF separation of internal and forced components of sea level change. Okay, and it's just that one. And if you want to point to the screen. Yep, great.
Perfect. Thanks so much. Hi, everyone. Good. Okay, it works. My name is Ashley Bayless-Manley. I'm a postdoc at University of Colorado Boulder. And today I'm going to talk to you about using the CESM2 large ensemble to assess a new data analysis technique. It's called the CSEOF technique, and we're going to assess how well it can separate internal and forced components of sea level change. But I want to comment that you can use this data analysis technique on any type of data. Okay, so a map of what we're going to talk about today. We all know that internal variability can obscure the forced response. CSEOFs have been used to reduce the impact of internal variability on observational data sets, for example, the satellite altimeter record of sea level. But based on that data alone, it's not clear, first of all, how much internal variability remains in the CSEOF corrected data, and secondly, how well the internal variability and the forced response are separated from each other by the CSEOF modes. It would be a problem if they were tangled together, and so we're going to assess that today because we have a luxury given to us by the CESM large ensemble, and that is that we can derive the forced response. So we're going to exploit that knowledge today to assess the efficacy of CSEOFs at removing internal variability. The way that we have approached this problem so far is to take the monthly sea level data from 100 members of CESM2 and to calculate the rate map. The data spans 1993 to 2023 to be consistent with the satellite altimeter record. It's difficult to glean much information from 100 maps of rate of sea level rise, right? So the two important things that we want to focus on really are, first of all, the large ensemble mean. We're averaging across these 100 members. It smooths out, it gets rid of any differences and keeps what's the same across those 100 members. And in other words, it is the forced response. And secondly, we look at the standard deviation of the rate map across those 100 members, because that tells us the influence of internal variability. It shows how much internal variability produces differences in the rate map of sea level across those 100 members. So we're going to use these two tools to answer two research questions. The first is, to what degree can CSEOFs increase the correlation of the member-specific rate map with the forced response? And secondly, to what degree can CSEOFs reduce the standard deviation of the rate map across members? In other words, reduce the influence of internal variability on the map of sea level rise, the rate, I mean. Okay, and I've put the answers up here because it's such a quick talk, and I'll walk you through how we got there. Okay, so CSEOFs are like EOFs, but a little bit more complicated. And I'm banking on the fact that everyone knows what an EOF is. It's an empirical orthogonal function. Some people call it principal component analysis. The gist is that the CSEOF decomposition breaks a data set into modes, where each mode describes a different amount of variance in the data. But what makes them cyclostationary is that the spatial pattern can vary on a nested period. So taking a look at mode 1, the spatial pattern starts out looking something like a La Nina event that persists through the first year of the nested period, and then that transitions into something that looks more like El Nino into the second year of the nested period. And it's important to note that we couldn't reproduce the variation in the spatial pattern just by applying a scaling factor of -1, which is what you're constrained to when you use EOFs. So the real benefit of using CSEOFs is that we can capture periodic variations in the spatial pattern, which we think that modes of internal variability probably comprise. Okay, so I apply the CSEOF decomposition to 100 members. Sorry, this is such a busy plot. What I want to communicate to you is that we decompose the sea level data from each of the 100 members into a number of modes. And here I've marked in green any mode that we've identified as internal variability. I'll tell you the method that we use to do that shortly. But first, what I want to point out is that in some cases, a lot of the variance is identified as internal variability, and in some other cases, none. So that's really interesting, but it's not something that I can properly explain to you without going through the method first. So let's jump into that. So the way that we identify which modes represent internal variability and should be removed to isolate the forced response is we calculate the correlation between the member-specific rate map and the forced response rate map. So that's plotted here as the black dot, and we similarly calculate that correlation after removing CSEOF mode number 1 or 2, or any combination of the first 4 CSEOF modes, since it's the low number modes that comprise the largest amount of variance in the data. So I wanted to show this very busy plot so that you get an idea of how much spread there is in the correlation with the forced response, depending on how many CSEOF modes are removed. But we can glean a bit more information from this condensed version of the plot. So here I'm only showing the correlation of the original member rate map with the forced response and the new best correlation with the forced response after removing some combination of CSEOF modes. We see that in some cases, there's a pretty marginal improvement in the correlation, and in other cases, a really significant improvement in the correlation. So on average, it's really quite marginal. We improve it from 0.69 to 0.72 averaged across the 100 members. But I think that the key really is that we don't know which one of these members is the best representation of the satellite altimeter record of sea level. And in some cases, we can improve the correlation by as much as 0.15. And so I think that actually that is really quite promising. Something else that we can look at to assess how well the CSEOFs are doing is the degree to which we reduce the standard deviation of the rate across 100 members. So here's the standard deviation of the rate after removing CSEOFs compared to before. And that's the optimal number of CSEOFs are removed to maximize correlation with the forced response rate map. And in some regions, we can improve it by as much as 50%. So we did a similar analysis on independent regions. We separated out the Indo-Pacific and the Atlantic. In general, the results are really quite similar. We see marginal improvements in the correlation if we average across all the members, but there are always some that are improved by quite a lot. For example, we can improve the correlation with the forced response by 0.25 or 0.21. Okay, so that brings me to my conclusions, which are, firstly, we asked the question, how well are internal variability and the forced response separated by the CSEOF modes? We attacked this problem by assessing to what degree we can improve the correlation with the forced response rate map. One idea that I have going forward to do this differently is, instead of identifying modes that represent internal variability based on the rate map, do this by optimizing for, well, selecting modes based on how similar they are to the member-specific PDO index, for example, or the ENSO index, or other indices that we might calculate based on the member-specific data. And then secondly, how much internal variability is removed in the CSEOF corrected data. We assessed that by looking at the standard deviation. And the answer was we could reduce it by as much as 50% in some regions. But this work, it's still in progress. So if you have suggestions, let me know, and I'll leave it there. Thanks.
Hey, thank you, Ashley. So we do have time for a question. If there's anybody in the audience, I know it's a little bit late, but anybody in the audience or online? Yeah.
Yeah, really interesting talk. I'm curious. So, I mean, this is doing a lot of pulling out that variance, but there's still a big question, especially in the individual ensembles, of how much you are mapping whatever the unknown truth is, right, to what you're able to pull out. And I'm just wondering, in those individual members where you were seeing there was no internal versus forced variability and things like that, to what degree do you think some of that is ultimately just bad solution versus actual variability between members? And what sort of uncertainty quantification can you do to get a sense of that?
That's a tough question. I thought a fair bit about why there are some cases where we identify no internal variability that we can remove, like no modes are selected. And I think that there is sort of a multi-pronged answer. It could be that in those cases, internal variability averages out over the 30-year period. And so it doesn't it doesn't improve the correlation with the forced response, so we don't identify it. It could be that the pattern of sea level trend in that mode is orthogonal to the forced response, and so makes no difference, and so we don't identify it. Yeah, I thought that I had a third prong in mind, but I can't call it up right now. But yeah, I think that by identifying the modes maybe in a different manner, we can get a sense of what the best way to do this is, and how successful the CSEOF method really can be.
Okay, thank you. And thank you again, Ashley. And let's have a round of applause for all of our speakers. So that concludes our session. I would just like to say that I think there is a happy hour at Sanitas starting at 6. Gunter. Oh, okay. Jim says yes. I got it right.
Follow Jim.
Follow Jim. That's exactly right. He knows where the beer is. If you need directions to Sanitas, I believe that at the front desk there are little handouts that provide you with a map, because it is within walking distance. So thank you for joining us and for staying a little bit over time.